Hey guys, Andrew here. Welcome to Chapter 2 of our problem-solving series for physics. In this chapter, we're going to focus on one-dimensional motion. If you've missed the prior chapter, take a look in the description below. I'm going to leave a link. Also in the description below, I leave timestamps for all the questions that we're going to cover, the general concepts or what we're solving in each question. So in case you have a specific question, take a look in that description. You might be able to find a very, very similar question to what you're looking for. Without further ado, grab your pen, pencil, and a calculator, and come on, let's take a ride. Number 1. Find the following for path A in figure 2.59, the distance traveled. All right, so let's first take a look at part A and path A. So over on the right-hand side of the graph, we find part A there in green. So we have to calculate the distance traveled for path A. So remember a very straightforward definition for distance. I'll write it down here. So distance, right, is basically a measure of the ground covered. Measure of the amount of ground covered. Whereas displacement, and we're going to get to that in part B, but I might as well just define it right now. Displacement is essentially the difference between the starting point and ending point. Between the start and ending point. Okay, so armed with those definitions, let's take a look at path A. So the distance it traveled. So let's take a look at where it started. It started at a value of 0. It ended approximately, it looks like at a value of 7 or so, right? If I were to dash this all the way down, looks like that ended at about a value of 7, right? These are both in meters. So now, for part A here and path A, the distance would just be the difference, right, between 0 and 7. So we would take 7 meters minus 0, and that comes out to be 7. So that's simple enough. Okay, part B. So now we are dealing, now it says, part B says the magnitude of the displacement from start to finish. Okay, so again, same thing for path A. Okay, so let me just erase some of these markings here. So path A again, where are we starting? We're starting at 0 meters, right? That's the start. And we're ending, it seems, at approximately 7 meters. So for part B, okay, the displacement, which we're going to call x, okay, is equal to, the technical definition for it is equal to the final displacement minus the initial displacement. So since I'm doing a final minus initial, really I need to put in a little triangle here that stands for delta, that represents the change in displacement. Okay, so let's plug in the values. So my change in displacement was the final displacement value, which was represented by 7 meters, minus the initial of 0. So my displacement was a total of 7 meters. Now, they didn't ask for the sign, they wanted just the magnitude. But if you plug in the values appropriately into this formula, then the sign will always come out correct. In this case, though, it really wants the absolute value of it, since it just wants the magnitude, not the sign. But since it came out to be positive, it won't do anything if we take the absolute value. So that's the final answer for letter B. Notice it's the same for letter A, and in this particular problem, the distance happened to be the same as the displacement. Moving on to now part C, it says the displacement from start to finish. So again, displacement is the same thing, right? You're going to notice it's literally going to be the same calculation. So final minus initial, 7 minus 0, and that'll equal 7 meters. So again, they don't want the absolute value this time, but it is positive. So all three of these values work out to be the same in this question. Number 2. Find the following for path B in figure 2.59. Letter A, the distance traveled. Okay, so let's take a look at path B here on the right-hand side. It's there in like a bluish purple. So we have to find the distance traveled. So recall that the distance is simply the amount, right? Amount of ground covered. Okay, so let's see. It looks like B is starting at 12, right? And it's ending, it looks like at about, if I were to draw a little line down there, looks like it's ending at about 7, right? That looks like it should be about 7. So just make this a little neater. So that should be about 7 meters there. And that's 12 meters. So now the distance that it traveled is just simply the ground that it traveled. So if we were to think about, a formula, it would simply be this, like the distance d would be equal to distance 1. In this particular problem, it would be a subtraction, minus distance 2. So distance 1, put the larger one first because the distances will always be positive, or need to be positive because they are considered scalar quantities, meaning they don't have a direction. Okay, we'll get into that a little later and probably some problems in the future. So it'll be 12 meters minus 7 meters. Okay, so that simply works out to a value of 5 meters. So that would be the distance. Okay, so that is the answer for part A. Let's take a look now at part B. Okay, just erase some of these things up here. There we go. So let's take a look at part B. So the magnitude of the displacement from start to finish. So recall that B is starting at 12 meters and ending at 7 meters. Okay, so let's write down our displacement formula. So the change in displacement is equal to the final displacement minus the initial displacement. Now, since they are specifically just asking for the magnitude of the displacement and not the displacement itself, simply take the absolute value. Okay, so now the final value was 7 meters minus the initial value was 12. That means it would be a negative 5 meters. But again, since we just want the magnitude, we don't want to know the sign, it would simply be just 5 meters. Okay, wonderful. That takes care of part B. And now part C, it wants to know the displacement, not the magnitude, but the actual displacement. So again, write the formula, change in, looks like in, I don't know what sign that is, change in x, right? Change in displacement is equal to the final displacement minus the initial. So no absolute value sign now because we want to know the displacement, magnitude, and the direction. And that's just going to be 7 meters minus 12 meters because it's the final value minus the initial. And now the displacement value is negative 5 meters. And that's it. Number 3. Find the following for path C in figure 2.59. Letter A, the distance traveled. Okay, so remember that the distance is equal to the amount of ground covered. So let's take a look at, in the graph, path C. So it looks like I don't know, we can think about this as somebody who's walking. They're starting at a displacement of 2. Okay. Then they're walking all the way on over to, it looks like about a displacement of 10. Okay. Then they turn back around and they go from 10, it looks like, to about 8 right here. And then they turn back around again and they go back to 10. So if we had to think about the total distance covered, right, we would be thinking about the total ground that they had covered. So I can think about this problem in essentially, 3 points, right? The first point from this location to this location. The second point will be from this location to that location. And then the third part will be from this location to that location. And we would sum everything up. So the distance will be equal to, we'll call it d1 plus d2 plus d3. Okay, distance will equal then the length of d1. Now be careful, they went to 10, but they started at 2, right? So that means they went 8 units, right? So I'm going to say 10 minus 2, that's for d1. Plus then, the distance covered in d2, which I am describing going from this point to this point. So that would now be 10 minus 8, right? Because that would give me the distance covered there. And then plus d3, which would go from this point to that point. And that would be, again, 10 minus 8. Now, why am I doing 10 minus 8 and not 8 minus 10? Because I want all the values to be positive. Distance is not a scalar. Distance is a scalar. It's not a vector, so it doesn't have direction. So, I mean, you could have, found the distance between these 2 points, 10 and 2, any way you like, or 10 and 8. You could have subtracted 2 from 10 or 10 from 2. Just always take the absolute value, and you'll be fine. So 10 minus 2 is obviously 8. 10 minus 8 is 2. 10 minus 8 is 2. So the total distance covered in part A is going to be 12 meters. Great, so that takes care of letter A. So now for letter B, okay, let me go back to my picture and erase these points. So now for letter B, it says the magnitude of the displacement. Okay, so remember our formula, right? The displacement is equal to the final displacement value minus the initial displacement value. And if I want to know just the magnitude, I'm going to take the absolute value of that. And why? Because we don't need to know the sign, just the amount, the magnitude. So where do we start in letter C, going back to the graph? We start right at a displacement of 2. Where do we end? We end at a displacement of 10. And that's it. I'm not worried about all the ground covered in between. I only care about, when we're calculating displacement, I only care about the start and the end point. So what this means is that when we plug it into our formula, the final displacement was 10 meters. The initial displacement in the problem was 2 meters. And now therefore, my displacement is equal to 8 meters. And that was always the absolute value and comes out to be positive. So that's the displacement, and specifically the magnitude, right? Because I took the absolute value. So now you can notice that there is a difference between these two, right? Between the distance and the displacement. Okay, so letter C. Now it wants to know the displacement, not just the magnitude. So very easy. So use the formula again. Displacement is equal to the final displacement value minus the initial. Okay, so the final displacement for letter C was, again, 10 meters. The initial was 2. So all we have to do is plug it in, and we get a value of 8 meters. So the magnitude of the displacement and the displacement itself, considering the sign, happen to be the same in this problem. Number 4. Find the following for path D in figure 2.59. The distance traveled. All right, so letter A. Let's write that down here. So let's go to, on the graph, let's go to path D. Here it is. And we have to calculate the distance, right? So remember, in this problem here, the distance, okay, is simply defined as, right, the amount of ground covered by a moving object. Okay, so let's see. Let's start, but the object starts right here, right? And it looks like it starts right at a displacement of 9. Okay, then it's going to travel this way. And it looks like it travels to this location here, right, which has a displacement of 3, until it turns back around and finally stops at what appears to be a displacement of 5 here. Okay, so if we had to calculate the distance, we have to calculate the total amount of ground covered. Okay, including, it's not just a start and end point. We have to consider if we turn back around, we have to add that to the total distance. So I can break this up into two pieces, essentially. I'll break this problem up into part 1 will be from the start point to the turnaround point. I'll label that as part A. And then part B will be from the turnaround point to the end, which that'll be, I'll put a little dot there, part B. Okay? So the distance, I'll just abbreviate as D, would be the distance traveled in part A plus the distance traveled in part B. Okay, so what's the distance traveled in part A? Well, they started at 9 and they went to 3, so if I take the difference, I'll find the total distance. And then what's the distance in part B? Well, part B essentially started at 3 and ended at 5, so if I simply take the difference, I'll find the distance. Now, I put the larger value first for both because I'm not interested in the sign. I want the positive value, I want the absolute value. Because that's what we need to do in order to calculate distance, the total ground covered. So 9 minus 3 is simply 6. This is all in meters, right? 5 minus 3 is 2. So the total distance covered here for path D is going to be 8 meters. Great, letter A is done. Let's move on to letter B. Okay, so now let's just erase the little notes there on the picture, and let's go back to the picture. So remember, the part B wants to calculate the magnitude of the displacement from start to finish. So recall the formula, that the change in displacement is equal to the final displacement value minus the initial displacement value. Since we're just concerned about the magnitude, we can take the absolute value of this, because we don't care about the sign. So we're starting at 9 and we're ending at 5. So let's plug in those numbers. So the final displacement value is 5 meters. The initial was 9 meters. And I'm going to take the absolute value. Right? So when I do the math here, 5 minus 9 is negative 4. And when I take the absolute value, the negative just becomes a positive. So it becomes 4 meters. Great, so that's part B. And now we can do part C, right? Part C is now asking to find the displacement. So they want to consider sign. So now we have the same formula, though we just get rid of the absolute value because we are concerned about the sign now. So we just plug in the same numbers. The final displacement value was 5 meters. The initial was 9 meters. So when I take the difference, it comes out to be, I forgot the x there. The difference comes out to be negative 4 meters. And that would be the answer to part C. Number 5, letter A. Calculate Earth's average speed relative to the sun. Okay, so what we need to do here, let's first draw a picture. All right, so let's draw a nice little circle for the orbit. Actually looks a little elliptical, which is actually what the orbit really is. I didn't intend to do that, but it kind of worked out. But we will assume it is a perfect circle for our calculations. So the sun here is right in the middle. Okay, here's the sun. And the Earth we'll put as a little dot over here. So what we need to know, and I'll label that Earth. And what we need to know is we need to know the distance. In order to solve this problem, we need to know the distance between the sun and the Earth. Okay, so I'll give you an approximate value. It's approximately 1.5 times 10 to the 8 kilometers away. Okay, great. So now what we need to find is we need to find the Earth's average speed. Okay, so let's write down a formula for average speed. So speed, an average speed that is equal to distance traveled divided by time. Okay, so that should be fairly straightforward. So in order to find the average speed, we need to know the distance that the object traveled and the time in which it took to travel that distance. So let's think about the orbit of Earth, right? So Earth is traveling around the sun in this fashion, right? It goes around the sun. So how can we calculate that distance? Well, remember, it's a circular orbit. We're assuming so. And how do you calculate the distance around the edge of a circle? Oh, I think I heard you. Circumference, right? Yep, that's it. So circumference, okay? So we need to know the circumference of this particular circle, or the orbit, right? So let's write down the circumference formula on the left side. So circumference is equal to 2 pi r. Okay, great. So let's calculate that. So 2 pi multiplied by the radius, and the radius was given to us as 1.5 times 10 to the 8 kilometers. Great. So let's plug that into the calculator. So 2 times pi times 1.5 times 10 to the 8th. Okay, great. So this works out to be approximately, so it looks like 9, and I'm going to round to 2 sig figs, 9.4 times 10 raised to the, let's see, 3, 6, 8. So that should make sense. Great. That's the circumference in kilometers. And remember, the circumference is the same thing as the distance traveled. So I do know the numerator. Now, how long does it take? Well, how long does it take for the Earth to make its trip around the sun? Well, it takes a year, right? So we know a year to be, right, 365 days. Technically, it's 365 and a quarter, but we're just going to keep it simple here. So now what I can do is I'm going to actually plug in, I'll work down. So let's now, the distance traveled, I'm going to plug 9.4 times 10 to the 8 kilometers. And I'm going to divide that by 1 year. Okay, great. Now it doesn't ask us what units they want it in, right? They just said calculate the average speed. So this could be a speed, right? This works. If you had to find kilometers per second, right, we could do that. We would just have to convert the years into seconds. Why don't we do that quickly? All right. So my job here is to, I want to try to convert this value into kilometers per second, let's call it. So I think about it in, 3 steps. I look at the numerator values. They're the same, so I don't have to do any conversions. Then I look at the denominator values, and I realize that they're different, so I will have to do a conversion there. And then what I do is I will just take these two and then divide them. Okay, my kilometer value by my second value. That'll be my step 2. So the first step here, right, will be to go from 1 year into seconds. So 1 year, years go on the bottom. I'm going to put days on the top because I do know how many days there are in a year, right? We said it before, 365. So the years will cancel. Great. Now I need to get rid of days, so they go on the bottom. And I do know the relationship between days and hours, right? 24 hours in a day. So days go bye-bye. Now hours in the denominator, and I can now go to minutes because I know that there are 60 minutes in an hour. So that goes away. And finally, last but not least, I'll get down to seconds now. So minutes go on the bottom so that the units cancel. Seconds on the top, 60 seconds in a minute. Bada bing, bada boom. And now let's do the math. So it's 1 times 365 times 24 times 60 times 60. And the value comes out to be about 3.2, let's call it. Now, I know I only began with one significant figure here. Really, I should have, you know what, I'll keep it technically correct. It's just going to be 3, right? 3 times 10 to the, looks like 7th. Yep, 3 times 10 to the 7th seconds. Great. So this is my second value. And now in step 2, what I'm going to do is now I'm going to take my kilometer value, okay, that we had before, so 9.4 times 10 to the 8 kilometers divided by 3 times 10 to the 7, 10 to the 7 seconds. So let's plug that in. So 9.4 times 10 to the 8th divided by 3 times 10 to the 7th. And that comes out to be about 30, 31. We're going to round to 2 sig figs, so about 30. So 30 kilometers per second. That's moving pretty quickly. All right, so that'll be the answer to part A. So now, moving on to part B, it now says what is its average velocity over a period of 1 year. So let's remember the velocity formula. I'm going to write it down here on the lower left. Okay, so the average velocity is going to be the change in displacement over the change in time. So let's really focus in on this numerator value, change in displacement. Now remember, that value can be broken down into the final displacement of the object minus the initial displacement. So let's go back to the picture up at the top here. Okay, where's Earth starting? Well, I chose it to start right here. So that's where it's starting its orbit. So we can call this displacement x. Really doesn't matter. Okay. Now, after it goes around a full revolution, it comes back to the same spot. So it came back to displacement x. So it started at displacement x. It ended at displacement x. What's x minus x? Zippo, right? So this whole thing, the whole numerator here goes to 0, right? So what that means now is that if I think about it mathematically, it'd be 0 divided by whatever time I have. This thing should be 0. So this is the average velocity. Generally, it's given in meters per second, but I can write kilometers per second. It really doesn't matter because it's 0. Number 6. A helicopter blade spins at exactly 100 revolutions per minute. Its tip is 5 meters from the center of rotation. A. Calculate the average speed of the blade tip in a helicopter's frame of reference. Okay, so let's draw a picture. So it seems like there's this blade going around in a circle. Right, we'll put the center right here. And the blade would be, this is a modern day Picasso. The blade's tip would be somewhere out here, right here. And it says that the tip of the blade is 5.00 meters, 5.00 meters from the center of rotation. The problem also tells us that this blade will make 100 revolutions per minute. Okay, and our job is now to calculate the average speed of the blade. All right, so let's recall our speed formula. So let's write it down here in part A. Right, so speed is equal to the change in distance divided by the change in time, not the change in displacement. Distance and displacement are two different things. So, how can we now solve this? There's a couple of ways to do it. Let's do it this way. Let's just look at one revolution. Okay? So when this blade goes around the circle, okay, it's traveling a certain distance, right? The tip is. So how do we find the distance that this tip is moving if it's moving in a circle? Well, you're thinking about it and you're tracing it and it's going around like this, right? Around the circle just like this. And it keeps going around a full revolution. So what is that called in terms of a circle? How do you measure the edge of a circle? It's known as the circumference, right? So let's write down our circumference formula. So really, what in this problem, the distance that the tip of the blade is traveling is the circumference. They're the same. So the circumference is equal to 2 pi multiplied by the radius. In this problem, it is 5.00 meters. I'll leave the unit out. It doesn't matter. Just know that the circumference will be in meters. So now, take out the calculator. 2 times pi times 5.00 comes out to be a value of 31.4. 31.4. And that is in meters. Okay, great. So now I have 3 significant figures here. Why? Because this value had 3. And that's the measured value. You might say, well, wait a minute, 2 has only 1 sig fig. That's not a measured value. It's 2 because it's half of the diameter. meaning the radius is half of the diameter, so we have to multiply it by 2. But we only concerned about significant figures for measured quantities. Okay, so we know the circumference. That's the distance that, let me change the color, make it a little more colorful. That's the distance that the tip of the fan blade is traveling. Now that's the distance it travels in one revolution. So what I can do now, if I know that that's the distance that it takes, right, to travel one revolution, and we also know that it did 100 revolutions per minute, that means if I were to take 31.4 meters, right, and multiply it by 10, multiply it by 100, just seeing if you guys were paying attention. And if I multiply it now by 100, what I will find now would be the total revolutions per minute, right? So that should make intuitive sense. So we have 3140. So 3,140. It'll be meters per minute. Okay, great. And how do the units work here? Well, remember that it's 31.4 meters per one revolution. And then I multiplied it by 100 revolutions per minute, right? So technically the R's canceled, leaving me with meters per minute. Okay, so I have my value right here. So this is actually the speed. Okay, notice how I have a distance divided by time. So this is actually the speed. I didn't even have to go back and plug it in. If I did, let's say I plugged in the 31.4, watch. If I plugged in the 31.4 meters in for the distance, then I would have had to have found out how long, right, does it take the tip of the fan blade to go around just one time, right? Well, if in 1 minute it went around 100 times, right, then that means that in order to find the time for one revolution, I would then have to flip the fraction. So let me actually just do that on the top here. If I were to look at it this way, 1 minute per 100 revolutions, and I divided the two, right, it would be 1 over 100, which would work out to a value of 0.01 minutes per revolution. This now told me the minutes per revolution. So since I have the distance of one revolution, and now I have the time of one revolution, I can plug that in here. So 0.01, right? And that would be minutes per revolution, or I could just write minutes. The reason why I can get rid of revolution is because it would be minutes per revolution. This would be meters per revolution, and the R's would cancel. But let's just leave it simple. Okay, when you do the math now, right, what happens? Well, it actually works out to be the same number. Plug it into the calculator. This would be meters per minute. So it doesn't matter how you solved it. Okay, we would have gotten the same answer. And we should have 3 significant figures here. All right, I think that's, that makes sense. Okay, part B. So now it says part B. What is the average velocity over one revolution? So remember now that velocity is slightly different. It's the change in displacement divided by the change in time. So let's consider where we're starting in our picture. So let's say the fan blade is starting right here. Okay, let's call that, I don't know, displacement X. And it makes its trip around, right, the circle all the way on back, and one revolution it stops. Where does it stop? It stops back at X. So the initial displacement was X, and the final displacement was X. So what happens when we plug both of them in for the change in displacement here in the formula? Remember, the change in displacement is the final minus the initial. So if they're both X minus X, that works out to be 0. They cancel. And if this whole term is 0, the whole fraction goes to 0. And therefore, the average velocity is 0. Put whatever units you like, meters per second, kilometers per hour, doesn't matter. Okay? It's 0. That would be the average velocity. Number 7. The North American and European continents are moving apart at a rate of about 3 centimeters per year. At this rate, how long will it take them to drift 500 kilometers further apart than they are at present? Okay, so let's identify what we're given. They gave us a rate here, right? So that could be either a speed or a velocity. They're drifting apart. It doesn't say that things are moving back and forth and they're just moving apart. So we can, call it either one. It really won't make a difference. Let's just call that a speed for now. Okay. So they gave us a speed. And they want us to find out, right? How long will it take? So they're asking for a time value, right? So they want us to find time. How long will it take for them to drift apart, or 500 kilometers apart, right? So this is now a distance, okay? And I'm going to call it a distance because I define the rate as a speed, right? If I called the rate a velocity, then I just would have called this a displacement. In this problem, it doesn't really matter. So notice what you're given and think about, do you know a mathematical relationship between these three items? And I think we do, right? So if we write down speed is equal to distance divided by time, right? In order for me to find time, I better know the speed and the distance. And we do, right? So we can essentially just plug them in and do a quick calculation. All right, so let's see what happens. So let's plug in 3 centimeters per year for the speed. And then the distance they gave us was 500 kilometers divided by time, which I'm trying to find. Now here's the problem. So don't do the calculation right now because the distance value they gave you in the speed is in centimeters and the distance value that they gave you for the actual distance in which they're drifting apart is in kilometers. No good. Okay, these units have to be consistent. So it doesn't matter to me whether they both are in centimeters or they both are in kilometers. We're going to get the same answer. Okay, they just have to be consistent. So always make sure that they are the same. And if they're not, we have to do a conversion. So I think the easiest conversion here would be to take the kilometer value, the 500 kilometers, convert that into centimeters. So let's do that on the right. So 500 kilometers, kilometers on the bottom, meters on the top. There's 1,000 meters in 1 kilometer. Kilometers cancel. Right, so this would essentially be 500 and then add 3 more zeros. So it becomes 500,000. And that would be in meters. Okay, now if I know the meters, I have to still convert it to centimeters, right? So now just take this answer. Okay, I'll rewrite it over here, 500,000 meters. Meters on the bottom now. Centimeter on the top, because I want the meters to cancel. And I know that there are 100 centimeters in 1 meter. So now simply just add 2 more zeros to your number. We already had 5 and 2 more. Right, so that'll give us now a value of 50 million. Okay, 50 million centimeters. Now this is the number that we need to be plugging into the numerator here. So let's rewrite everything. I'm going to not write the units in now just so it looks a little cleaner and it doesn't get too cluttered. Okay, just remember though that your time value here is in years. Therefore, the t value that you're going to calculate will also be in years, which is fine because they didn't ask us for a particular time value. They just said how long. They didn't say how long in seconds, how long in years, how long in minutes. All right. So let's plug in that 50 million value. Great. Divided by then t. Okay, so t, just doing a little cross multiplication, right? T will be equal to 50 million over 3. And then just take out your calculator, plug that on in. So 50 million divided by 3. So that works out to be about 1.7. I'll round to 2 sig figs. Actually, when I look back, let's just do 1 sig fig. Because that's how many there are, right? If you go back to what's given in the problem, the 3 has 1 significant figure, and the 500 also has 1 significant figure because there's no decimal. So this works out to be 2 times 10 raised to the 7th. And that is in years. So it's going to take almost 20 million years for these tectonic plates to move apart that amount, 500 kilometers. Number 8. Land west of the San Andreas Fault in Southern California is moving at an average velocity of about 6 centimeters per year northwest relative to land east of the fault. All right, so before we move on, let's just draw a quick picture. So here is the San Andreas Fault. And it says that land mass that is located to the west of the fault. So I'll draw this little box here. Remember your coordinates, north, south, east, and west. This particular landmass is moving at an average velocity of 6 centimeters per year northwest. So it's moving in this direction. So that is 6 centimeters per year. Yeah, right. Relative to the east, relative to the land east of the fault. Okay. Next sentence. Los Angeles is west of the fault. Okay, so let's consider this LA. And may thus someday be at the same latitude as San Francisco, which is east of the fault. Now, knowing San Francisco lies also to the north, you need to know a little bit about U.S. geography here. But San Francisco lies also north of Los Angeles. So it's saying that eventually, someday, this landmass of Los Angeles will eventually be at the same latitude, right? Remember, latitude's horizontal. It'll be at the same latitude as San Francisco. So now it says, okay, how far in the future will this occur if the displacement to be made is 590 kilometers northwest? So, in order to get to this latitude, it tells us that the landmass here, the Los Angeles landmass, must travel 590 kilometers. Okay. So, and they want to know how long it's going to take. So, I'm looking for time, right? They gave me a velocity, average velocity. They told me that it was 6 centimeters per year. And then they also told me the displacement value, that it was 590 kilometers. Now think about a relationship between these three variables. Do you know one? Mathematical relationship, that is. Not a romantic one, but a mathematical one. We do, right? So the velocity, average velocity, is equal to the change in displacement divided by time. Okay, great. So it seems like we have everything we need. Let's plug it in. So we have 6 centimeters per year for the velocity. The displacement, right, or the change in displacement, they told us was 590 kilometers. And then divide that by the time value. And as long as I know two of the variables, I can always solve for the third one. Okay, so it sounds great. So now we're just going to calculate and solve. But wait a minute. We can't yet do that, right? Because the displacement units here in the problem are not consistent. They better be consistent, otherwise your calculation will be wrong. Now, I don't care if you convert this value into kilometers or you convert this value into centimeters. As long as they're both the same, that's the important part. That's the important point. So I think it might be easiest to convert this value into centimeters. So I'm going to do that on the lower left-hand corner. So 590 kilometers. I put kilometers on the bottom, meters on the top, because I know that there are 1,000 meters in 1 kilometer. That gets rid of the units of kilometers. Then meter goes on the bottom so I can cancel it. And now I do know the relationship between meters and centimeters, which is 100 centimeters in 1 meter. So the meters cancel. So now take out the calculator and plug it all in. Right, so we get 590 multiplied by 1,000 multiplied by 100. And the answer comes out to be 5.9 times 10 raised to the, let's see, 7th, it appears, times 10 to the 7th. And that is centimeters. Okay, great. So I have 2 sig figs here because I started with 2 sig figs. There's no decimal, so the trailing 0 does not count. Okay, so now let's take this value and plug it back into my equation for the displacement. So let's rewrite everything. So we have 6 centimeters per year will equal 5.9 times 10 to the 7th centimeters over time. So now everything's consistent, I can solve. Now just remember, when you solve for time here, the time will be in years, because that's the unit of time in the velocity. Okay, so I'm just going to get rid of the units now. Just keep that in mind. I'm going to get rid of the units just so I can clean it up a little bit, so it's a little easier to follow. All I'm going to do here is just now switch these two variables, bring the time up to the numerator on the left-hand side, and bring the 6 down to the denominator on the right-hand side. So now it's 5.9 times 10 to the minus 7. Not minus 7, sorry, just 7. And then we can now simply calculate, right? So take 5.9 blah, 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 divide it by 6. Okay. So we get a value of approximately 9.8, right, times 10. Let's see what it's raised to. Looks like it's going to be raised to the 6. Okay. And remember, that's in years. So that's about 9.8 million years, or almost about 10 million years. Now remember, this isn't really the answer because I didn't take into account significant figures right now. Look back at the calculation, right? I had 2 sig figs here in the numerator, 1 sig fig in the denominator. Therefore, my answer should have no more than 1 significant figure. So I would have to round this answer. The 8 would round the 9 up to a 10. So it'd be 10 times 10 to the 6th. Or in other words, it would be 1 times 10 to the 7th years. And that would then be the final answer. Number 9. On May 26, 1934, a streamlined stainless steel diesel train called the Zephyr set the world's nonstop long-distance speed record for trains. Its run from Denver to Chicago took 13 hours, 4 minutes, and 58 seconds, and was witnessed by more than 1 million people along the route. The total distance traveled was 1,633.8 kilometers. What was the average speed in kilometers per hour and meters per second? All right, so just a quick sketch here. Let's say this is Denver here, and then I'll draw a line on over to Chicago. Okay, and it says that the distance between these two, or the total distance that the train traveled, is going to be 1,633.8 kilometers. Great. And it said that in order to travel this distance, right, the time that elapsed over this distance was 13 hours, 4 minutes, and 58 seconds. Okay, now what we want to do is, it says find the average speed in kilometers per hour. So I'll label that part A of the problem. Okay, so part A, we need to find the average speed in kilometers per hour. So remember, speed is equal to distance divided by time. And the units here, I must have kilometers in the numerator and then hours in the denominator. So this looks fairly straightforward at the start, right? The distance that they gave us is already in kilometers, so I can simply just plug that into the formula. And then the time is a little more challenging. What we need to do here is we need to then find the value of this time in hours solely. So basically what I need to do is convert the 4 minutes into hours and also convert the 58 seconds into hours. Then what I can do is take my 13 hours and add both of these values to find then the total hours. Okay? So let's take a look at this conversion first. 4 minutes into hours. I'll do that down here on the bottom left. So 4 minutes. Put minutes on the bottom, hours on the top, and there's 60 minutes in 1 hour, so the minutes will cancel, and that will tell you the number of hours. So 4 divided by 60 works out to be, in terms of a decimal, works out to be 6.67 times 10 to the negative 2 hours. And since there's only one significant figure here in my calculation, that's the limiting significant figure. I have to round this to 1 sig fig, so it would be 7 times 10 to the minus 2 hours. Okay, great. Now let's do the second conversion. Let's convert the 58 seconds to hours. So I start with my 58 seconds. Seconds on the bottom, minutes on the top, because I do know the relationship. There's 60 seconds in 1 minute, so the seconds cancel. Then the minutes go on the bottom. And now I'm going to put hours on the top because I know that for every 1 hour there's 60 minutes. Okay, great. So the minutes cancel. So now I need to take 58 and divide it by 60 times 60. And when I do that, the value comes out to be 1.61 times 10 raised to the -2, it looks like. And that's in hours, but again, well, actually, in this particular case, I had two significant figures here. So we're going to round this value to 2 sig figs. Okay. And so it should come out to be 1.6 times 10 to the -2 hours. Okay. All right. So actually, just thinking back to the prior calculation here, even though the value is 4 minutes, I actually want to change the answer slightly here. The clock measured down to the seconds value, right? So although this is 4 minutes, we can assume that this is essentially, right, 4.00 minutes, or at least 4.0 minutes. So I probably should have left two significant figures, which would have been 6.7 times 10 to the -2. But in terms of the calculations, it's not really going to make a big difference. Whichever one you were to use, 6.7 or 7 times 10 to the -2, the answer should come out to be so close that you would get credit either way. So let's not get too bogged down with those minor details. It's weird. In the beginning of this class, they're all concerned about significant figures. Once you get to the end of the class, start doing, centripetal acceleration and torques, nobody cares anymore. So I'm going to stop caring. No, I'm kidding. But we don't have to worry about it too much, probably in the next couple of chapters. Anyway, now what I can do is I can take my 13 hours, add that to this hour value, and then this hour value to find the total. So when I add 13 hours plus 7 times 10 to the -2 hours plus 1.6 times 10 to the -2 hours, we get then, and I'm going to put the equal sign over there, so 13 plus 7 to the -2 plus 1.6 to the -2. So we get an answer of so close to 13. Right, so it's really 13 point, let's just call it 1 hours. Okay, great. So that's the hour value. So now what we're going to do is we're going to take this and plug it in now for the time. And now this would give me the value of the speed in kilometers per hour. So the numerator is 1,633.8 kilometers. The denominator will be 13.1 hours. And now the speed is going to be, let's take 1,633.8, divide that by 13.1, and we're going to get a value, we'll just round to 3 sig figs, we're going to get a value of approximately 125 kilometers per hour. Okay, great, so that would be the speed in kilometers per hour. And now they just want to know the value of that answer in meters per second here. So basically what we now need to do, we can take the kilometer per hour value here and convert that into meters per second. So I think about this in a 3-step process. Remember, this is 125 kilometers per 1 hour. So convert kilometers to meters, step 1. Step 2 will be to convert hours into seconds, 1 hour into seconds, that is. And then after you get those two results of meter and seconds, just divide the meters by the seconds, and that will be step 3. So being that I'm running out of a little space here, I'm going to go to the upper left-hand corner, and I'm going to do the first conversion. So first conversion was 125 kilometers. Convert that into meters, right? So write down what we're given. Kilometers on the bottom, meters on the top. 1,000 meters in 1 kilometer. Kilometers cancel. And now it's going to be 125,000 meters. Okay, great. So that's that value. Step number 2 now will be to convert 1 year into seconds. So this one's a little longer. So let's write down what we're given 1 year. And the years on the bottom. I do know the relationship between days and years, so that's going to go on the top. So we have 365 days in 1 year. Years cancel. Then write days on the bottom so that the units will cancel. And now I know how many hours there are in a day. So that's my next step. 24 hours in 1 day. So days go bye-bye. Next, hours on the bottom. and I know the relationship between hours and minutes, namely 60 minutes and 1 hour. So hours are done. Last but not least, I'm trailing off to the bottom here a little bit, but I think you get the idea. Minutes and then seconds. There's 60 seconds in a minute. Let me just make that a 6. Minutes cancel. So now just do the multiplication. So multiply everything on top, divide everything by the bottom. Obviously, the denominators are all 1, so you don't even have to bother with that step. But we have 365 times 24 times 60 times 60. And that comes out to about let's do 3.2 times 10 to the, we got 3, 6, 7. 10 to the 7 seconds. So that's the seconds value. Now, step 3, over to the right of the problem, I'm going to do, take the value you found in the first step, the 125,000 meters, and divide it now by the seconds value of 3.2 times 10 to the 7 seconds. And when you do this division now, you're going to get your answer in meters per second. Why? Because those are the units there, right? So 125,000 divided by 3.2 times 10 to the 7th. And we get an answer of approximately 3.9 times 10 raised to the negative 3 meters per second. And that is the final answer. Number 10. Tidal friction is slowing the rotation of the Earth. As a result, the orbit of the Moon is increasing in radius at a rate of approximately 4 centimeters per year. Assuming this to be a constant rate, how many years will pass before the radius of the Moon's orbit increases to 3.84 times 10 to the 6 meters? Okay, so let's just sketch a simple picture here. So let's say this dot represents the Earth, and then the Moon's orbit around the Earth would look something like this in terms of a circle. And the Moon, let's say, is out here now, M for Moon. And the radius between the Earth and the Moon, it says it's increasing, so it's moving outwards by approximately 4 centimeters per year. Okay, and now it says, assuming this to be a constant rate, how many years, so we're looking for time, how many years will pass before the radius of the Moon's orbit increases by 3.84 times 10 to the 6th meters. So it sounds like this value here is a distance or a displacement value, right? And it doesn't matter in this problem which you choose because they're both going to be the same, distance and displacement. So I'm just going to call it a displacement. So my displacement value in the problem is 3.84 times 10 to the 6 meters. Okay, great. So, and remember, they also gave us the rate at which it's increasing. So they told us the velocity, and they said it's 4 centimeters per year. So now step back and consider, do you know a relationship between these mathematical variables? Right, and we do, right? The volume is equal to, not the volume, the velocity is equal to the change in displacement divided by the change in time. Okay, so what was the velocity? Well, they told us 4 centimeters per year. And the change in displacement, they said, is going to be 3.84 times 10 to the 6 meters. And time is what I'm looking for, right? So it looks like I have everything I need. I know this variable, therefore I can calculate the time. But one quick second, you always have to check and make sure the units are consistent. So the displacement value in the velocity is centimeters, and meanwhile the displacement value is meters on the right-hand side. No good, they have to be consistent. So either you convert the centimeters in the velocity to meters, or you convert the meters of the displacement into centimeters. Doesn't matter, either way will work. I think it's easiest to just convert this value into centimeters. So let's do that here on the left-hand side. So we have 3.84 times 10 to the 6th meters, and I'm looking to convert that into centimeters so that I have consistent units. So let's write down what we're given. Meters go on the bottom, centimeters on the top. Meters on the bottom because I need the units to cancel. Now I have to think of a relationship between those two variables, and there are 100 centimeters in 1 meter. So we just have to simply multiply. So it'd be 3.84 times 10 to the 8 now centimeters. Great. So now this is the value I can plug back into my equation here. So let's continue. Now I'll have 4 centimeters per year is equal to 3.84 times 10 to the 8 centimeters over t. Now I can solve for t. Just remember when you do so, since your time value on the left-hand side is years, the time value that you will solve will be in years as well. So just don't forget that. Because what I'm going to do now is I'm just going to get rid of the units to make the calculation look easier, just to simplify it a little bit. We don't need the noise of the units. Over t. So now just switch the t and the 4. It's basically like a cross multiplication idea, kind of. So t is equal to 3.84 times 10 to the 8 divided by 4. So the t value will work out to be, take out the handy dandy calculator, divide that by 4, and we get a value of 9.6 times 10 raised to the count your decimal places. So 3, 6, 7. So it comes out to 7. And remember, that's in years. Now, considering significant figures, I should probably have no more than one significant figure, a y, because the velocity in which they gave to me only had one significant figure in it. So my answer should have no more than 1. So really a better answer here would be 1 times 10 to the 8 years, because the 6 would round the 9 up to 10, and just move the decimal place, so that's why now it's 10 raised to the 8 instead of 10 raised to the 7. So this would be a better answer. Number 11. A student drove to the university from her home and noted that the odometer reading of her car increased by 12.0 kilometers. The trip took 18 minutes. Letter A. What was her average speed? Okay, so let's write down what we're given. So it said that the odometer reading, right, increased by 12 kilometers. So that means the distance that she traveled during her trip was 12.0 kilometers. And it told us that the time in which it took her to drive these 12 kilometers was 18.0 minutes. So now it asks us, what was her average speed? So we're looking for S. Now it doesn't ask for speed in kilometers per second or kilometers per minute or meters per second or whatever. So I'm probably just going to leave the units how they are to make it simple. But what we now need to think about is, do we know a mathematical relationship between these variables? And we do, right? We see that the speed of an object is equal to the distance that it travels divided by the time it takes to travel that distance. So speed here will equal 12.0 kilometers divided by 18.0 minutes. And when I do this math, right, plug it into the calculator, 12 divided by 18, that works out to be 0.667 kilometers per minute, because those were the units of speed that I used. And I have 3 significant figures here, and that matches the 3 significant figures of the measured values that were given to us. So this would be the speed for part A. Okay, let's move now on to part B. So it says, if the straight line distance from her home to the university is 10.3 kilometers, in a direction of 25.0 degrees south of east, what was her average velocity? Okay, so this gets a little confusing, I think. First thing is, why don't we just draw a quick picture of maybe what they're talking about? All right, so what I'm going to do is I'm going to draw, actually let's label this part B over here. I'm going to draw a coordinate system very quickly. Let's say we have something like this. And it says that she is traveling at 25 degrees south of east. So here's the east direction. Here's the south direction. So she's traveling, well, that looks like 45, right? We got to do about 25. It's probably still a little too much, but I think we get the idea. So she's traveling 25 degrees south of east, right? So this angle right here is 25 degrees. Okay. And it says that the straight line distance from her home, so we'll say that this little dot represents her cozy little home. And I'll say the point out here represents the cozy little university. All right, and it says that this distance that she traveled, the straight line distance, is 10.3 kilometers. Okay, great. So apparently, though, when she traveled to university, it wasn't a straight line path, because before the part A told us that it took 12 kilometers. So let's just assume, right, we can make this hopefully make a little more sense. Maybe she drove something like this. Maybe she drove east and then had to go south. Right, and if she did something like that, then obviously it would be longer than 10.3 kilometers. Okay, just to kind of make sense of what's going on in the problem. All right, so now it says, all right, great. So we got everything set up, and now it wants to know the average velocity. So let's see what we're given. Okay, so let me draw. So they told us the straight line distance, which is essentially the displacement. Why? Because it is the difference between the starting point and the ending point. Okay? The exact shortest distance between the start point and the end point, that is the displacement. Remember, the distance is the total ground covered. So sometimes distance and displacement will be the same thing, but usually it won't be. I mean, well, not usually, but sometimes it won't be. All right? So generally speaking, displacement, if it's not the same as the distance, should be less than the distance. Okay? All right, so that's a little trick to help you determine which is displacement and which might be distance. So this value right here is the displacement I'm going to call x. Okay, so they gave us an x value, right? They did also tell us the time that we have to use from it's the same time in part A, right? So it's 18 minutes, 0.0 minutes. And they're asking us to solve for the average velocity, which is the question mark. So I have to ask myself, do I know a mathematical relationship between displacement, time, and velocity? And we do, right? That would be velocity, average velocity, is equal to the change in displacement divided by the change in time. Okay, wonderful. So in order to calculate velocity, I need to know displacement, I need to know time. And we know both. So let's just plug them in. So it'd be 10.3 kilometers divided by 18.0 minutes. Okay, wonderful. Now it doesn't ask us specifically what units they want it in, so I'm just going to leave it in kilometers per minute. So just take 10.3 divided by 18, and we come to a value of 0.572. And remember, 3 significant figures here, because the values here are all 3. Okay, and this is in kilometers per minute. So that would be the average velocity. Okay. Letter C. If she returned home by the same path 7 hours and 30 minutes after she left, what were her average speed and velocity for the entire trip? Okay, so let's break this down. So in order to find, so here's part C on the left-hand side. So the average speed, remember, is equal to the distance divided by the time. Now, more specifically, it's equal to the total distance traveled divided by the total time that has elapsed in which the object was moving that distance. So in order to find then the total distance, right, remember the frame of this problem now is she's starting at home, she drives to school, and then she drives back. Okay, so she's starting at home and ends at home. So let's write that. Start at home and end at home. So if the problem starts at home and then she returns back to home, what would be the total distance she traveled? Well, if it took, as it says in the problem, 12.0 kilometers to get to school, then it must also take, right, 12.0 kilometers to get home. So the total distance that she would have traveled would be 12 plus 12, aka 24. So let's write that down. So we got 24.0, right? 0.0 kilometers was the total distance. Now what is the total time? Well, the total time, read C carefully. It says, if she returned home by the same path 7 hours and 30 minutes after she left. Okay, so that means that it must have taken, right, this from the time she left home to the time she returned back home, 7 hours and 30 minutes has elapsed. So that's essentially the total time that has elapsed. So let's write that in the denominator. So we got 7 hours and plus, right, 30 minutes. Now the problem here is that I can't have two different time units. So do one of the two things: either convert one unit to either convert the minutes to hours or convert the hours to minutes. I think because everything was in terms of kilometers per minute, I'm going to convert the 7 hours into minutes. Okay, so I'm going to do that. On the upper left-hand piece of the paper. So we have 7 hours. I'm going to convert that into minutes. So write down what you're given: 7 hours. Hours on the bottom, so they cancel. And I do know the relationship between hours and minutes. 60, well, not 61 minutes, 60 minutes in an hour. So now just take 7, multiply it by 60, and we should come up with the value of 420 minutes. Right? Okay, great. So now what I would do is then, that's the 7-hour value. Now if I want to find the total, right, time, just take those minutes and add 30 to them. And then your total time now will be 450 minutes. So this is really representative of the total time. Okay? So now let me write my average speed formula over again. So average speed is equal to 24.0 kilometers divided by 450 minutes. Okay, so when we do the math, take out the calculator. 24 divided by 450 comes out to a value of 5.3 times 10 to the minus 2 kilometers per minute. Okay, great. So that is her average speed. All right. I used 2 sig figs because since we converted them to minutes, we had 2 sig figs in that value. Okay, so now the second part of part C was what's her average velocity now, right? So let me put that in there. So in order to find average velocity, we need to know the total displacement divided by the total time. Okay, now focus on the total displacement. Remember that is simply the displacement of the final displacement of the object minus the initial displacement of the object. So tell me, where's the end of the problem? Well, we said that we start at home and end at home. So the end of the problem is the displacement value at home. Okay, you might say, well, I don't know what's the number. Don't worry about it for now. Just call it h. What's the initial displacement? Well, where is she at the start of the problem? Well, again, we're starting at home, we're ending at home, so it's also h. So what's h minus h? 0, right? Anything minus itself is 0. So if we think about what happens when we plug 0 into the numerator here, well, the average velocity goes to 0, right? That's the average velocity, that's all. So this could be in kilometers per minute, could be in miles per hour, it doesn't really matter, but it's 0. Number 12. The speed of propagation of the action potential, an electrical signal, in a nerve cell depends inversely on the diameter of the axon, the nerve fiber. If the nerve cell connecting the spinal cord to your feet is 1.1 meters long, and the nerve impulse speed is 18 meters per second, how long does it take for the nerve signal to travel this distance? Okay, so let's just identify the variables that we're given. So we're given a length, right, of the spinal cord. That's basically similar to a distance, right? So that's 1.1 meters. They told us the speed at which the nerve impulse moves at, right? So that's 18 meters per second. And they're asking us for time. So do you know a mathematical relationship between these three variables? And we do, right? We know that the speed is equal to the distance an object travels divided by the time it takes for the object to travel that distance. So speed now will be the distance value of 1.1 meters divided by the time value of 18, we're solving for time, right? And we don't know this is what happens when you move too quickly. All right. We don't know the time, and we do know the speed, right? It's right here. So that is 18 meters per second. Okay, great. So I know 2 of the 3 variables. That means I can solve for the third. And I notice, thank goodness they gave me consistency within the units. Both of the distance values are in meters. So that being the case, I can simply solve, right? So this is going to be 18 is equal to 1.1 over t. I just get rid of the units to make the problem, easier. Don't worry about the units now. Just remember, if your time value here is in seconds in the velocity, the time value you calculate will also be in seconds. So now I'm just going to switch these 2 variables. So t is equal to 1.1 over 18. And now t is equal to, plug it into the calculator, 1.1 divided by 18. So that works out to be a value of approximately 6.1 times 10 to the minus 2 seconds. So pretty fast. All right, 2 sig figs because we had 2 sig figs in the given information. Number 13. Conversations with astronauts on the lunar surface were characterized by a kind of echo in which the earthbound person's voice was so loud in the astronaut's space helmet that it was picked up by the astronaut's microphone and transmitted back to Earth. It is reasonable to assume that the echo time equals the time necessary for the radio wave to travel from the Earth to the Moon and back. That is, neglecting any time delays in the electronic equipment. Calculate the distance from Earth to the Moon, given that the echo time was 2.56 seconds, and that radio waves travel at the speed of light, which is 3 times 10 to the 8 meters per second. Okay, so a quick picture here. So let's say this little dot represents the Earth. Okay, and this little dot over here will represent the Moon. Now it says that these radio waves, right, they were echoing, right? It was so loud that it was echoing, the person's voice was echoing in the astronaut's space helmet. Okay, and it's reasonable, it says, to assume that the echo time equals the time necessary for the radio wave to travel from the Earth to the Moon and back. So, the time it takes the radio wave to go from the Earth to the Moon and then back again, okay, was the total time here, so I'll call it T total, is going to equal 2.56 seconds. And that's, okay, great, so they gave us the time. They also told us the rate at which this radio wave is traveling. It travels at the speed of light, right? So it told us the speed. So the speed value of this radio wave is equal to 3.00 times 10 to the 8 meters per second. And now they want to calculate the distance from the Moon to the Earth. So what I want to know is I essentially want to know the distance between the Earth and the Moon. Right? So that value right there will represent the distance. Okay, so do we know a relationship between these 3 variables? Time, distance, and speed. And we do, right? We know that the speed of an object is equal to the distance the object travels divided by the time it takes for that object to travel that distance. So that's the key in this problem. The distance between the Earth and the Moon is, as noted in the picture, described by this gold line. But the time that they gave us describes the time it takes this radio wave to go from Earth to the Moon and back again. So, when you look at our formula, the distance that we're using in the formula must be consistent with the time that we're using. Okay, remember, it's distance an object travels divided by the time it takes for the object to travel that distance. So how long does it take the radio wave to travel from the Earth to the Moon? Well, if it takes 2.56 seconds for the radio wave to travel from Earth to the Moon and then from the Moon back to the Earth, wouldn't it stand to reason that half of that time would be just the time it takes to go from Earth to the Moon? Yeah, I think that's fairly reasonable. Right, so what we're going to do is we're going to take 2.56 seconds and divide it by 2. What that does, again, is that will get us the time it takes to just go from Earth to the Moon. So 1.28 seconds. So this is our time value that we're going to use, because the distance we're measuring is simply the distance from Earth to the moon, not from Earth to the moon and from the moon back. Okay, so now let's plug in everything we know. So the speed, they said it was the speed of light, so 3.00 times 10 to the 8 meters per second. That equals the distance, that's what we're trying to find, divided then by the time, which we calculate to be 1.28 seconds. So it looks like we can just calculate now because I have consistency with my units, meaning the time values of both my velocity, speed in this problem, but both the speed and the time are consistent. They're both in seconds. So just know that whatever you calculate d to be will be in meters because that's the distance value in the speed. Okay, so now, keeping that in mind, let's just get rid of the units to make the calculation simple. So 3.00 times 10 to the 8 equals d all over 1.28. Okay, so just simple cross multiplication here. So d will equal, so 3 times 10 to the 8 times 1.28. Oh, I did 1.25, sorry. So 3 times 10 to the 8 multiplied by 1.28. So we get 3.84 times 10 raised to the, let's count it out, 3, 6, looks like 8. Times 10 to the 8 meters. Okay, great. And I should have 3 significant figures in my answer because I have 3 significant figures in both of my measurements. So that's good. So that would be the total distance. Number 14. A football quarterback runs 15.0 meters straight down the playing field in 2.5 seconds. He is then hit and pushed 3 meters straight backward in 1.75 seconds. He breaks the tackle and runs straight forward another 21 meters in 5.2 seconds. So calculate his average velocity for A, each of the 3 intervals, and then B for the entire motion. Okay, so why don't we draw a picture first? All right. So here's the quarterback. Starts running, it says, straight down the field. Actually, let me make it a little longer. So starts running straight down the field. And it appears that he first travels in the first part 15.0 meters, and it takes him 2.50 seconds, right? So this looks like it's his displacement value, or I'll call it his distance, right? And then this is the time it took him. Okay, then in the second part, he's pushed 3 meters straight backwards now. Okay, so now we're starting at this particular point, and he's pushed straight backwards about 3 meters. Okay, so that's probably good about there. So it says 3 meters backwards, so 3 meters. And let me actually include the decimals, so the distance here is going to be 3.00 meters. And then the time it took to travel back this distance was 1.75 seconds. Then he breaks the tackle. And now he runs straight forward for another 21 meters. Okay, so now we're going to start from this point. Okay. And we're going to move forward now, right? So let's 21 meters. Okay, great. So now it says that the distance he travels here is going to be 21.0 meters, and the time it takes him to do this is going to be 5.20 seconds. Okay, so calculate the average velocity for each of these intervals. Okay, so let's do the interval in yellow. Okay, so I'll call that part 1. So velocity is equal to the displacement, right? The change in displacement divided by the change in time. So since the quarterback is moving to the right, I know that the displacement is positive. So I'll just make a note of that when I plug it in. Right, so he moved 15.0 meters to the right. So that's a positive value. Remember, to the right is always positive, and to the left is always negative. Okay, also up. And let me make it a little cleaner. Remember that I'll do it up here. Up is always positive, and down is always negative. Okay. So divided by then time, right? So the time it took him to go 15 meters was 2.50 seconds. Great. So now the average velocity will simply just be the division of this. So take 15 and divide it by 2.5, and it works out to be 6, right? And keeping in significant figures should be 3, so 6.00 meters per second. So that's the answer to part 1. Then part 2, now he gets pushed back, right? 3 meters, and took him 1.75 seconds to do that. So again, the average velocity is equal to the displacement divided by the time. Okay, so now in this problem, though, the object is moving to the left, right? So you can see it here. It's moving to the left. So what that means is that the displacement value will be negative here. So it's negative 3.00 meters divided by 1.75 seconds. So just take that and throw it into the calculator. So 3 divided by 1.75. And remember 3 significant figures here, so it looks like it comes out to 1.71 meters per second. Negative. Okay, great. And then last but not least, we'll look at the last part. So part number 3 here. Remember that again, velocity is equal to the displacement divided by the time. So now, to find the average velocity, the object is now moving to the right. So it's positive. So the 21.0 meters is a positive value. So we got 21.0 meters positive divided by the time, so 5.20 seconds. Okay, so the average velocity would be, plug that into the calculator, 21 divided by 5.2, so 4.04. So it looks like it comes out to 4.04 meters per second. 3 sig figs because that's what we're given. Okay, so that all would be for part A. Now let's take a look at part B. So now it wants to know the average velocity for the entire motion. Okay, so remember, in order to figure this out, let's just first start with the velocity formula. So I'm going to do part B over here. Okay, now remember, the velocity is equal to the change in displacement divided by the change in time. Now let's just break that down a little more. The change in displacement, right, is really the final displacement value minus the initial displacement value. Okay, all right, divided by time, right, or the change in time. So where's the start of this problem now? Because it wants to find the average velocity for the entire motion. So what's the start of the entire problem? Well, the start of the entire problem would be here. This is the start. Okay, and what's the displacement value at the start? Well, you didn't move anywhere, right? The quarterback didn't move anywhere. So the displacement initially should be 0. He didn't go anywhere. Okay, it's only after the clock started ticking. Also, the time value here would also be 0 because that's when the clock essentially started. Now think about, where is the end now of the entire motion? So the end should be here, right? This is now the end. And now what's the displacement at the end of this? Well, how do you think about it? It's really the difference between the starting point, so this value, and the ending point, right? So now if we think about it, how do we find that? Well, think about the motion. So first the quarterback traveled 15 meters this way. Then they got pushed backwards 3 meters. So if I had to just work with that for right now, I would say that it would be 15 minus 3, right? So that would have been 12 meters. Okay, and that's where I would have been at this particular point, at the end of the second part. And then it says from that point, from the second point, he moved another 21 meters forward. So this now moved 21 meters. So what would I have to do to find the point at the end here? Right, you would have to add 21 meters to the 12 meters. Right, so this works out to be 33 meters. Now I'm just going to put the point 0 because that would be using the proper significant figures. I didn't include them in the calculation because they're all 0. But this now represents the total displacement. This is now the total displacement, aka the change in displacement. Okay, so that's the value that goes into the numerator here, right? So we would have 33.0, that's a weird 3. So 33.0 meters, divided then by the total time. So how much time elapsed from the start of the problem to the end of the problem? Well, the total time that elapsed had to be the time from the first part, plus the time from the second part, plus the time from the third part, right? That should make sense. We would add all of them together. So I'll say that the total time here, I'll write it in the upper right-hand corner, the total time should be equal to the time of the first part plus the time of the second part plus the time of the third part. Okay, so therefore the total time would be equal to 2.50 plus 1.75 plus 5.20. Great. Plug that into the calculator now. So we get 2.5 plus 1.75 plus 5.2. So it comes out to 9.45. 9.45 seconds. Great. That's the total time, and now that's the value down there. Okay, beautiful. So let's plug that in. So now we have 9.45 seconds. And now finally I can calculate the average velocity over the entire problem. So 33 divided by 9.45 works out to be about 3.49. So 3.49 meters per second. And that would be the answer for part B. Number 15. The planetary model of the atom pictures electrons orbiting the atomic nucleus much as planets orbit the sun. In this model, you can view hydrogen, the simplest atom, as having a single electron in a circular orbit 1.06 times 10 to the minus 10 meters in diameter. If the average speed of the electron in this orbit is known to be 2.2 times 10 to the 6th meters per second, calculate the number of revolutions per second it makes about the nucleus. Okay, so, all right. So why don't we draw a simple picture? All right, so here's our nucleus, and we have an electron orbiting that particular nucleus. So here out here, I have my electron. So now it says that the diameter, right? Actually, you know what? Let me just move that a little bit over so it's a little more in the middle. That looks a little better. So now it says that the diameter, right, of this circular orbit is 1.06 times 10 to the minus 10 meters. All right, so let's draw that in. So we got a little, okay, we have a nice diameter here, and it said that the diameter, I'm going to say D, is equal to 1.06 times 10 to the negative 10 meters. Okay. Now it says if the average speed of the electron in this orbit is 2.2 times 10 to the 6 meters per second, so meaning it's moving at a speed, not a velocity, but a speed of 2.20 times 10 to the 6 meters per second, it wants to calculate then the number of revolutions, or the number of times per second it goes about the nucleus. So we can do this in a couple of ways. Let's first find the time it takes to make one revolution. So in order to do that, we're essentially trying to find how long it would take for the electron to make this particular path or travel this distance. Now you might want to ask yourself, what is this distance known as in terms of a circle? Well, that distance is known as the circumference, right? Capital C. So how do we calculate circumferences? Well, we know that the circumference formula is 2 pi r, right? Or pi d. Well, we can use either one, but it'd be a little easier to use pi d. Why? Because they gave us the diameter. So let's do that. So circumference is equal to pi multiplied by the diameter. and the diameter was 1.06 times 10 to the negative 10 meters. Okay, great. So let's plug that into the calculator. So we get 1.06 times 10 to the minus 10 multiplied by pi. So we'll do three significant figures here. So it works out to be 3.33 times 10 to the negative 10 meters. Okay, that's the circumference. In other words, this is the distance, right? I'm just going to now rewrite it as the distance. So the distance it travels to make one revolution, that is 3.33 times 10 to the negative 10 meters. Okay, so if that's the distance, and they told us the speed, right? If we go back, they told us the speed. Can we find the time it takes to travel that distance? Sure, right? We need to know a mathematical relationship between the three variables. And the mathematical relationship is that the speed of an object, the average speed, is equal to the distance traveled divided by the time, right? So the average speed they told us is that the electron is moving at 2.20 times 10 to the 6. So let's plug that in, 2.20 times 10 to the 6 meters per second. And that will equal the distance it travels, which I said in one revolution, we just calculated it, was 3.33 times 10 to the minus 10 meters. And now I can solve for the time, right? So I can go about and solve it right now because I noticed that my meters are consistent with the meters on the left-hand side, meaning that the distance value in the speed is in meters, and the actual distance is also in meters. Therefore, I can just go about and solve. Just remember your time value will work out to be in terms of seconds because that's the time value in the speed. Okay, so let's just clean it up. Let's get rid of the units. So 2.20 raised times 10 to the 6th will equal 3.33 times 10 to the negative 10 divided by t. Solve for t, just switch these two variables. So t is equal to 3.33 times 10 raised to the negative 10 divided by 2.20 times 10 raised to the negative 6. Excuse me, not negative 6, 10 to the 6th. And now just plug that into the calculator. So we get, okay, take that divided by 2.2, second e to the 6th. So we get a value of the time it takes would be 1.51, I'm going to round to 3 sig figs, times 10 to the negative 16 seconds. Okay, so this is the time it takes to make one revolution. Right? So essentially I can write this value as something that looks like this. So it's 1.51 times 10 to the minus 16 seconds per one revolution. And now what we want to find is actually, take a look back at the problem, we want to find though revolutions per second. So essentially I know seconds per revolution, but what I want to do is I want to find the reverse of that, revolutions per second. So all we need to do is simply just flip this fraction. So now I'm going to put one revolution on the top and divide it by 1.51 times 10 to the minus 16 seconds. This will now tell me revolutions per second. So simply just plug that value into your calculator. So 1 divided by 1.51 times 10 to the minus 16 works out to about, and I'm going to round, so this works out to approximately, I'm going to write it below, 6.61 times 10, again, three significant figures, to the 15 revolutions per second. So that's how many revolutions it would make. A whole bunch. Okay, so that takes care of essentially part A. Now for part B, it says what is the electron's average velocity? So the object is moving, the electron is moving in a circular orbit, right? So we have to know where it starts and where it ends. But let's just assume, because we're talking about revolutions, right? If it makes one revolution, so let's say the electron's starting here, okay? If it starts here and makes one revolution, it would also end in the same spot. So remember what that means in terms of velocity. Okay, I'm going to write the formula on the upper right-hand corner. So average velocity is equal to the average displacement divided by not the average displacement, but the change in displacement, but divided by the change in time. So writing out the change in displacement, I can write the final displacement minus the initial displacement divided by the change in time. So what's the displacement value at the end, meaning when it makes one full revolution? Well, I don't know. Just call it x. And then what's the displacement value when it starts, or where it starts? Well, it's the same thing, right? Because it started and ended at the same point. So I would call that x as well. Well, what's x minus x? 0. And what's 0 divided by t? 0. So that would be your average velocity. Number 16. A cheetah can accelerate from rest to a speed of 30 meters per second in 7 seconds. What is its acceleration? Okay, so let's first start with a formula for acceleration. So remember that the acceleration, that's the average acceleration of an object, will be equal to the change in the velocity of the object divided by the change in time. Okay, expanding the numerator, right, the change in velocity, and any change value that is, any change value will always be the final value minus the initial value. So, to calculate average acceleration, it would require us to know the final velocity and subtract it from the initial velocity, divided by the change in time, which could also be represented as the final time minus the initial time. Okay, so in order for me to calculate acceleration, I need to know these values. So let's see if we do. So what's the final velocity in this problem? Well, it says that the cheetah accelerates from rest to this speed, right, of 30 meters per second. So it sounds like this is the final speed that the cheetah will reach in this problem, at least. It doesn't mean that that's the maximum speed it can ever attain. And it looks like it started or had an initial value of resting, meaning 0, right? Okay, so let's plug those values in. So the final speed value was 30, or final velocity value was 30.0 meters per second, minus the initial velocity was 0 meters per second. And that's all now divided by the time, right? So it says it took the cheetah 7 seconds to do this. Well, I can assume that the time value at the beginning, right, was 0. That's when the clock essentially started. So therefore, the final time would have been 7.00 seconds, and the initial time again was 0 seconds. So now, to solve for the acceleration, just simply do the easy subtractions, right? So it's going to be 30.0 meters per second divided by then seconds, 7.00 seconds. So the average acceleration in this problem, very simple. 30 divided by 7, so we get 4.29. And I'm going to round to 3 significant figures because I have 3 significant figures in both of my values. So this is 4.29 meters per second now squared. And that would be the acceleration. Number 17, a professional application. Dr. John Paul Stapp, a U.S. Air Force officer who studied the effects of extreme deceleration on the human body. On December 10, 1954, Stapp rode a rocket sled, accelerating from rest to a top speed of 282 meters per second in 5 seconds, and was brought jarringly back to rest in only 1.40 seconds. Calculate his A, acceleration, and B, deceleration, and then express each of them in multiples of g. Okay, so let's just draw a quick sketch. So let's say here's the start of the problem, all right, with the little dot, and this guy is going to accelerate from rest to, it says, a top speed of 282 meters per second. So the velocity here at the start, right, or his initial velocity should have been 0 meters per second because he's starting off. And then the velocity here at the end should have been the final velocity for this part in black, which would have been 282 meters per second. Okay, and in order for him to change his velocity by this magnitude, it says 5.00 seconds. Okay, great. Now, after that, right, it says now, and was brought jarringly back to rest in only 1.4 seconds. So if we think about how this problem would have continued, he would have still been traveling forward and to the right, right? So I'll just continue that on out. And finally, he would have been brought to a stop, right, at about this point, right, where he came to a stop. Okay, so now, in terms of the part in red, okay, the time that elapsed, it says, was 1.40 seconds. The velocity here at the end of the red part would be his final velocity, which was 0, because it said he came to rest, meters per second. And then in terms of the initial part of the red part of the problem, his initial velocity here would have been 282 meters per second. Okay, we should have enough we need to calculate now part A and B. Now you might be saying, well, wait a minute, how can this one point here have both? How can it be called a final velocity and an initial velocity? Well, that's a good question, actually. It depends on the frame of the problem. A very important concept in physics, and as you guys will get into it, is how to frame the problems. So in terms of the black frame, or the dark gray frame of this problem, this point would be considered the final value for the, like I said, the dark gray or the black frame. But if I'm looking at the red frame, then that's the start of my red frame, and this location over here would be the end, or the final point of the red frame. Okay, so just keep that in mind as we go throughout the class. Framing is very important. All right, so now let's calculate part A. So it says calculate his acceleration, right? So remember, acceleration is equal to change in velocity over change in time. Okay, so acceleration will be the final velocity value minus the initial velocity value divided by the final time value minus the initial time. Okay, so for the gray part, right, the final velocity in the gray part, the dark gray part that is, would be 282 meters per second, right, minus the initial was 0 meters per second. And that'll all be divided by the final time value, which we can consider to be 5.00 seconds. And then the initial would have been the start of the clock, right? Meters per second. Okay, so now the acceleration for the black frame here is essentially, let's do 282 divided by 5. So 56.4. So 56.4 meters per second squared. That would have been his acceleration. Now I'm going to leave it in 3 significant figures because I have 3 significant figures in both of my numbers here. Okay, so now for part B, which is the red frame now, I'll just do this all in red. It says to calculate the deceleration. I'm going to do it in terms of acceleration, and what we should see is that the value should be negative. So when the acceleration is negative, that means it's decelerating. Okay. So acceleration, average acceleration, you can just leave the bar out, it doesn't matter, is equal to the change in velocity divided by change in time, same thing. So the acceleration is equal to the final velocity minus the initial velocity divided by the final time minus the initial time. Okay, so now in the red frame, what's the final velocity? The final velocity was 0. So 0 meters per second minus now, what was the initial value for the red frame? Well, the initial value for the red frame was 282 meters per second. Now that'll be divided by the final time, and then subtracted by the initial time. So this part you can get a little creative, it doesn't really matter. You can say, well, the total time that would have elapsed should have been the 5 seconds plus the 140, right? So the final time would have been here 6.40 seconds. And then you could have said, well, the time here at the start of the red frame would have been 5 seconds, right? 5.00 seconds. Okay, great. So if those are the values, let's plug them in. So 6.40 seconds was the final time. The initial time then in the red frame was 5 seconds. And notice what you get in terms of the denominator, right? So let's first look at the numerator, right? It's just going to be negative 282 meters per second. And the denominator, when we subtracted to it, just simply came out to 1.40 seconds. It's the same thing that they gave us, right? So if you calculated the change in time as we just did, it's totally fine. Or you could have assumed it started at 0 here, and the end time was 1.40. That would have been fine too, because that would have came out as well. Doesn't matter. All right, so now when we do the math here, so let's plug that into the calculator. Negative 282 divided by 1.4. So it comes out to a value, so crazy acceleration, a deceleration that is. So it's negative 201, okay, because I need three significant figures, meters per second squared. So that would be the acceleration. It's negative, therefore it is a deceleration. Now it says so for part, well, it's not really part C, but I'll call it part C. So then for part C here, it says to express each in multiples of g. So I'm just going to give you a quick formula for g. So basically, g will equal the acceleration value divided by 9.80. Okay? So in terms of, g for the black part, right, would have been the acceleration value of 56.4 divided by, and these, by the way, all have to be in meters per second. That's the assumption here. This value here needs to be in meters per second squared. I think I just said meters per second. It has to be meters per second squared because those are acceleration values. Okay, so as long as they are, you can plug them in. If not, you got to do a conversion. Then divided by 9.80. So g for the black frame would be 56.4 divided by 9.80. So it comes out to, and we're going to round to 3 sig figs, 5.76 g. And that would be that. Easy enough. Now for the red frame, right, we'd have to do essentially the same thing. The g is equal to the acceleration divided by 9.8. In this case, it's negative 201, right? So divide that value by 9.80. So again, g here will be equal to negative 201 divided by 9.8. And that works out to be negative 20.5. And that's 3 significant figures. And we could put the g at the end if we wanted. Number 18. A commuter backs her car out of her garage with an acceleration of 1.40 meters per second squared. Letter A. How long does it take her to reach a speed of 2.00 meters per second? All right, so let's work with part A first. Let's just draw a quick sketch. So this individual is backing out of her garage, and she accelerates with a value of 1.40 meters per second. Well, accelerates, and the acceleration here is 1.40 meters per second squared. Now, it's safe to assume that if she's starting in the garage here, right, this is her start point, that her velocity was initially 0, right? So the initial velocity is 0 meters per second. And it says now in the question, right, that the final velocity is 2 meters per second because they're asking us how long does it take for her to reach this speed. So the final velocity here, she's traveling at 2.00 meters per second. And they're asking us to calculate the time which it took to go from 0 meters per second to 2 meters per second. So let's think about, do we know a formula that relates all of these variables together? The velocity, the acceleration, the time? And we do, right? The acceleration is equal to the change in the velocity divided by the change in time. So in other words, the acceleration is equal to the final velocity minus the initial velocity divided by the time it took, right? Or the change in time. So the final velocity in this problem is 2.00 meters per second. The initial velocity was 0 meters per second. And the time it took her to travel this distance is the question, right? So t is our variable. Now, let's just plug in the acceleration. So I'm just going to erase that because they gave it to us, right? The value was 1.40. So I can plug that in. So 1.40 meters per second squared. And now I can simply calculate my time value. Right? If you notice, there is consistency within the units. The distance, or I should say the displacement unit in the acceleration is meters, as well as in the velocities. And the time values are also consistent, seconds and seconds. Okay, great. So let's do our calculation. I'm just going to rewrite everything though without the units just so we can clear the field a little bit. So 2.00 minus 0 over t. So just switch the t with the 1.40. So the time would now be equal to 2.00 divided by 1.40. So now the time would be, plug it into the calculator, and it works out to be 1.43 seconds. Great. So that is the time it took her to back out of her driveway and accelerate to a value of, or not accelerate, but to reach a final velocity of 2 meters per second. Now let's take a look at part B. If she then brakes to a stop in 0.8 seconds, what is her deceleration? Okay, so basically if we continue this picture on out, right, she's going to brake and eventually come to a stop, right? So in terms of the gold frame here, her final velocity here would actually be 0 now, meters per second. And the initial velocity at this particular point is the same as the final velocity of the black frame. A reason being is because the 2 points are the same, right? The end of the black frame is the same as the beginning of the yellow frame. So I'm just going to move the box up here a little bit just so I don't cut off the line. And now what I need to do, and now also they told me that the time it takes to go from 2 meters per second squared to 0 meters per second is 0.800 seconds. And that's the time. Okay, so now again, do we know relationships between these variables? Yes, we do. Now remember, they're asking us to calculate her deceleration, aka her negative acceleration. So let's use that formula again. So acceleration is equal to change in velocity divided by change in time. So the acceleration is what we're looking for. The velocity can be broken down then into final velocity minus the initial velocity, divided by the change in time. So now the final velocity we said was 0 meters per second. The initial velocity was 2.00 meters per second. Remember, I'm only considering the yellow frame here. And then the time it took her to go from 2 meters per second to 0 occurred in 0.800 seconds. Great, so now I can just calculate my acceleration. I have consistency amongst all the units, meaning the distance or the displacement is in meters and the time is in seconds. So now let's just clear the field, get rid of the units. Just remember your units though, so that you can place them in when you finish the acceleration calculation. Right, so the numerator here should be negative 2.00 over 0.800. And as we said before, this should be negative. So if the object is slowing down in the positive direction, it therefore has a negative acceleration. So negative 2 divided by 0.8 works out to be negative 2.5. So the acceleration is equal to negative 2.5. And I'm going to add another 0 there because I have to have 3 significant figures, because both of the measured values do have 3 significant figures. And the acceleration is meters per second squared. And that would be the final answer for letter B. Number 19. Assume that an intercontinental ballistic missile goes from rest to suborbital speed of 6.5 kilometers per second in 60 seconds. The actual speed and time are classified. What is its average acceleration in meters per second squared and in multiples of g? Okay, so what are we given in the problem? So it says that a missile goes from rest, right, to a speed of 6.5 kilometers per second. So those sound like rates to me, and specifically they're velocities, right? So it starts at rest, and it then gets somewhere to a speed of 6.50 kilometers per second. That's the final velocity. Okay, and then the initial velocity here at the beginning was 0 because it started at rest, kilometers per second. Okay, and it takes the missile 60.0 seconds to obtain this velocity. Okay, great. Now it says, what is the average acceleration? So, what's the formula for acceleration? The formula for acceleration is equal to the change in velocity divided by the change in time. So in order for me to find the acceleration, I need to know the change in the velocity and the time in which that change in velocity occurred. And we do, right? We know those things. So we can calculate the average acceleration. So just breaking down the change in velocity, it's the final velocity minus the initial, divided by the change in time, right? Or the final time minus the initial time. Okay, great. So the acceleration now is the final value of the velocity. So that was 6.50 kilometers per second minus the initial value, which was 0 kilometers per second, all divided by the final time, which would have been 60.0 seconds, and the initial time would have been 0 seconds. Great. Everything looks nice and consistent here. So I'm going to calculate, meaning the time values are all the same. So let's just calculate. I don't need to make any conversions yet. So the acceleration here, I'm going to get rid of the units. It's going to be 6.50, right? Divided by 60.0. Okay. So now when I calculate this, let me do 6.50 divided by 60. So it comes out to a value of 0.108. Now remember, this is in kilometers per second squared. Go back and look at the displacement value. It's in kilometers. Therefore, your acceleration is in kilometers. I'm just going to dot this. This would be an answer, but they didn't want it in kilometers per second. They just wanted it in meters per second. So all I have to do is convert the kilometers to seconds. Excuse me, that would be a conversion. Convert kilometers to meters. And then once I do that, I'll have my answer. So let's do that over here on the, we'll do it on the right-hand side. So I'm looking to take 0.108 kilometers and convert that into meters. So we'll write down what we're given, 1.108 kilometers. The kilometers must go on the bottom. The meters go on the top. There's 1,000 meters in 1 kilometer. Kilometers go bye-bye. And now just multiply the 0.108 by 1,000. Just move the decimal place 3 places to the right. So it's 108 meters. Now, since it was kilometers per 1 second, now the answer would just be 108 meters per second. Right? Because I'm going to essentially divide this by 1 second squared. All right. So now the answer becomes 108 meters per second squared. And that would now be the average acceleration in meters per second squared. So that's the answer to the first part. And then the second part says, let's now calculate it in multiples of g. So quick formula for g here. G is equal to the acceleration value divided by 9.80. Okay. So all we have to do to find the g value is simply take your acceleration that we found over here, we just found, plug that in. All right. Now, the only thing here you got to remember that the unit here, 9.80, is in terms of meters per second squared. Okay, what that means is that the only units you're allowed to plug into this particular G formula for the acceleration, they must also be in meters per second squared. Anything else, your number and your answer is going to be wrong. Okay, so just always make sure. So I do see that I did calculate it in meters per second squared, so therefore I'm just going to plug in the 108 and divide it by 9.80. And I just got to throw it into the calculator. Throw it on in. So 108 divided by 9.8 works out to a value of 11.0. And again, 3 significant figures because both numbers have 3. And that would be the G value. Final answer. Number 20. An Olympic class sprinter starts a race with an acceleration of 4.5 meters per second squared. Letter A. What is her speed 2.4 seconds later? Okay, so let's just sketch a quick picture. So we have a sprinter, and she starts a race, and her acceleration, right? Well, she's starting from rest, right? So we know that the initial velocity here would be 0. And it says that her acceleration is 4.50 meters per second squared. And it wants to know her speed 2.4 seconds later. So the time that elapsed from, let's say, the starting point to now the ending point, okay, is t is equal to 2.40 seconds. So what we now need to do is we need to figure out at this particular point what is her speed or her velocity. Okay, the question asks for speed. I know I'm using v here. In the problem, they're going to be the same, but I will start using the variable s. So actually, just so we don't confuse anyone, let's just substitute s in here right now, and then again back over here for initial. We'll just put speed. Okay. All right. So now the formula, right? If we're thinking about speed, speed is equal to change in displacement over change in time. And another formula that we may need, that we probably will use instead, is going to be the acceleration formula. Is usually the change in velocity over the change in time. But like I was saying before, since velocity and speed in this problem are going to be the same. So I'm just going to change that to be change in speed over change in time. So now, if we're looking to we're trying to find the final speed basically, right? So let's just expand the delta s. So the final speed minus the initial speed divided by the change in time. Okay, so the acceleration they gave to us was 4.50. Right, so 4.50 meters per second squared, and equals the final speed minus the initial, which was 0, divided by now the change in time, and for this problem it was 2.40 seconds. So from here I can now do my calculations. I have consistency within the time units, so that's good. Now, when I do find the speed value, it will be in meters per second, okay? So let's just now get rid of all those units just to clean things up a little bit. So 4.50 will equal the final speed divided by 2.40. So just do a cross multiplication here. Take out the calculator, 4.5 times 2.4. So it comes out to 10.8. And we have 3 significant figures, so that works out. This is meters per second. And that's the final speed there when the sprinter reaches a time of 2.40 seconds. Now for part B. So now it says to sketch a graph of her position versus time for this period. All right, so what we can do is we can come up with a few general graphs. Okay, so I'll give you a couple here. So let's assume that we have a constant acceleration and that the acceleration is a positive value. Okay, so here we'll do acceleration as a positive number. The graph, I'll give you a few graphs. The graph of then the acceleration versus time, remember the acceleration will be constant, should be just a nice straight line. Okay, now if I were to then draw a graph of, let's say, the velocity per time, okay, this is all for constant acceleration. So constant A, okay. This graph will be linear and will be increasing with a positive slope. And now, last but not least, we can now draw the position graph. And the position graph would be essentially the distance versus time, right? Or displacement versus time here. What we're going to see here is we're going to see almost like an exponential type of graph now. Okay? So these are the 3 graphs you must be familiar with when you're considering a constant positive acceleration. Okay? If it were a constant now, actually, I'm just going to write If it were a negative acceleration, okay, that would be a deceleration, we would have these three graphs now. Just draw a little line. We would have these three. So now the acceleration value, right, if I were to think about where this would be the time, this would be the acceleration, and now the graph would just be there at the bottom, right, of my axes. Okay. The velocity now would depend on, what the starting initial velocity would be, but it's going to be a negative slope. Okay, that's for sure. So it's going to have that appearance to it. And then if I were to think about now my position versus time graph, it should have a form of something like this now. Okay. Last but not least now, so we talked about positive acceleration, negative acceleration, and now let's say when acceleration is 0. What do the graphs look like? Well, right, the acceleration versus time graph would now be where the acceleration is just 0 the whole time, right? So it's down there on the x-axis. The then velocity graph will look like this now. We have velocity here. The velocity is now constant, so now it'll be horizontal. Whether it'll be a positive velocity or a negative velocity, I don't know. But I do know that it will be horizontal, and that's most important. Okay? And then, last but not least, if I were to now draw let me make it a little bigger. Oops. If I were to now draw the position versus time graph, this graph will now look like a linear increasing function. And again, it'll be increasing if the velocity is positive, or if the velocity were, let's say, a negative value. I'll put that in black here. The velocity were a constant negative number, then we would see the graph of the position versus time just have a negative slope. So those are all the possible cases of graphs that you can see. So if it asks us just to sketch, a graph here, what we really want to think about which one of these looks like 9 models, right? Or if you count the black ones as separate, then that would be 11 models, right? The black lines here with the negative velocity and therefore the negative slope on the position graph. We just have to pick out which one it is, right? So notice the acceleration. Let's go back to the problem. The acceleration is positive, right? So if we got to sketch a position versus time graph, it would look something like this. Okay, so I'm going to draw that over here on the right. So time, distance, we know that she's starting from rest, so therefore her position we could assume to be 0, and it would just be a sketch like this. It would be it would have a constantly changing slope there, and that would be the general sketch. Maybe we have to also find some time values, but we'll do that in another problem. Number 21. A well-thrown ball is caught in a well-padded mitt. If the deceleration of the ball is 2.1 times 10 to the 4 meters per second squared, and 1.85 milliseconds has elapsed from the time the ball first touches the mitt till it stops, what was the initial velocity of the ball? All right, so let's just create a quick sketch. So we have a ball, and it says that, well, it doesn't say it's thrown, but it must be thrown, right? So it's thrown, and it's going to hit this particular mitt right here. Okay? And what's going to happen is as soon as the ball hits the mitt, the ball's going to slow down. All right? So let's just draw this little part in here like in red. Okay? So it's going to slow down as it hits the mitt. Now, the deceleration it said on this ball during this particular point is 2.1 times 10 to the minus 4, as it says in the problem. So the acceleration then, since it said it's a deceleration, we have to make sure we put it in as a negative sign. So 2.10 times 10 to the minus 4 meters per second squared. Okay, and the time it takes to go from just touching the mitt to then eventually coming to a stop is 1.85 milliseconds. All right, so the time value there is, so t is equal to 1.85 milliseconds. And it also gave us a nice conversion factor if we need. So, okay, now it says the ball then eventually comes to a stop, right? So the ball comes to a stop at this particular point where that arrow is. So right here, the velocity, on the final velocity, right, is 0. Why is that the final? Well, because I'm given information or being asked information about the initial point, which is right here. So if that's the initial, then sometime in the future, meaning when the ball reaches this particular point, that has to be the final value. Okay, so this is the initial velocity. Now that's what we're looking for. They want us to find the initial velocity. Okay. They gave us the acceleration, as I wrote down over here. So we do know that the acceleration is negative 2.10 times 10 to the negative 4 meters per second squared. And I do know that the final velocity is equal to 0. So what I'm actually going to do first, before I think about any equations, I'm just going to make sure I have consistent units here. So I notice the time was in milliseconds, but yet my acceleration is in seconds. That's not good. You have to make sure that the time values are consistent. So let's simply take 1.85 milliseconds and convert that into seconds. So let's write that over here, 1.85 milliseconds, convert that into seconds. Let's write down what we're given, 1.85 milliseconds. Milliseconds, and milliseconds on the bottom, seconds on the top. Now they gave me a conversion factor right here in the problem. So what I'm going to do is I'm going to plug that in. So it says 1 millisecond for every 10 to the minus 3 seconds. Milliseconds will cancel, leaving you with seconds. So now all you have to do is just multiply that in the calculator. So when you do so, it's going to come out to 0.00185 seconds. Great, so that's the new time value, okay? So this equals, it's the same thing as saying 0.00185 seconds. Okay, wonderful. Now, let's take a look. We have all these variables, okay, and we're looking to solve for the initial velocity. I know the time, I know the acceleration, and I know the final velocity. So now what you want to do is you want to consider a formula that relates all 4 of these variables. Why? Because if you know a formula that relates all 4 of the variables, but yet you don't know one of them, you can do algebra to find it. So let's take a look at the formulas on the upper right-hand corner. Which formula has all 4 of those variables in it? Yep. If you notice the one all the way at the top, you'd be correct. So let's write that formula down. So it says that the final velocity is equal to the initial velocity plus the acceleration multiplied by time. So let's just plug in the values. The final velocity is 0. The initial velocity is what we're looking for, so let's leave that VI. The acceleration was a negative 2.10 times 10 to the minus 4. I'm also going to leave out the units now because I know that they're all consistent. And the time was 0.00185. Now just know that the initial velocity, the unit that we will find, will be in meters per second. Reason being is because those were the units of the distance value was in meters and the time value was in seconds. So let's do some math. So this is 0 equals the initial velocity. Now multiply negative 2.10 times 10 to the minus 4 multiplied by 0.00185. Okay, so now it's a VI minus, it's negative, 3.89, because I'm going to round to 3 sig figs, times 10 to the minus 7. Okay, great. So now I just have to add this on over, 3.89 times 10 to the minus 7, and then add that on over to, I realized, I'm like, wait a minute, this doesn't look right. I'm like, wow, that's a really small initial velocity. The ball was barely moving. See? So even I make mistakes, but let's learn from it. So as I'm calculating this, right, to give you a little thought, give you a little insight, as I'm calculating this, I'm like, well, wait a minute, the initial velocity is going to come out to be this. That 3.89 times 10 to the minus 7, that's like this, right, with the decimal over here. It's really small. It's really small. It's way too small to be reasonable. So, not that everything has to be reasonable, but it's always a good check. So, I say to myself, well, wait a minute, did I make a mistake somewhere? So I look back, and sure enough, I did, right? Some of you may have caught the mistake before, so thank you, that was good. Some of you may have not. Take a look for it now. Can you find it? Well, the mistake is right here, and this is a silly mistake, and these are the mistakes you want to minimize, because these are really going to affect your grade. The deceleration is 2.10 times 10 to the minus 4. So look back up at the problem. But look what I wrote. Look what I wrote. I, for some reason, converted it to a negative 4. So, totally wrong. Okay? So, here's a lesson that you can learn actively as I'm making my mistake. Okay? So, always check to make sure the answers are reasonable. And if the answer doesn't make sense, it doesn't mean that it's not right, because maybe they gave you a weird problem. But it's always a good idea to go back and check then. Just make sure. Okay? Because usually they'll be pretty accurate. So now just what I'm doing is I'm going to erase all the negative 4s and just put 4 there. Okay? I got to do one more here. Right? Erase that one. Let's put a to the 4th. Okay? Now, since I corrected them everywhere, I don't see any more mistakes. Let's finally now calculate this this initial velocity correctly. All right. So now what I'm going to do is now I'm going to multiply these two numbers. All right. So negative 2.10 times 10 to the 4th times 0.00185. And I look at my calculator, and now I plugged in 1.00128 instead of 185. See, I'm always constantly checking. Why? Because I've made plenty of mistakes in the past, and I learn from them. So always constantly check your work. Okay? So now I went back and I recalculated it, and it is correct because I'm looking at it on the calculator. So this should work out. So this should be minus 38.9. Okay? Now to solve for the initial velocity, add the 38.9 to both sides. Okay? That cancels. Therefore, now I'll write it on the side. So now my initial velocity is equal to 38.9 meters per second. That sounds a lot more reasonable. Number 22. A bullet in a gun is accelerated from the firing chamber to the end of the barrel at an average rate of 6.2 times 10 to the 5 meters per second squared for 8.1 times 10 to the minus 4 seconds. What is its muzzle velocity? That is its final velocity. All right, so let's write down what we're given. So it says that the bullet is accelerated at this particular rate of 6.2 times 10 to the 5. So let's write that down. Acceleration is equal to 6.02 times 10 to the 5 meters per second squared. Okay. It also says that it is traveling with this acceleration for 8.1 times 10 to the minus 4 seconds. So let's write down that as the time. So 8.10 times 10 to the minus 4 seconds. That doesn't say it explicitly in the problem, but since the bullet is being fired, right, we have to assume that it is starting from rest. So in some books, you might see it written as V naught, right? That stands for initial velocity. I actually prefer to write VI, but they're going to mean the same thing. That's 0 meters per second. And then what they're asking for is they're asking for the final velocity. So they're asking for VF. Okay. So what we want to do now is we want to think about, do we know a relationship between these these 4 variables? And let's see. Bam! Now here's all of the formulas we need for this chapter. I'm going to put it over here on the upper right-hand corner. So take a look at those formulas and let me know if there's, you can let me know, I won't hear you, but think about if there is one particular formula there that relates all 4 of the variables I circle in red. So if we search through it, what do you guys think? So keep looking if you can't find it. Right, so we have final velocity, initial velocity, acceleration, and time, and here it is right at the top, right? So that's the one we're going to use. So let's write it down. So we have final velocity is equal to the initial velocity plus the acceleration multiplied by time. So if I know 3 out of these 4 variables, that means I can solve for that 4th one that I don't know. So we're looking for the final velocity, so let's leave that as Vf, or V sub f. The initial velocity is 0. The acceleration in the problem is going to be 6.02 times 10 to the 5. Right, meters per second. I'm just going to leave out the units for now, just to make things neater. And then the time, it says that it's 8.10 times 10 to the minus 4 seconds. Okay, great. So just remember to check the consistency within the units here, meaning the time values have to be consistent. They are both in seconds, so that's good. And my meters, I actually don't have any other value in which they gave me the value of the displacement or the unit of the displacement. So that should be fine. Just know that when you calculate your final velocity, it will be in terms of meters per second. All right? Okay, so now let's go back to the calculation here. And all we have to do is basically just plug it in, right? So take 6.02 times 10 to the 5, multiply that by 8.1 times 10 to the negative 4, and wow, it's pretty fast. So that reaches a final velocity of 400, and I'm going to round to 3 sig figs, 488 meters per second. That's the final velocity of the bullet. 3 significant figures because I have 3 significant figures in my acceleration and 3 significant figures in my time. Therefore, I should have no more than 3 significant figures in my answer. Number 23. Letter A. A light rail commuter train accelerates at a rate of 1.35 meters per second squared. How long does it take to reach its top speed of 80 kilometers per hour starting from rest? All right, so let's just sketch a very quick picture. So let's just call the dot the train, right? And it's going to be moving forward. And it's starting at, it says it starts from rest, right? So its initial velocity must be 0. Okay, I'm going to use the units of kilometers per hour because it looks like that's what they're giving in the problem. Then it also says, yeah, it doesn't, yeah. Well, actually, you know what? Let me write it in meters per second for right now. It doesn't really matter because it's 0, okay? But I'm just going to write it in meters per second for now. It wants to know how long it takes, right, to reach its final speed of 80 kilometers per hour. So the final velocity here is 80 kilometers per hour. And again, remember, it's asking for how long, right? The time here it's going to take to go from the start to the end, okay? And it gives us another piece of information. It also says that it is accelerating, right, at a rate of 1.35 meters per second squared. Okay, so let's look at what we're given here, right? We know the acceleration, we know the initial velocity, we know the final velocity, and we're looking for time. So, do we know of a formula that relates these 4 variables? So, let's take a look at all the formulas. I'm going to put it on the upper right-hand corner. So now, if you do take a look, it looks like we can use the first formula, right? The one all the way at the top. So let's use that one, all right? So this is for letter A. I'm going to put it over here. So for letter A, we'll use the final velocity is equal to the initial velocity plus the acceleration multiplied by time. Now, what you have to make sure is that you have to make sure all the units are consistent. Okay, and unfortunately in this problem, if you look closely, they gave us a final velocity in kilometers per hour, but then they gave us our acceleration in meters per second. So both the displacement the displacement unit of meters is not the same, right? One's meters, one's kilometers. And then the time value is also not the same. One's in seconds, one's in hours. So we have to make sure that they're consistent. So what this tells me is that I need to do a conversion. What I'm going to do is I'm going to convert this into meters per second so that I do have consistency amongst my units. So let's do that at the bottom here. So we're going to do 80 kilometers. So actually, let me give myself a little room. let me do it up here on the top, okay? So let's do 80 kilometers per hour, per 1 hour that is, right? And we want to convert that into meters per second. So think about this in a 3-step process. Step 1, convert kilometers to meters. Okay, I'll write a little 1 there. Step number 2 will be to convert hours into seconds. And then step number 3 here will then be to divide your meter value by the second value. Okay, so part number 1. So 80 kilometers, convert that into meters. So 80 kilometers, kilometers on the bottom, meters on the top. There's 1,000 meters in 1 kilometer, so the kilometers cancel. And this leaves me with now 80,000 meters. Okay, great. So that's the first part there. The second part now is going to require us to go from 1 hour to seconds. So let's start with what we're given, 1 hour. I'll put hour on the bottom, but I can't put seconds yet because I don't know the relationship, meaning how many seconds there are in an hour. By the way, that's 3,600, but let's just assume that we don't know it. But we do know the minutes to hours, right? So that's 60 minutes in an hour. The hours go away. And then I would put the minutes on the bottom and now the seconds on the top. So that'd be 60 seconds in 1 minute. And again, as I mentioned before, 3,600 seconds. Great. So now for the third step of this conversion, what I'm going to do is I'm going to take then the answer to the first part, the 80,000 meters, divide that then by the 3,600 seconds. And when I do this division, I will get meters per second. So take out your handy dandy calculator, 80,000 divided by 3,600. And I'm going to do, what do we have here? So let's do 3 significant figures because that's actually what we were given. I was a little sloppy here. If you go back to the problem, notice how they gave us 80.0, right? And I was just using the simple value of 80 here. It won't change the value, but it'll change the amount of significant figures we go out to. So let's just be consistent. So it would come out to be 22.2 meters per second. Okay, great. So now this value right here that I calculated, I'm going to use as my final velocity. So these two values are equivalent. 80 kilometers per hour is the same thing as 22.2 meters per second. So I can use them interchangeably, but when I have to use the final velocity in my formula, I have to make sure the units are consistent again. So let's now finally plug in the values. So the final velocity in the equation will be 22.2. I'm going to leave the units out just to make it neater. The initial velocity was 0. The acceleration was 1.35. And I'm looking for time. Okay, so this just simply works out to 22.2 is equal to 1.35 times t. Divide out then the 1.35. Divide out the 1.35. And we have now t equaling, let's see, 22.2 divided by 1.35. So 16.4. So we got 16.4 seconds. Why is it in seconds? Because that's the time value of all the other units. Okay, so we answered part A. So this is the answer for part A. Okay, now let's take a look now at part B. It says the same train ordinarily decelerates at a rate of 1.65 meters per second. All right, so let me just do a quick highlight here. So the train is now decelerating at 1.65 meters per second squared. Now, how long does it take to come to a stop from its top speed? Okay, so now if I continue the picture on out over here, if I continue the picture on out, what I would notice is that basically I'm going to start now the second part of the problem, part B, from the same location here in red. And now I'm going to be moving, it's still moving to the right, right? The object is still moving to the right, but it's going to be slowing down. Okay. So I know that if I'm considering now this yellow line as the frame of my problem, this point now actually becomes the initial value. And the end point here becomes my new final value. Okay, it's very important in physics in terms of framing the problem. So the initial velocity, it started out in the yellow frame here. It started out at 22.2 meters per second. The final velocity of this frame is 0 because it said it came to a stop. And now it says that it is decelerating, right? Which means the acceleration is negative. Okay, so the acceleration is a negative 1.65. I'm just going to write the units down here, meters per second squared. Okay. So now again, we need to find the time, right? They're asking us now for the time here. So I need to think of a relationship between initial velocity, time, acceleration, and final velocity. And again, we can use that same formula, right? So that works. So let me write part B over here on the right-hand side. So we would use the final velocity is equal to the initial velocity plus the acceleration multiplied by time. So the final velocity in this problem was 0. The initial velocity was 22.2. The acceleration was a negative 1.65. And again, I'm looking for the time. So that's my variable. So now when we do the math, right, this simply becomes 0 is equal to 22.2 minus 1.65 t. Great. Add the 1.65 t to both sides. Add 1.65 t to both sides. There's the line. There we go. Now the time becomes, not the time, but the left-hand side becomes 1.65 t. And that will equal 22.2. Now simply divide out the 1.65, right? In order to get t by itself. Take out that calculator. And 22.2 divided by 1.65. And notice how we get a value of 13. Again, I'm going to use 3 sig figs, 13.5. Seconds, that is. Why seconds? Because go back and look at all the time values or the time units in the other variables. Okay, and notice the time came out to be positive, which it should be. Time won't be negative. Okay, so part B is done. This is the answer now to part B. And then finally part C. It says, in emergencies, the train can decelerate more rapidly. Okay, let's start highlighting some stuff. It says the train can decelerate more rapidly, coming to a rest from 80.0 kilometers per hour in 8.3 seconds. What is its emergency deceleration in meters per second? So it's asking us to calculate for the acceleration, right? But the acceleration will just be negative. So let's do that particular calculation over here on the top left. So letter C. Let's write down what we know. So it sounds like it says the train is coming to a rest, right, from 80.0 kilometers per hour. Now remember, the 80.0 kilometers per hour is the same thing as, I already did the conversion, it's the same thing as 22.2 meters per second. Okay. Now this value will represent, in part C, it should represent the initial velocity, because the problem is framed as such, where we're starting, right, with some velocity, and then it's coming to a stop here. So the end part, the ending of the problem, I apologize. There's a lot of barking. I think my dog may have just eaten the mailman. Or still is. But anyway, don't mind the distraction. Well, seems like stuff is really unraveling downstairs. Yeah, what are you going to do? Anyway, so the final velocity here is 0. Okay. The initial velocity then will be the value I just found before when I did the conversion. Okay. And they told me that the time it takes to go from the initial state to the final state will be 8.30 seconds. Okay? So great. So now we should have enough information in order to solve the problem, right? They're asking us what is the acceleration. So if we think about the relationship between all the variables, we would be, again, using the same formula. The final velocity is equal to the initial velocity plus the acceleration multiplied by time. Final velocity here is 0. As we mentioned, the initial velocity will be 22.2. The acceleration is what we're trying to find, and the time it says will be 8.30. Okay, so let's just do the math. I can already see that let me subtract over the 22.2, right? 22.2. that cancels. This is now negative 22.2. And you'll see how these values, the sign values, will all make sense in a second. Now divide out the 8.30 from both sides. That cancels. And now I'll write the acceleration value over here to the right. So take negative 22.2 and divide it by 8.3. And again, 3 significant figures. So we get negative 2.67. 2.67. And that's in meters per second squared. All right. Notice how the acceleration did work out to be negative, which is what we anticipated it to be because it told us that the train is decelerating. Number 24. While entering a freeway, a car accelerates from rest to a rate of 2.4 meters per second squared for 12 seconds. Draw a sketch of the situation. All right, let's draw a little dot here. We'll sketch it on out very quickly. It doesn't have to be a Picasso. So it says that it's starting from rest, so this particular point here will be the initial velocity, and it's starting at rest, so that means it's 0. I'm going to use the units of meters per second. And it says that it accelerates, right, at a rate of 2.40. So the acceleration over this whole distance covered will be 2.40 meters per second squared. And it accelerates over the time frame, right, of 12.0 seconds. So from the initial point to the final point here, it's 12 seconds. So I'll put the time right here, 12.0 seconds. And I also don't know, right, the other part of this is what's going on at the ending point or the final point. And, you know, really the most notable thing to note would be that the final velocity here is something that we don't know at the moment. So that would be a full sketch. Then for part B, it says list the knowns in the problem. I did that already. Now it says how far does the car travel in those 12 seconds? Okay, so it says how far, right? So we're looking for a distance. So we want to know, let me just change the color here. So we want to know what the distance is over this span, okay? Or in other words, the displacement. The distance and the displacement would be the same in this problem. But let me just use the term displacement. It's a little better, okay? So I'm looking for x, all right? So let's see. We're looking for x. We know the acceleration, we know the initial velocity, and we know the time. So take a look at the upper right-hand corner and see if there are any equations that have those variables in them, in which case we know all of them except for one. And it looks like I'm going to land on number 2 here, right? That looks pretty good. So if I write that down, so the change in displacement is equal to the initial velocity, right, multiplied by time, plus half of the acceleration value multiplied by time squared. So the displacement, or the change in displacement, is equal to the initial velocity, which we said was 0, right? The time was 12.0 seconds, plus 1/2 times the acceleration, which was 2.40, times the time squared, so 12.0 squared. Okay, now just doing some math, that part cancels out. Now just plug the rest into the calculator. So it'd be 0.5 times 2.4 times 12 squared. Okay, so we'll do 3 significant figures. So it'd be 173 meters. Now why meters? Well, because look at the distance values in the other variables, right? Look at the acceleration specifically. It's meters per second squared. So therefore, my distance that I calculate should be meters. Okay. So part C is done. So this is the answer to part C. And this whole part here was part C. So it says to solve this part, first identify the known. Okay. Skip all the way down to D. What is the car's, let's highlight it now. What is the car's final velocity? So solve for this unknown. Okay, just find the car's final velocity. So again, I know, so I can use a couple of different equations potentially. So let's see. We want to find the final velocity. And we know now these 4 things. We know the initial, we know the time, we know the acceleration, and we also just calculated the distance, right? Or the displacement. So you might say, well, great, it looks like I can use possibly two formulas, right? It looks like we can either use the first one at the top or the fourth one, right from the top. So either one will work, but in my opinion, one of these is better than the other. Not because one is more mathematically sound, they're both great formulas. But one involves us using our calculation of displacement in the calculation then for the final velocity. So this one, I would have to plug in the displacement value. But let's say you made a mistake, and you made a silly mistake, let's just say. That means if you found the wrong displacement and you plug in the wrong displacement into this equation, now your final velocity will be wrong. So why take the chance, right? If we use the first formula up here, all of those values were just given to us. So we could still make a silly mistake, but there's a lower probability that we would have, right? Because we're really just copying stuff. We didn't have to do calculations and worry about signs and make sure you square it and all this, significant figures, blah, blah, blah. So let's just use, for part D, let's just use the first one. So the final velocity is equal to the initial velocity plus the acceleration times time. So we're looking for the final. We knew that the initial was 0. The acceleration they told us was 2.40, and the time was 12 seconds. So now simply just plug it on in. So it's very quick. So 2.4 times 12 works out to be, and again, 3 significant figures, so 28.8 meters per second. And that would then be the final velocity. Number 25. At the end of a race, a runner decelerates from a velocity of 9 meters per second at a rate of 2 meters per second squared. How far does she travel in the next 5 seconds? All right, so let's just sketch a quick picture. So let's say here the runner is located at this particular point. And what we're going to do now is we'll draw in her direction that she's traveling. Okay, and it says that the runner decelerates from a velocity of 9 meters per second. So I'm assuming that that means that is the velocity at which she is starting out at, or the initial velocity. So 9.00 meters per second. And the acceleration, the deceleration in this case, but the acceleration will be negative 2.00 meters per second squared. Now it wants to know how far, right, does the runner travel? So looks like we're looking for this particular displacement, right? So that's my variable. And it says that they want to know how far does she travel in the next 5 seconds. So they also gave us a time. They gave us a time. That looks like an F. Let's try one more time. There we go. So they gave us a time of 5 seconds. Okay, so let's think about the formulas of kinematics, and boom, there they are, right? If only they could come that easy to you on the test, right? So here are the formulas. I'll put them in the upper right-hand corner. And what I want to do now is I want to look at what I'm given. So I'm given the initial velocity, I'm given acceleration, I'm given time, and I'm asked for the distance. And what we want to do is we want to see, do we know any formulas that relate those four together in one equation? And it looks like we do, right? So it looks like the second one is going to be our winner. Okay, so let's take that formula and rewrite it. So let's change in displacement is equal to the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. Okay, so to find x here, the displacement, I need to know the initial velocity, which was 9 meters per second. The time was 5 seconds, plus then 1/2 of the acceleration, and that was negative 2.00, right? And then the time value was, again, 5.00 seconds, and that's squared. So let's just be a little neater here. Even though the math will work out nicely when I have 9 and 5 there, let's just put the values in with their appropriate number of significant figures. So the initial velocity was 9.00, and the time, again, was 5.00 seconds. So I'm not even going to bother putting units in here because, again, I have consistency in the units, right? Time is in seconds, my velocity was in seconds, the acceleration is in seconds, so that's all good. And the displacement values here are in meters and meters, so that's all good. All right, so let's just now plug this all into the calculator. So 9 times 5, you might not need to do that, right? In the calculator, 9 times 5 is 45. Now add to that 1/2 times -2 times 5 squared. Okay, and that comes out to be -25, right? And now let's add them together. So the change in displacement should be 20, and the unit will be meters. Okay, so that's how far she travels in the next 5 seconds. So that's the answer to letter A. Now let's take a look at letter B. What is her final velocity? So let's pick out that particular point in our picture. I'm going to dot it right here in red. Okay, right here would represent the final velocity value, and that's now what we are looking for. So let's see if we can figure out an equation that relates the known variables, right? So there's a couple of actually equations you can select, but I would actually I would recommend that you choose this one at the top, number 1, that I just boxed in red on the upper right-hand corner. The reason why I'm going to choose that one is because, well, let me just rewrite it down here on the bottom left, and then I'll tell you the reasoning. Initial velocity plus acceleration times time. The reason why I'm going to choose this is because the velocity, the initial velocity was given, the acceleration was given, and the time was given. So I don't have to worry about if I made a mistake, let's just say in calculating my displacement, I don't have to worry about it, that mistake propagating into my next calculation. All right. The only thing I could have mistakenly done is copy down the numbers wrong, right? Whereas if I use a formula that involves displacement and I want to solve then for the final velocity, maybe I would have chosen something like this equation that I just circled on the upper right-hand corner. I could have used this because I know the initial, I know the acceleration, and I just calculated the displacement. The problem though is that if I messed up calculating my displacement, then now my final velocity will also be off. So try to minimize the chance for error. Okay, it's not only a good strategy here in physics, but it's a good strategy in life. Who would have guessed? You get life advice here too, right? All right, so back to business. So the initial velocity is 9 meters per second, right? 9.00. The acceleration was again negative 2.00, and then the time was 5 seconds. Okay, so it looks like my final answer should have 3 significant figures. Okay, and let's do that. So 9 plus -2 times 5. I put 90 instead. I mean, we don't even need a calculator, right? So why am I even wasting my time? So this is 9.00, right? -2 times a -5 is going to be a -10, right? And that's going to be to that decimal. And then when we now actually do this subtraction, we're going to go out only to the ones place. Okay, so let's see what we get. So this will work out to be a -1.0. Okay, so it actually drops down to 2 significant figures. All right. In any case, so that would be the answer for letter B. Okay, -1 meter per second. And letter C says evaluate the result. Does it make sense? No. Right? No. The answer doesn't make sense. Why doesn't it make sense? Well, how the runner, she ended the race, right? And I assume she's going to come to a stop, which means that her velocity, well, her velocity, final velocity could have been 0, but maybe she didn't come to a stop yet. So maybe it was less than the 9 meters per second that she started out at. I don't know, maybe it'd be 7 or 6 or 5 or 4 or 3 or 2 or 1 or all the way to 0. But once we calculate a negative velocity, this implies that the runner is now moving backwards, right? Does that make sense? Would somebody stop and then start running back? Maybe they dropped something, right? maybe they dropped their watch or their iPhone or whatever the case is, and they had to run backwards. I don't know, but I don't think that's what happened here. So I'm going to say it doesn't make sense because why would the runner have turned around unless, like I said, for the reasons I just discussed? All right, so that would conclude Part C. Part C, no sense. Number 26, a professional application. Blood is accelerated from rest to 30 centimeters per second in a distance of 1.8 centimeters by the left ventricle of the heart. Make a sketch. All right, so here's the beautiful heart. And blood will be accelerated right from rest. So the point here, we'll consider the initial point. And it says that it's at rest, so the initial velocity here would be 0 centimeters per second. And it says that it moves a distance, right, of 1.8 centimeters. So this distance here will be 1.80 centimeters. That's the distance or the displacement. And what else? And it also tells us that the final velocity of the object here is going to be 30 centimeters, 30.0 centimeters per second. I know it's a velocity because the units of the measurement are displacement per time. So that's why I know that that's a velocity, even though it didn't state that explicitly. Okay, so here's a sketch. Now it says list the knowns. I just did. Letter C. How long does the acceleration take? So it sounds like we are trying to calculate time, right? Okay, so let's take a look here. So let's write down, so I'm looking for time. Okay, so what I want to do is I want to see, do I know a relationship between these four variables, initial velocity, final velocity, displacement, and time, in one of my equations of kinematics in the upper right-hand corner. So take a look through them. Right, have you found one? Well, it sounds like we might be able to use one of the formulas, right? How about using the last one? So why don't we take a look? So let's rewrite it, right? We have change in displacement is equal to 1/2 of the initial velocity plus the final velocity times time. Okay, great. So let's see what we got. So the displacement was 1.80, that was centimeters. Okay, multiplied by 1/2 times the initial velocity, which was 0, plus 30.0, and then the time is what we're looking for. So this comes out to 1.80 is equal to, so half of the 30 is going to be 15, right? So 15.0 times time. Now just divide out the 15.0 on both sides. Divide by the 15.0. And now time works out to be, let's see. Just take it out and plug it into the calculator. So 1.8 divided by 15. And that was 15.0. Okay, and it comes out to the time value is 0.12. And that's in seconds. I know that because the seconds value was given to me in the velocity. Okay, so that's going to be the time it takes for blood to be accelerated from 0 centimeters per second to 30 centimeters per second. Okay, so now we found out how long the acceleration takes. Okay, wonderful. Now, so that's letter C, and then let's take a look at letter D. So now it says, is the answer reasonable when compared to the time for a heartbeat? Okay, so let's just take what would you say the average heartbeat is of a person? Right? Maybe 60, 70, 80, somewhere around there. Okay, I know it depends on a bunch of things. But let's just say the average heart rate is going to be 60 beats per 1 minute. Okay? Now, if that's the rate of 60 beats per minute, how many beats would that be per second? Well, there's 60 seconds, right, in a minute. So therefore, this should be 1 beat per 1 second. Okay, great. So every time your heart beats, the cycle of the heartbeat takes about a full second, right? But if you think about the actual beating action, right, the actual systole, right, the part that actually ejects the blood from the heart, it would be less than 1 second, right? Because remember, heart rhythms involve systole and diastole, both contraction and relaxation. So the systolic part is a fraction of a second. So let's now compare. So the time value we just calculated was about 1/10 of a second. So can the heart do that? Can the heart, in a beat, speed up the blood from 0 centimeters per second to 30 centimeters per second in 1/10 of a second? Well, yeah, I mean, it kind of sounds reasonable, right? Because the actual lub-dub, right, specifically the lub part, will take a fraction of a second. So I would say that the answer to this would be yes. The answer does sound reasonable. Number 27. In a slapshot, a hockey player accelerates the puck from a velocity of 8 meters per second to 40 meters per second in the same direction. If this shot takes 3.33 times 10 to the minus 2 seconds, calculate the distance over which the puck accelerates. All right, so quick sketch. Here we have a puck, and the puck is going to be pushed forward by the player. Right? The initial, they told us, so the problem starts here. The initial velocity is going to be 8.00 meters per second, and it says that it's going to be accelerated to a velocity, aka a final velocity, of 40.0 meters per second. And that, so this shot, okay, so reading the second sentence, it said this shot takes 3.33 times 10 to the minus 2 seconds. So what that means is that in order for the player to accelerate the puck from 8 meters per second to 40 meters per second, that process will take a total of 3.33 times 10 to the minus 2 seconds. Okay, great. And it says, now what we want to do is we want to calculate that distance, right? So we want to calculate from this point all the way down to this point. So that's my x. Okay, so let's consider a formula that we may know that involves these three variables. So we have displacement, we have time, and we have the initial and final velocities. So let's take a look. On the right-hand side, I got all the equations. So which one might be the best? Well, it looks like this one will work out pretty well, right? The last one. Okay, so this one says that the change in displacement is equal to 1/2 the initial velocity plus the final velocity multiplied by time. So in order for me to find the displacement, I need to know the initial velocity, which it said was 8 meters per second, 8.00. The final velocity then was 40.0. Okay. And then now the time, right? So the time it took, it said in the problem, was 3.33 times 10 to the minus 2. Okay, and that's in seconds. I'm just leaving out the units, but I already know I have consistency, meters and meters, so that's good. So remember, my displacement then will work out to be in meters. Okay. And the time values are all in seconds, so that works. So change in displacement is equal to 1/2. When you add these two together, you get 48. Okay, but 48.0. Why? Because when you add the numbers together, the rules of sig fig say you can only go out to the 10th place here. This other number goes out to the 100th place. So you have to choose the number with the least number of places. Okay, great. And then that'll be multiplied by 3.33 times 10 to the negative 2. Okay. And now my x value is the displacement is. So take out your calculator, plug it in. So 0.5 times 48 times 3.33 to the minus 2 times 10 to the minus 2. And that works out to be a value of 0.3 sig figs. We're going to have to round this, right? So 799 meters. So that will be the displacement. And that makes sense. It's about a little less than a meter. All right. So it sounds reasonable. Number 28. A powerful motorcycle can accelerate from rest to 26.8 meters per second in only 3.9 seconds. What is its average acceleration? All right, so let's draw a quick sketch. Here's the motorcycle, we'll just represent it as a dot. And it's going to start, as it said, at rest. So the initial velocity is 0 meters per second. And it says eventually it's going to reach a velocity of 26.8. Okay, so right at this point at the end of the problem, it reaches a final velocity of 26.8 meters per second. And the time in which it took to go from 0 to 26.8 was 3.90 seconds. Okay, and now the question is asking, what is its average acceleration? So we're trying to find the acceleration. So what I want to do now is I want to look to find if I know an equation that relates all four of these variables: initial velocity, time, final velocity, and acceleration. So take a look on the upper right-hand corner. And which formula do you think? It looks like it's going to be the first one, right? So let's write that down. So part A. So we got final velocity is equal to initial velocity plus acceleration multiplied by time. So the final velocity here is 26.8. I'm going to leave out the units because I know that they're all consistent, meaning I have meters and seconds and seconds. So I can just plug it all in. So the initial velocity here was 0. The acceleration is what I'm looking for, and my time value is now 3.90. So let's just simply now calculate. So this is going to be 3.90a, just reorganizing it a little bit, and then you got to divide that out, right? 3.90. Okay, so the acceleration now should be, take out your calculator, and it's going to be 26.8 divided by 3.9. So it comes out to 6.87. So 6.87, I'm going to have three significant figures in my answer, and this should be meters per second squared. Okay. I know that because my displacement value in the problem was meters, and the time value was in seconds. Okay, so that's part A. Let's take a look now at part B. It says, how far does it travel in that time? So what they're asking here is, in terms of how far, they're asking us to find the displacement, or x. Okay, so now what we would want to do is let's consider, do we know any formulas that involve, I would choose these three variables again, and this one. The reason why I'm not going to look for a formula that includes acceleration is because, well, maybe it might not be possible to do so, but maybe I made a mistake in my calculation here, and I don't want the mistake to propagate into part B. So I noticed that the last formula here, right, number 5, right, essentially has all the pieces I need. So now this is part B. Let's rewrite the formula. So we got the change in displacement is equal to 1/2 times the initial velocity plus the final velocity multiplied by time. So let's just now plug in the values. The initial velocity was 0. My final velocity was 26.8. And the time again was 3.90 seconds. So now just doing the math, cleaning it up, it's going to be 1/2. Obviously 0 plus 26.8. It would be 26.8. And times 3.90. Okay, so let's just take out the calculator now, and let's plug in these values. So we got 0.5 times 26.8 times 3.9, and that works out to a value of 52.26, but I'm going to write down 52.3 because of significant figures, and this is in meters. Okay, this value has 3 sig figs, that value has 3 sig figs, therefore my answer has to have 3 sig figs. Okay, and that would be the displacement. Number 29. Freight trains can produce only relatively small accelerations and decelerations. What is the final velocity of a freight train that accelerates at a rate of 0.05 meters per second squared for 8 minutes, starting with an initial velocity of 4 meters per second? Okay, so let's just draw a sketch of this. Okay, so we have a train here. Oops, wrong button. So we have a little train. So, choo-choo. Okay, that's as good as the jokes are going to get. So now it is moving and accelerating, right? So it says that it's accelerating at a rate of 0.05 meters per second squared. So let's write that here. So the acceleration is 0.0500 meters per second squared. And it says it accelerates at this particular rate for 8 minutes. Okay, so this timeline here is going to be 8 minutes. So that's my t value. Okay, and it says it starts from an initial velocity of 4 meters per second. Okay, so I'll consider the beginning case right here, right at the front of the train, let's just call it. Doesn't matter, could be to the middle. But the initial velocity is going to be 4.00 meters per second. Okay, and the question is finally asking me, right, what is the final velocity? So when the train reaches this point in yellow. So I want to know what the final velocity is. Okay, so first thing I'm going to do before I think about formulas is I want to look at my units, right? And I notice one problem. I have seconds in the velocity, I have seconds in the acceleration, but I have minutes in time. No good. Okay, they all have to be consistent. So I suggest converting the 8 minutes into seconds. That probably would be the easiest way to go about this. So let's do the calculation over here on the left. So we're going to do 8 minutes and convert that into seconds. So let's write down what we're given. 8 minutes. The minutes go on the bottom. Seconds on the top. 60 seconds. Whoop. 60 seconds in 1 minute. Minutes will cancel. And now just do the math here. Right. So this comes out to 480 seconds. Okay, great. So I'm just going to write that on the top here. 480 seconds. All right, now I'm good to go. I noticed that my distance values, the displacements would be a better term here, are both in meters, so that's fine. All right, so now what I want to do is I want to find an equation that relates these variables: time, acceleration, initial velocity, and final velocity. So take a look at the upper right-hand corner, and it appears to be, if you scroll through all of them, it appears to be the first one would be the best candidate. So let's rewrite that. I'm going to write letter A here. Actually, let me do it beneath. So letter A I'll put on the bottom. So we got the final velocity is equal to the initial velocity plus the acceleration multiplied by time. So the final velocity is what I'm looking for. The initial velocity, the problem told me, was 4.00. Going to leave the units out just to make everything nice and simple. The acceleration was 480. And the time value, oh, excuse me. Whoops. It wouldn't have mattered in terms of the math, but let's just be consistent here. The acceleration is 0.0500, and then the time value was 480 seconds. Okay, so now let's just plug it into the calculator. So we got 0.05 multiplied by 480, and we can take this in pieces, right? So let's just write, so 4.00 plus, now we're going to add these values together. And this number has 3 sig figs. This number has 3 sig figs. Let me just go back and check. Yeah, it should. I should place a decimal in there because the 8 minutes that they actually gave me, if you go back to the problem, that had 3 significant figures. All right. So really, if I should have right here, okay, I should have made that really 8.00. And then the value of 8 here and here should have also been 8.00. It won't make a difference in terms of the math, but it will make a difference in terms of significant figures, and that may slightly change your answer, depending upon how particular your professor or teacher is. So in any case, when I do this math, coming back, when I do the math there, I find a value, I get a value of 24, and I'll put a decimal there, and it should be 24.0 because I need 3 significant figures. Okay. Now, when I add these two values together, I'm going to get a value of 28. But my answer should be 28.0. Why? Because this number right here only goes out to the hundredths place, and this value goes out to the tenths place. I got to choose the one with the least places, so therefore it only goes out to the tenths. So this will be the value in meters per second. That is the final velocity. Okay. So now let's move forward. So now let's take a look at letter B. All right, so it says, let me just change the color here. So it says, if the train can slow down, okay, at a rate of 0.550 meters per second squared, how long will it take to come to a stop from this velocity? All right, so let's see what's happening. So what I'm going to do here in gold is I'm going to continue out this diagram, okay? And what it's saying, so again, I'm just going to actually erase this question mark now because I do know what my final velocity is. The final velocity should be 28.0 meters per second. And that's the final velocity in reference to the part in black. Okay. So now this not new point, but this point now in terms of the gold frame becomes my initial velocity. Okay. So in terms of my frame in gold here, That's the initial velocity. It would be the same value, 28.0 meters per second. It also says that if the train can slow down at a rate of 0.550 meters per second, what that implies, anytime it's slowing down, that means the acceleration is negative. All right? So when I write my acceleration value here, I'm going to write a negative 0.550 meters per second squared because it is slowing down. All right, and now it wants to know how long this is going to take. So I'm looking for my time here. Okay, how long this is going to take to finally come to a stop. So that means at this particular point out here, the final velocity of the frame in gold is going to be 0 meters per second. All right. So what I'll do here, just so we don't get too confused, I'm actually just going to erase this, and I'm just going to change the color here, okay, to red. So I said at this point, the first part of the problem, right, this was the final velocity, and that had a value of 28.0 meters per second. Okay, so now what we want to do is let's think of an equation that relates these variables together. The initial velocity, the time, the acceleration, and then the final velocity. And oh wait, it's the same equation again, right? The same one that we used in letter A. So for letter B here, for part B, we're going to use the final velocity is equal to the initial velocity plus the acceleration multiplied by time. The final velocity in this problem is 0. The initial is going to be 28.0. The acceleration now is a negative 0.550. And I'm looking for the time. Okay, so basically what I'm going to do is I'm going to, this is really a subtracted term, right, after I actually distribute the negative. And so what I'm going to do is I'm going to then add this. I'll be able to add the term 0. I'm just combining a step or two here in one part. So this whole thing cancels. I'm going to add that to the other side, 550t. And now what's going to happen is I get 0.550t is equal to 28.0. Now just divide out the 0.550. Great. Now divide out the 0.550. And now my time becomes, so take out your calculator, do 28 divided by 0.55. All right. And the value comes out to be, and we're going to have 3 significant figures. So it looks like it comes out to about 50.9 seconds. All right, so that will be the time it takes. So if the train can slow down to, at the rate of 0.55 meters per second, it'll take 50.9 seconds, almost a minute, to come to a stop. Okay, so now letter C is now asking us how far will it travel in each case. All right, so I guess what they mean is that there's really 2 parts to this problem, right? The frame in black, I'm just starring my picture. The frame in black, right, and my frame in gold. So it sounds like it wants me to calculate the distances or the displacements in each case. So let me first do the first case in black. Right, so this is part C, and I'll keep the writing in black. So I need to now find the displacement. So what I need to do again is I need to find a relationship between all my variables, right? So we really have a lot of the variables. We know a lot of them. So there's a bunch of formulas we can choose. Why don't we choose the second one? All right, let's use this formula here. All right. So displacement will equal the initial velocity multiplied by time plus half of the acceleration multiplied by time squared. Okay. So the displacement for the part in black is going to be the initial velocity of 4.00 multiplied by my time value, which was 480 seconds, right? Plus 1/2 of my acceleration, which was mentioned in that part of the problem was 0.0500. And I'm just running out of space. I'm going to put it right underneath. And now multiplied by my time value squared. So 480 squared. Okay. So I'm going to do this in pieces. I'm going to do the math here first. Okay. So that will be 4 times 480. Works out to be 1920. Okay. Now I need to have 3 significant figures. So I'm going to do, I'll do 1920 without the decimal. That makes it 3 significant figures. And then plus now, let's do the math for the second part. So it's 1/2 times 0.05 times 480, and that's squared. Okay, so I get a value of 5,760. And again, it looks like I'm going to have three significant figures, so let's just leave it at that. So 5,760. Okay, wonderful. And now to find the displacement, I would just simply add these two together. So take the 1920 and then add the 5,760. So now we get a total of 7,680 without the decimal point. That's in meters, and that would be the final answer with the correct number of significant figures. All right. So now, part C for the part in gold. So guess what we're going to do? We're going to do the same thing. All right, same formula we can use. We know all the pieces to that puzzle. I mean, you could choose a different formula if you like. I'm just seeing if maybe there's a faster way to do it. You know what? In case I made a mistake here, all right, with my time value in part B, why don't we choose this formula? All right, number 4. Reason being is because, again, if I made a mistake in calculating my time, I don't want the mistake to propagate into the last step here. All right, so let's write down the equation. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So what's the final velocity in the gold frame? Well, it's 0. So it's just 0 squared. What's the initial velocity? What's 28.0? And I realized that, hey, I had to use my answer from part A anyway, right? Because I calculated that. So, all right, I wasn't able to I might not be able to minimize my chance of error here, but it's always a good thing to think about. So multiply by 2 times my acceleration, and they told me that the acceleration is negative 0.5. Actually, you know what? Just running out of a little space. Let me just condense this a little bit. So it's 2 times 0.550, and that's multiplied then by x. Okay, so let's do some math here. So let's find, and by the way, this value here in terms of the acceleration is negative. Okay, so that's a little negative sign above it. So we have, let's take 28 and square it. So that gives us 784. So we got 0 is equal to 784. Now this is going to be minus, right? 2 times 0.55. That's pretty easy math here. So minus 1.10, because I need 3 sig figs, and that's x. So now simply just add the x on over, so 1.10 to both sides. X. That cancels that term, so that's 1.10x is equal to 784. And finally now divide out the 1.10. And this is a long problem, right? So let me write my x value here. X is going to equal 784 divided by 1.1. And it comes out to about 713, considering the sig figs. So 713 meters. I'll just write that up here. So x here in the gold part will be 713 meters. And then the part in black that we just calculated was 7,000. So x. So the x part here was going to be 7,680 meters. Okay, great. Number 30. A firework shell is accelerated from rest to a velocity of 65.0 meters per second over a distance of 0.25 meters. How long did the acceleration last? All right, so let's just draw a quick picture here. Here I have a rocket or a firework, all right, and it's going to travel upwards, right? It's going to start at rest, so the starting point here, the initial velocity is going to be 0 meters per second. It says it goes from rest to a velocity of 65.0, so I know that the point up here must be the final velocity, and that's going to be 65.0 meters per second. And it covers a distance, right? So this total distance it covers is going to be 0.250 meters. Okay, now it wants to know how long. So basically we're solving for time, right? So we want to know time. Okay, let's think of a formula that may relate these these four variables together. Displacement, final velocity, initial velocity, and time. And if we go over to the right-hand side, looks like the last equation will suffice. So, letter A, write down change in displacement is equal to 1/2 times the initial velocity plus the final velocity multiplied by time. So the displacement they told us was going to be 0.250. It's 1/2 then times the initial velocity, which is 0, plus the final velocity, which is 65.0, multiplied now by my variable t. So let's just clean things up a little bit. So this is 0.250, and it's now, right, 65 plus 0 is 0, right? And then just use your calculator if you need. 0.5 multiplied by 65, that should come out to 32.5. So we have a value of 32.5. And again, I'm consistent 3 significant figures here because that number has 3 significant figures. And that's still multiplied by time. To solve for t now, we got to, right, divide out the 32.5. And now t will become, so let's take 0.25 divided by 32.5. And I'm going to convert it into scientific notation. We need 3 significant figures. So it's going to be 7.69 times 10 to the minus, looks like 3 seconds. So that's quite fast. All right. It's about almost 100th of a second. Okay. So great. We did that part. Now for part B, it says calculate the acceleration. Okay. So now I want to know the acceleration. And we just found the time, so I'll just plug it in here. Right, instead of the question mark, I can now get rid of that question mark and now write in the 7.69 times 10 to the minus 3. And that's in seconds. Okay, great. So now quickly thinking about the acceleration, I'll do that part B on the right-hand side. Do we know an equation set that can relate the variables that I know now? Usually what I'm still going to try to choose, the original variables because I don't. So the final velocity, the displacement, and the initial velocity. If I can't relate that to acceleration, it looks like I can do that through the fourth equation, right? If I couldn't do that, I would then look for an equation that involved time, but I prefer not to do that because in case I made a mistake in calculating the time, I don't want that error to propagate into part B. Okay. So let's write down the formula. So the final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration times the displacement. It's a lot to say. It's a mouthful. So the final velocity of this firework is going to be 65.0, and that's squared. The initial velocity was 0 because it started at rest. Now it's going to be plus 2 multiplied by my acceleration, which is what I'm trying to find, then multiplied by the displacement, right, which was 0.250. Okay, so now let's do some math. So take 65 and square it. So this comes in, again, I need 3 significant figures, so I'm just going to convert it into scientific notation. So it's going to be 4.23 times 10 to the third. And that will equal now 2 times, 0.250, right? So that should just be 0.5. So this would be 0.500, 3 significant figures, A. So divide out the 0.500, divide out the 0.500. So this should be fairly straightforward. So 423, essentially divided by 5 is just multiplied by 2. So just simply be 8.46, looks like a G, 8.46 times 10 to the third meters per second squared. And that would now be the acceleration. Number 31. A swan on a lake gets airborne by flapping its wings and running on top of the water. If the swan must reach a velocity of 6 meters per second to take off, and it accelerates from rest at an average rate of 0.35 meters per second squared, how far will it travel before becoming airborne? All right, so let's sketch a quick picture here. So let this dot represent the swan, and the swan is going to have to accelerate some distance. And it says that the acceleration of the swan is going to be equal to 0.350 meters per second squared. It's going to also travel, right, some distance from the start point all the way to the end point. That's actually what it's asking us to calculate, right? We're trying to calculate the displacement here. It also says that it starts from rest. So we know that the velocity at the start here, the initial velocity that is going to equal 0 meters per second. And we know that in order for it to finally take off, the velocity must be at the end 6 meters per second, right? So the final velocity here is going to be 6.00 meters per second. Now, taking this information, right, knowing the initial velocity, the acceleration, the final velocity, can we calculate the displacement? So take a look at formula number 4 on the right-hand side. This one right here in the box. That relates all 4 of the variables together. So we should be able to use that to calculate the displacement. So let's write it down. So we have the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is 6.00. Okay, that's squared. The initial velocity was 0, and that's squared, plus 2 times the acceleration, which is 0.350. And now my displacement, which is x. So let's do the math. 6 squared is going to be 36. 0.0 because I need 3 sig figs. And then it's 2 times 0.350. So that's simply going to be 0.700, and that's x, right, times x. And then divide out the 0.700 from both sides. So my displacement here should be, let's take out the calculator. So it's 36 divided by 0.7. So it comes out to about 51.4. So we got 51.4 meters. Okay, so that's how far this swan is going to have to travel before it can get airborne. So that was part A. Now let's take a look at part B. It says now how long does this take? So what we're doing now is we're going to solve for time. Okay, so again, I can use, now I know the displacement, so I can use a whole bunch of formulas, but I'd still like to use formulas that involve the initial, the final, and the acceleration since they were given. Right? Maybe I made a mistake in copying them, but I think that's pretty unlikely. Whereas if I use displacement now, you know, I had to do some calculations. Maybe I made an error. I don't want those I don't want that error to propagate into my next answer. So what I'm going to try to do is choose a formula between initial velocity, acceleration, final velocity, and time. And if you realize it's the first equation on the top, that relates all 4 of those variables. So let's do that. So the final velocity is equal to the initial velocity plus the acceleration times time. The final velocity was 6 meters per second. The initial velocity was 0. The acceleration was 0.350. And now we're looking for t. So just simplifying this, right, it's 0.350 t. Divide out now the 0.350 from both sides. 350. And now we get the time is equal to, so 6 divided by 0.35 works out to be 17.1, right, 17.1, and that'll be in seconds. And that will be the time it takes for the swan to go from 0 meters per second to 6 meters per second, accelerating at a value of 0.350. Number 32, a professional application. A woodpecker's brain is specially protected from large decelerations by tendon-like attachments inside the skull. While pecking on a tree, the woodpecker's head comes to a stop from an initial velocity of 0.6 meters per second in only a distance of 2 millimeters. Find the acceleration in meters per second squared and in multiples of g. Okay, so let's have a quick sketch. So here's, I guess, the woodpecker's head. All right, and it's moving at some initial velocity. I'll say it's moving to the right. Okay, it's going to be pecking a tree, I guess. And it says that the initial velocity here of the head at the beginning is going to be a value of 0.600 meters per second, right? And it comes to then a stop, right? So it's going to stop at the end here. So the final velocity is going to be 0 meters per second. And it goes from this velocity of 0.6 to 0 in a distance, as it mentioned, of 2 millimeters. So this distance here is going to be 2.00 millimeters. Great, and that would be my x value. Okay, so now it says find the acceleration. So we're looking then for a, right? So what I want to do is I need to now think about one of the equations of kinematics. And I'm thinking about, do I know a relationship between the displacement, the initial velocity, the final velocity, and the acceleration? And we do, right? If we use this equation, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement, blah. That will give us, right, the acceleration by knowing these 3 variables. Okay, great. So we have that. All right. Now, the only thing, though, I realize is that here in my velocity, I have meters and meters, and they gave me the distance in millimeters. So no good. I have to do a conversion. I want to convert my millimeter value into meters. So let's do that on the right-hand side over here. So we've got 2.00 millimeters. I'm going to put millimeters on the bottom, meters on the top. And I know that for every 1 meter, there's 1,000 millimeters. So that cancels. Right, so now the value will be, so just plug it into the calculator. It should work out to be a value of 0.00200 m. Okay, I still have to have 3 significant figures. All right, so now this is the, not new distance, but that's the distance value I'm going to use. So let me just write that above here. X will equal 0.00200 m. Okay, now let's plug in everything into our formula. So the final velocity is 0. The initial velocity is 0.600, and that's squared. And now that's going to be plus 2 times my acceleration, which is what I'm trying to solve for, times the displacement, which was 0.00200. Okay, now let's calculate. So let's do some math. So 0 squared is 0. 0.600 squared is going to be 0.360. I got to have 3 significant figures there. And then doing the multiplication, 2 times 0.002 should be 0.00400 a. Now let's subtract this value on over. Okay, minus 0.00400 a. That cancels. Now I'm left with negative 0.00400 a is equal to 0.360. And now divide out the negative 0.00400 on from both sides. And now that leaves me with an a value of, take out the calculator, 0.36 divided by 0.004. And it works out to about 90. And this is negative, right? Don't forget that negative sign. And this will work out to a value of negative 90. And I have to have, again, I have to have 3 significant figures here. So negative 90.0. meters per second squared. Okay, great. So that is my answer for part A in terms of the acceleration. It should be negative. The reason why is because if the bird's head is moving to the right but it's slowing down, there must be an opposing force in the other direction that has an acceleration. And we know accelerations that move in the left-hand direction are negative. All right? So that takes care of that. And now it also asks us to calculate this in multiples of g. So let me do this over here on the right-hand side. So just remember this formula that g is equal to a over 9.80. The only thing you have to remember is that the units of a must be meters per second squared in order to use this, which they are. That's how I solve for it. So g will then be equal to negative 90.0 over 9.80. And now my value will be, just divide out the 9.8. So that comes out to negative 9.18 g. Okay, so that would be the value in g. All right, so part A is finished. Let's take a look at part B. So now it says calculate the stopping time. Right, so now what it wants me to do back to my picture, wants me to calculate the time that it took in order for the bird to have its head go from this velocity to 0. Okay, so again, I'm going to think of a formula. that relates my givens, right? So I'm going to be looking for a formula that relates initial velocity, final velocity, time, and displacement. Okay. So what should we use, right? Well, this formula may come to mind, that the change in displacement is equal to 1/2 times the initial velocity plus the final velocity multiplied by time. All right, you could have chosen other equations, by the way, but you would have had to have used the acceleration. Okay, the only problem with that is that if you calculated your acceleration wrong, and then you used a formula that involves that acceleration, now you're doubly wrong. All right, so just try to avoid that. I could still make a mistake in copying my information from the problem, but it's less likely. All right, so remember, you're doing this to do well on a test. So minimize the chance for error so you can do better on the test. All right, so my change in displacement, they said, was going to be 0.00200. I'm using that in meters. Is equal to 1/2 multiplied by the initial velocity, which they said was 0.600. My final velocity was 0, and now I want to solve for the time. So just some simple math here. Let's just rewrite that. So half of 0.6, right, should be 0.300 times t. Looks like a weird t. Okay. And then divide out the 0.300. Great. And that's going to give me now my time. So 0.002 divided by 0.3. And it comes out to, and I'm going to convert this into scientific notation, this should be now 6.67 times 10 to the minus 123, it looks like. And that is in seconds, all right? So I need 3 significant figures there again because I divided these values with 3 significant figures. All right, so that takes care of B. So now, last but not least, let's take a look at letter C. So it says the tendons cradling the brain stretch, making its stopping distance 4.5 millimeters greater than the head, and hence less deceleration of the brain. So what is the brain's deceleration expressed in what is the brain's deceleration and expressed in multiples of g? Okay, so honestly, the wording of this question is a little odd. Greater than the head. I don't quite understand how exactly they're telling me this distance. All right. So I'm going to make one assumption that basically the new stopping or the new distance in the problem from the head. So let's take a look back at the picture. So from the head, now it's going to travel out to here, let's say. Okay, so this distance now that was covered, the displacement value is now going to be 4.5 millimeters. Okay, so I'm just going to convert that right to meters, 0.00450. Okay, the other way to have interpreted that may have been to say, well, it's going to be an additional 4.5 millimeters from the end point of the first problem. That's possible, but that just sounds a little crazier to me. But again, it might just be my interpretation, or maybe my brain is a little fried at the moment. But in any case, assuming that this is how they're meaning for me to interpret the distance, I will be correct though in my calculations moving forward by using this particular displacement. Okay. So now, again, they want us to calculate the deceleration. So basically now, I'm going to be using the same formula as I did in letter A. Right, so A's work was here in red. All right, so now let me actually do all the work here for letter C in black. So I'm going to just box in that displacement. So I'll put letter C on down here in black. Okay, so we're basically using the same formula. So the final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration multiplied by the displacement. So the final velocity is still 0 because the head is still coming to a stop. The initial velocity is still the same, so 0.600 squared. Plus then 2 multiplied by the acceleration, which is what we're trying to find. And now the displacement is the value that changes. So this is 0.00450. That's the value that changes when you go back to part A. That other value in terms of the displacement was 0.002. So now we made it a little longer. So obviously the acceleration should go down, right? So let's make sure that it does. So now just doing some math here, right? 0.6 squared is going to be the same, 0.360, plus then 2 times the value of 0.0045 should be 0.00900. Reorganizing this equation now, it should work out to be negative, right? Because I'm going to move this to the other side of the equation. All right, so it should be now negative 0.00900A, and that's equal to 0.360. Okay, I don't know why I just noticed I wrote in the squared sign over here. It's not squared anymore, just going to erase that. So now what we can do is simply divide out the negative 0.00900 from both sides. 0.00900. And let's take that and put it into the calculator. So 0.36 divided by 0.009 works out to now be 40, negative 40 that is, negative 40 meters per second squared. Okay, and that is what I anticipated should happen. Look, when the distance was shorter, the acceleration was negative 90. Now when the distance was lengthened, essentially as a result of these tendons that are able to stretch, we more than decreased the acceleration by half. So that's a good thing. Now it just wanted us to finish this out in terms of g. So remember, g is equal to a over 9.80. So g will equal negative 40. And I technically should have, this should be point. And let me just make sure I'm technically correct here. Let me just erase this a little bit. And this should be 40.0. because I need 3 significant figures. All right? So this is over 9.8. And finally now, man, this problem's a long one, huh? So negative 40 divided by 9.8 is going to be negative 4.08 G. Okay, that takes care of that. Number 33. An unwary football player collides with a padded goalpost while running at a velocity of 7.5 meters per second and comes to a full stop after compressing the padding and his body by 0.35 meters. What is his deceleration? All right, so let's draw this unwary football player. And look at that. Not too bad. Oh, well, I could make it a little better. There we go. Big biceps. Okay, so now he's traveling, right, at a certain velocity, it says. Okay, so let's draw this little arrow. And initially it says that he's moving at a velocity of 7.50 meters per second. And eventually he's going to come in contact, right, with this padding, okay, that's essentially going to be compressed. So basically he's going to hit the padding about here, okay, but then the padding essentially will be compressed between him and his body. So therefore I'm just going to enlarge in the picture here, and now here's the padding. Okay. So the distance then that he traveled here will be 0.35 meters. So let me just change the color slightly. So the distance here, or the displacement, right, is going to be x is equal to 0.350 meters. Okay, great. And it tells us, right, finally he comes to a stop. So that's another piece. So at the end, this is the final. It's 0 meters per second. So now what we have to do is we have to calculate his deceleration, or in other words, we have to calculate his acceleration, right? And it should work out to be negative. So let's see. Think of a formula. Let's see if we can find a formula that relates these 4 variables on the screen. And it looks like the 4th equation will be that particular formula. So let's write it down. So the final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration and then multiplied by the displacement. So the final velocity is 0. That's easy. Initial velocity is 7.50, and that's squared. 2 times now my acceleration, which is what I'm trying to find, and my displacement here is going to be 0.350 meters. Okay, I have consistency in all the units over here, so I don't need to do any conversions or anything like that. And I know my acceleration unit should be then in meters per second squared. Okay, I'm just not putting them in to make it, cleaner. So we have 0 is equal to now, so take out the calculator, 7.5 squared. Comes out to about 56.25, but we need 3 significant figures, so it's going to be 56.3. Plus then 2 times 0.35, right? So that should be 0.700a. Okay, subtract this on over to the other side. 0.700a minus 0.700a. Cancels on that side, so now we have negative 0.700a is equal to 56.3. Great, now divide this out. Negative 0.700. So now my a value should be 56.3 divided by 0.7. So that works out to be approximately negative 80.4. Okay, 80.4 meters per second squared. All right. So remember 3 significant figures because I divided 2 numbers that each had 3 significant figures. So that's part A. Let's take a look at part B. So now it says how long does the collision last? So now I'm looking for time, right? So we can use a whole bunch of formulas to figure this out, but what I'm going to focus on is find a formula that relates the initial velocity, the displacement, the time, and the final velocity. The reason why I'm not going to use my acceleration in this calculation, or try not to if I can, is because maybe I made a mistake here. I don't want the mistake to now propagate into my time calculation. Because like I have said plenty of times before, now we're going to be doubly wrong. All right? So it looks like if I look over to the right-hand side, it looks like the last equation would work really well. So let's write it out. Change in displacement is equal to 1/2 of the initial velocity plus the final velocity multiplied by time. The displacement in the problem is 0.350, and it's then 1/2. The initial velocity was 7.50, the final was 0, and now I just got to solve for time. Okay, so this is 0.350. So 1/2 of 750, just take it out and plug it into the calculator. So 3.75. Again, I need 3 significant figures there, multiplied by t. Now just divide out the 3.75. And the t now will be, so 0.35 divided by 3.75. So it looks like it works out to be about, what is this? So we need 3 significant figures, so 0.0933 seconds. Okay, great. So it comes out to about 1/10 of a second. All right. Sounds reasonable. I think everything looks good. Number 34. In World War II, there were several reported cases of airmen who jumped from their flaming airplanes with no parachute to escape certain death. Some fell about 2,000 feet or 6,000 meters, 20,000 feet, or 6,000 meters, and some of them survived with few life-threatening injuries. For these lucky pilots, the tree branches and snowdrifts on the ground allowed their deceleration to be relatively small. If we assume that a pilot's speed upon impact was 103 miles per hour or 54 meters per second, then what was his deceleration? Assume that the trees and the snow stopped him over a distance of 3 meters. Okay, so just draw a picture. We have an unfortunate situation of someone falling out of an airplane, right? So they're traveling down. And it says that the distance that they would have fallen, let me just see. If we assume the pilot's speed upon impact, yes, okay. So let's take this as the point of impact, actually. So once they impacted the snow, and let's say everything beneath here, right, is snow, okay? At the point of impact here, they were traveling with a speed, I'll call this the initial speed, of 54 meters per second. Okay. Now, I really should make this negative because it's in the downward direction. I don't have to really for this problem. It's all going to work out. But I'm going to do it anyway, okay? Just so we can see that it's proper to do so and we should get the right values. Okay. So now, So now if he's falling, great, so we got that. All right, so assume the trees and snow stopped him over a distance of 3 meters. So that means that from here, right, all the way down, the displacement value is going to be 3 meters. Okay, wonderful. And that's really all that they give us, right? We also know that he came to a stop, right, at the bottom here. So we know that the final velocity should have been 0 meters per second. Also, in thinking about using proper signs, I have to make the 3 meters negative, right? Because the starting point is at the top, and then it's traveling downward. Okay, so I should have everything I need, and now it says what was his deceleration. So we are looking for A, right? Because we're looking for acceleration. All right. So now, is there a formula that relates these three variables to one another? The initial velocity, the displacement, the final velocity, and acceleration. And there is, right? If we notice, it's the fourth one. So let's write that down. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity here is 0. Right? The initial velocity is negative 54 squared. Plus then 2 times the acceleration, which is what we're looking for, and then the displacement was negative 3 meters. I left out the units because I know I'm consistent. I got seconds and meters. Okay, so I know my acceleration will come out to be meters per second squared. So type into the calculator negative 54 squared. Okay, so we got negative now. And what was it? Yeah, so I got to use 2 sig figs. So negative 2900. Okay, plus then 2 times negative 3. And this should have been 2 significant figures because we're really 3.0. So just add that over there a little bit. So now it should be plus a negative 6.0 A. Okay, so now let's add this on over to the other side, right? So we got 6.0 A, and now 6.0 A, and that cancels. So we got 6.0 A is equal to, and here's the thing, I don't know why I put a negative here, because when you square it, right, it becomes positive. So that was just a silly oversight on my part. So let me just erase that. Apologies. And now let's come back down to, so 2900 here. And let's divide out now the 6.0. 6.0. So I should have 2 significant figures. So my acceleration here, 2900 divided by 6. So it comes out to about 480. Okay, 480 meters per second squared. Okay, great. So that is the acceleration. Now, you might say, well, wait a minute, why isn't that negative? I thought it's decelerating. So why is it not negative? Well, it is decelerating, but the thing is the acceleration actually of the object is pointing upwards, right? Since the object, since unfortunately the individual is he's traveling downwards. So in order to slow the travel downwards, there has to be an opposing force pointing upwards. Okay? So, and that opposing force is essentially related to the acceleration. So notice that the actual acceleration is pointing in the positive y direction, and therefore the acceleration should be positive. See, so technically speaking, the answer here has to be a positive value. Now, if you don't put in the negative values, like the initial velocity and the displacement, like I did in the beginning here and here, your answer will come out to be negative. Now, technically that's wrong because of the way the object is traveling. He's moving down. Okay? So, I don't know how particular your professor or your teacher is going to be. They might accept both and it might not be a big deal, but it really should be positive in this case if we consider the actual physics of it and how the object is moving in the negative y direction. Number 35. Consider a gray squirrel falling out of a tree to the ground. A. If we ignore air resistance in this case, only for the sake of this problem, determine the squirrel's velocity just before hitting the ground, assuming it fell from a height of 3 meters. Okay, so let's draw a little picture. This dot will represent the squirrel, and unfortunately the squirrel finds itself in a position where it is falling. So it says that we want to determine the velocity just before it hits the ground, so let's just assume that this is the ground over here. Okay, so it wants us to determine the velocity right here. So I would assume that that would be a final velocity. And it falls out of a tree, right? So therefore, it probably wasn't moving at the moment. So that means the initial velocity here is 0. I'll just put this in meters per second. And it says that it fell from a height of 3 meters, right? So the distance, or the displacement from here on down, is going to be 3 meters. Now I'm going to call it negative 3 meters. Okay? The reason why is because the problem we're talking about an object, in this case the squirrel, moving down in the negative y direction. Therefore, my velocity should be negative, my displacement should be negative. That also means, though, that my acceleration would actually be positive because it would be pointing in the opposite direction. All right, so just keep that all in mind. All right, so, okay, so that's basically all it gives us. And now, meaning, when I say acceleration, I'm talking about if there is a force, right, after it hits the ground and it starts slowing down, there's a force that is pointing up. I don't mean that all the accelerations in the problem are negative, positive, because we do have the force of gravity in this problem. Right? And the gravitational acceleration is always negative because it's pointing down. All right? So let's take a look. So we actually also do know that in addition, right? Because this is a free fall problem. So the acceleration due to gravity, that is always going to be negative 9.80 meters per second squared. All right? All right. So let's see, do we have enough information to solve the problem? So what we need to know is we need to look for a formula that relates to final velocity, the initial velocity, the acceleration, and displacement. And it looks like we do, right? If we go over to the right-hand side, it looks like the fourth formula here will work out nicely. So let's calculate that letter A down here. So the final velocity squared should be equal to now the initial velocity squared, plus 2 times the acceleration multiplied by the displacement. Okay, so the final velocity squared, right? We don't know we're looking for the final velocity. So the initial was 0, so that's simple. 2 multiplied by the acceleration, and the acceleration in this problem is due to gravity, right? Because the object is in free fall, so that's why it's negative 9.80. And the displacement it traveled was negative 3 meters. Okay. And by the way, let me just be careful. This is 3.0. I got to make sure just for significant figure purposes. All right. That means I'm just going to alter this slightly on up here. Okay. And I'll put this as 0.0 meters. All right. So let's do some math. So the final velocity squared should be equal to now, let's turn on the calculator, 2 times negative 9.8 times negative 3. And that works out to be 58.8, but I can only have 2 significant figures in my answer. All right, so it's going to leave me with 59. Okay, so that works out well. And then to solve now for VF, we would have to take the square root of both sides because I got to get rid of the square. All right, so when I do so, let's plug that in. All right, and now it becomes radical of 59. And it becomes 7.68, right? But I have to round to 2 sig figs, so it's going to be 7.7. All right? And this is meters per second. Now, technically, when you take the square root, the answer could either be positive or negative. So really, that's the technical answer, plus or minus, all right, 7.7. But now the thing is, only one of those, in the context of this problem, given the direction in which the object is moving, only one of these signs, the positive or negative, will be the correct answer. And since it's traveling downward in the negative y direction, we would have to give the negative answer. All right? So the final velocity here is going to be negative 7.7 meters per second. That's the answer. Okay, so that's part A. Now let's take a read over part B. If the squirrel stops in a distance of 2.0 centimeters through bending its limbs, compare its deceleration with that of the airman in the previous problem. Okay. So basically what's happening now is we're really focusing in now, if you guys look back at the picture, we're focusing in now on this particular area when the squirrel is just hitting the ground. Okay, so I'm essentially going to blow this up and zoom in on that particular area. All right. So now the squirrel is essentially hitting the earth here, okay, with a velocity, as we just calculated, of negative 7.7 meters per second. Right, so the velocity right here is going to be the initial velocity. Okay, now the final velocity of letter A becomes the initial velocity of letter B, because I know that I want to calculate the stopping time when it actually makes contact with the Earth. Okay, so the initial velocity here is going to be negative 7.7 meters per second. So make sure you understand that point, because it's an important point in terms of framing the problem. Initial velocities, final velocities, they're just relative. They're just relative to what the frame of the problem is. So our initial velocity is negative 7.7. When it finally comes to a stop, right, final velocity is going to be 0 meters per second. And it says that the distance that it covers here by bending its little legs, okay, is going to be 2.0 centimeters. 2.0 centimeters. Okay. So it wants now us to calculate the deceleration. Okay. Now this should be the positive acceleration, and you'll see how that should work out, because since it's stopping, there must be a force facing upward. Okay. So first thing I notice, I need consistency in my units. I have centimeters in the displacement, but meters and meters in my velocities. So I have to do a conversion first. So let's convert the 2 centimeters into meters. So centimeters on the bottom, meters on the top. For every 1 meter, there's 100 centimeters. And we can just do our conversion nicely now. So 0.020 meters. Great. So I'm just going to write that up here. X is equal to 0.020 meters. Okay. So now I can do my calculations. All right. So I need to consider a formula, right? We're trying to find A. So consider a formula that relates displacement, acceleration, initial and final velocities. And oh wait, it's the same exact equation we just used. Right? So final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration multiplied by the displacement. So now the final velocity is 0. Right? The initial velocity is negative 7.7. That's going to be squared. Plus 2 multiplied by my acceleration, which is what I'm trying to find. And now the displacement over which this acceleration occurred is going to be 0.020. That's the value that we just calculated. So let's do some math. Right, so 7.7 squared comes out to 59.29. All right, so 0 squared, I don't have to plug that in, right? So negative 7.7 squared came out to 59.29, but I need only 2 significant figures, so therefore it needs to be 59. Okay, plus 2 times the acceleration multiplied by 0.02. So this should work out to 0.040 A. Okay. Let's now move the... let me just fix that A a little bit. So let's now move the... I almost forgot one thing here, right? And that's why my signs would have been off. So I'm thinking, I know the acceleration has to be positive, but I'm just thinking forward, and my acceleration is going to come out to be negative. What did I forget? Well, I forgot that when I plug in my displacement here, it has to be negative. Okay, why? Because again, the squirrel is still traveling downwards, right? It's still going in the negative y direction. So I need a big old negative there. Okay, not going to make a big deal, but it will make a big deal in terms of the signs in the problem. All right, I'll get the right magnitude, but I just won't get the right sign. So that should be negative there. Now let's add the acceleration on over, 0.040 A. That cancels. So this is 0.040 A is equal to 59. And divide this out now. 0.040. So A is 59 divided by 0.040. 2 significant figures, right? So now my acceleration will be all round. It's going to be 1.5, right, times 10 to the 2. Times 10 to the 3. Silly mistake. And that's meters per second squared. So that's the acceleration of the squirrel. Now it says compare that with the deceleration of the airman in the previous problem. So let's just flip back to the previous problem. Here it is. And the deceleration now of the airman was 480 meters per second squared. So the squirrel's deceleration is almost 3 times greater than the airman's. It's kind of crazy if you think about it, right? The airman, right? If you go back to the prior video, you'll see it all worked out. But that airman fell. What was the distance? 6,000 meters. Yeah, there it is at the top in the highlight. 6,000 meters. Number 36. An express train passes through a station. It enters with an initial velocity of 22 meters per second and decelerates at a rate of 0.15 meters per second squared as it goes through. The station is 210 meters long. How long is the nose of the train in the station? Okay, so let's just draw a quick sketch. So here's my train. Choo-choo! And it's going to be entering a station. Okay. So let's just say this is the station over here, right? I have an opening up there. Just closing those lines. Got a little roof. Not too bad. Should have been an architect. Okay. So it says that as a train is entering the station here, its initial velocity, so the point at which it enters, is going to be 22.0 meters per second. Okay, and it's going to decelerate at a rate of 0.150 meters per second. So remember, since the train is moving in the positive x direction, and there is a deceleration that's occurring, what that means is that there's a force pointing in the negative x direction. All right, so in other words, the acceleration must be negative. So if you don't place the negative sign in front of the acceleration, all the calculations will be wrong. So it's actually a very important thing to consider. All right. All right. So, sounds like my son is excited to take a nap. Oh, he's getting even more excited. So I apologize for the distraction, but let's see if we can progress forward. I will try my best. So it says now, so the question is actually, oh boy, things are starting to unravel. Okay. So it says that the train passes through the station, meaning it's not going to come to a stop in the station. All right. So that's one thing. Now, the second thing is it says how long is the nose of the train in the station? What do they mean by long? Do they mean a distance? Do they mean how long does this train get into the station? Or does it mean how long as far as time? So it actually means how long in terms of time. All right. So it's really the time that they're asking for in terms of the nose. How did I know that? Well, I just did the problem before and found that the total stopping distance was about 1,000 meters. But meanwhile, the station is only 210 meters long. So what that would have meant was that the train blew through the station. So I figured that couldn't be right. Also, another piece of information here I want to place in is that the the station is going to be 210 meters long. Okay, so it wants us to find now how long is this particular point in the station. So in other words, how the time value, they want us to find the time here, and how long is this dot as it moves through the station? How long is it going to be seen essentially in the station? So what we want to do is we now want to find a formula that will relate time, okay, displacement, acceleration, and the initial velocity. So if you look on the right-hand side, it appears that the second equation will be the one to use, right? So let's write it down. So this is for letter A. So we got the displacement is equal to the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. Okay. So now the displacement, it told us, was 210 meters, right? The initial velocity was 22.0. The time is what we're trying to find. And now I have to add to that half of the acceleration, which was negative 0.150 times t squared. All right. So let's clean this up a little bit. So this would be 210 is equal to 22.0 t. That looks like a c. 22.0 t plus then 1/2 of that. So just take 1/2 of the 0.15. All right. So that works out to be, and actually I'm just going to change the sign there because it's negative. So minus now a 0.0750 t squared. Okay. So now, how do we solve for t? Well, you have to take a step back and notice that this has the structure of a quadratic equation. All right. So what I'm going to do is I'm going to take these terms and I'm going to subtract this term on over to the left, and I'm going to add this term on over to the left as well. Okay, so I'm going to write the result here on the right-hand side. So now it should look like 0.0750 t squared minus 22.0 t plus 210 is equal to 0 now. So now we can go about solving this particular equation. Now remember, there's a couple of ways to do this. Well, I mean, we could try to find the factors, but this would be a little ridiculous. So your best bet here is to use the quadratic formula. So it's negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? And please recall that this equation has this general form a t squared, right, minus b t plus c. Okay, so this is my a. This is my b. Okay, and this value is my c. All right, so we can take that and plug it in. I actually programmed a shortcut in my calculator. So all I have to do is place in the coefficients. So let me just do that. So my a value is 0.075. My b value is negative 22. And my c value is 210. And it calculated it. Great. So we actually get two values. Okay, so we get two time values, it seems. So let's see. Let me change the color back. So it appears that we get, let's see. So I get my x is equal to, so I get 9.88 meters per second squared. Oh no, x. Yeah, I'm sorry, that's the time value. This is in seconds. Okay, so let me just go back and change this to a t. All right. And the second value that I do obtain also is that it's 283 seconds. Okay. 283 seconds. Okay. So I got two times, but which one would be, which one's the right time? Well, in order to kind of figure this part out, it would probably be best, well, first, the simplification of this would be to take the shorter time, right? I mean, if you just step back and you think about what's going on here, just look at the initial velocity. It's 22 meters per second. That means if there's no deceleration, this train will be covering 222 meters every second, right? So that means in 1 second, it would be 22 meters. In another second, it would be another 22. A second after that, 22, 22, 22, 22, 20, right, etc. Okay? So, in 10 seconds, right, how long, assuming there was no deceleration, in 10 seconds, how long would it have traveled? Right? Well, in 10 seconds, at 22 meters per second, it would have traveled 220 meters, which means it would have just been to the outside, right? So now, okay, so now the train's slowing down though, right? It's a slow acceleration. It's a slow deceleration. But the first answer in terms of the time is reasonable, right? It should be just held back slightly. So the first time is the most reasonable one. All right, so probably the best check here to figure out which one the answer should be when you do the quadratics would be to do a little logical check, okay? All right. So that's the answer to part A. Now for part B. All right. So part B, it says, how fast is it going when the nose leaves the station? So it wants to know once the nose of the train, right? So here's the nose. Once that nose gets to the edge of the station and it's still traveling forward, it wants to know what is the velocity here. Okay? Now, in the context of the problem, I could frame this as the final velocity. Reason being is because I know the initial that it enters the station. Okay, so it's very important in terms of framing now. Okay, if this is my final, I can consider this my initial. And if my starting point of the problem's here and my ending point of the problem's here, the distance I need to consider is the overall distance between the two, which is the 210 meters. Okay, so let me just backtrack one step. So I want to find a formula that relates the final velocity, the initial velocity, the displacement, and probably the acceleration all in one equation. All right? I could use the time value, but maybe I made a mistake and I don't want that mistake to propagate into my Part B calculation. So what formula should we use? It looks like the fourth candidate here would be the best one, right? So we have the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is the question. Okay, the initial velocity was 22.0. The acceleration was a negative 0.150. And the displacement that it traveled was 210. Okay, so the final velocity squared. So let's see. So 22 squared, right, comes out to 484, and that works with 3 significant figures. Plus now, let's do the math over there. So 2 times negative 0.15 times 210. So that works out to be negative 63. So negative 63, I got to have 3 significant figures, so 0.0. And now let's add them together. So I get my squared value, so 484 minus that answer, essentially. 484, sorry, minus 63. So that comes out to be 421. And then to find the final velocity, I have to take the square root. Okay, so let's take the square root of that. And we get we need 3 significant figures. So the final velocity here will be equal to, technically, whenever you take the square root, it could be plus or minus. So 20.5, okay? But you have to remember, what direction is the train traveling? Traveling in the positive x direction, and therefore we have to choose the positive sign, okay? So that would be the answer, and I'm just going to erase then the negative one so we don't get confused, okay? And that would now be my answer to Part B. Answer. Okay. Now, let's move on to Part C. So it says Part C, if the train is 130 meters long, when does the end of the train leave the station? Okay, so basically now basically what we're manipulating now is the total distance, right? So not only does the nose here in the picture have to travel 210 meters to get to the edge, also this whole part of the train now has to also travel through the station, right? And the train length here was, it told us 130 meters long. So really what I want to do, right, is I need to find now the time, because it's asking for when does, right? So it's really wanting me to calculate time. Okay, so when does the end of the train leave the station? So I have to manipulate essentially the total distance, right, or the total displacement that the train is moving. So, in order to figure out my displacement for the problem, right, it's going to be the displacement of the station plus the displacement of the train. Okay, so the total displacement change in this problem now for Part C will be the 210 meters plus the 130, plus 130. Okay. So when we do the math here, right, that works out to be 340 meters. Okay, so that's the new displacement value. Okay, so now we want to find out, well, how long does it take? So this essentially becomes this same type of question as letter A, right? So it would be beneficial for me to use that equation. Again, reason being is because I'm only going to work with the given values that were given to me in the problem. No calculated values. So I reduce my chance for error. So let's write that equation down. Change in displacement is going to be equal to the initial velocity multiplied by time plus 1/2 at squared. All right, so the displacement we just found was now 340. Okay, by the way, what do you, in terms of the total time, do you think it's going to be longer, or do you think it's going to take longer for this, for part C than part A, or shorter? If you said longer, you'd be correct. So we should, right, we want to be thinking about intuitively as well, make sure our calculations work out appropriately. So it should be something greater than 9.88. Okay, and if it's not, then something's wrong. So the initial velocity again was 22.0. I'm finding the time, plus then 1/2 multiplied by the acceleration, which was negative 0.150, and then that multiplied by t squared. Just going to put it on the bottom there. So let's clean it up a little bit mathematically. So this is going to be 340 is equal to 22.0 t, then minus, right? We should now have the same, we have the same answer as before, right? So half of that, so it should be minus 0.0750 t squared. And again, I'm going to move these values on over to this side. So therefore I have to subtract this number. And in terms of this value, I'm going to add it on over to the other side. Okay, so now rewriting it, it's going to be 0.0750 t squared minus 22.0 t plus 340 is equal to 0. And again, you can use the quadratic equation. Here's my A value, here's my B value, and here's my C value. So notice the only thing that should have changed here would be the C value when you're comparing part A to part C. Okay, so we could use the quadratic equation. And if you need to work it out that way, that's fine, but I'm going to use my program here. And if you're curious about the program, I'm sure there's a resource online you can look up. Just look up how to program the quadratic equation into your TI-84 or 83, whatever you have. So the A value was 0.075. The B value is negative 22. And the C value is now 340. Let's calculate. Oh, nice, right? So I get two answers again. So I get my time value to either be 16, and I need 3 sig figs, 16.4 seconds, or 276, or 77 if I round appropriately, 277 seconds. So which one of these would make sense? Well, the first one does. Okay, so this is the answer. All right. So in order for the whole train to now pass through the station, it should take 6.4 seconds. All right, and if we go back and make a logical check, it works out. It also works out well when I compare that time to the time I calculated in part A. All right, we said it should be longer, and that's about how much longer. Notice the train is also 130 meters, right, which is almost 50% more than the station's length of 210. And I know the acceleration is fairly minimal, so I should be expecting about a 50% increase, which it is, right? If you compare 9, which is about 9.88, which is close to 10, and this is about 16, it's a little more than 50%, obviously, but that should be the case because there is a deceleration. But it makes sense. Okay, all right. So hopefully, let's do D. What is the velocity at the end of the train as it leaves? Okay, so now we just got to find, so essentially we're doing part B again, right? But just for now, part D. So I'm going to put that in the upper left-hand corner. All right, so it wants to know now the velocity of the end of the train. Okay, so again, I'm going to use the same VF squared is equal to VI squared plus 2AX. Remember that the final velocity is what we're looking for, okay? The initial velocity is still the 22. I'm still looking at that as the beginning of my problem. That's squared. Plus now 2 times the acceleration, which was the same, 0.150. And then now the displacement, remember, the displacement is going to be the 210 meters that the station is, plus the additional 130 meters of the train. So that's going to be 340. Okay? All right, so VF squared. Now let's do the math. I already did 22 squared before, so this should be 484. And this will now be minus, let's take out the calculator. And this is 2 times negative 0.15 times 340. So it comes out to negative 102 now. All right, so doing the subtraction here, so we got the final velocity squared is going to equal to 382. Let me just double check myself, right? So 484 minus 102, yeah, 382. It's getting late in the problem here, so I use the calculator a little more than I probably should. But the final velocity here now, all I have to do is take the square root. Okay, take the square root of that. And again, it comes out to 19.5. 19.5. Remember, this would be plus or minus because you're taking the square root. It'll always turn out that way. But since the train is still moving in the positive x direction, we take the positive value. All right? So I'm just going to backtrack to make it a little neater here. So the answer should be positive 19.5. And the units here are going to be meters per second. Great. And if you compare that to the value we found in part B, right, it's less, which it should be, because the train had to travel longer and it's decelerating. So before, the nose of the train was traveling at 20.5 meters per second, and as I started that, I noticed I missed the units, meters per second, and the end of the train will be traveling at 19.5 meters per second. Number 37. Dragsters can actually reach a top speed of 145 meters per second in only 4.45 seconds. Considerably less than that given in the examples. Okay. Letter A. Calculate the average acceleration of such a dragster. All right. Let's take a look at that first. So for part A, what are we given? So we have like this dragster, zoom, zoom, and it's traveling, or it's going to reach a top speed at this particular location, a final velocity of 145 meters per second. And it starts from rest, so the initial velocity should be 0 meters per second. And it can change its velocity in 4.5 seconds, right? So the time here is 4.45 seconds. Okay, and now it says calculate the average acceleration. So this should be fairly straightforward. Just remember the basic acceleration formula is change in velocity divided by change in time. Okay, so the acceleration here should be the final velocity, right, of 145 minus the initial velocity of 0 divided by the time change, which was measured to be 4.45. All right, and the acceleration here should be 145 divided by 4.45. So it works out to be, considering three significant figures, 32.6. So 32.6 meters per second squared. So that would be the average acceleration. So now it says, okay, so let's take a look at now part B. So it goes on to say, it says, find the final velocity of this dragster starting from rest and accelerating at a rate found in part A for 402 meters. Okay, so let's now take a look at that. So here's going to be my part B. I'll just keep using the same picture actually. So now it wants us, so now it's going to say, all right, this is going to keep going, right? And it says now that it's going to travel a total distance of 402 meters, right? So that's the distance, but the better term in this problem would be a displacement since we're talking about velocities and stuff. So it wants us to now at this location find the final velocity. Okay, if it starts from rest. So the initial is still 0. Okay, and great, and accelerating at the rate, blah, blah, blah. Okay, and now it says without using any information based on time. So what that means is that I'm probably going to have to use the acceleration value I just calculated in part A. Well, it actually said that, right? Okay, so I need to now figure out an equation that represents acceleration, displacement, final velocity, and the initial velocity. And if we look on the right-hand side, equation number 4 fits the bill. So final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration multiplied by the displacement. Okay, so the final velocity is what we're looking for, so we'll leave that alone. The initial velocity was 0, So now it's just going to be 2 times the acceleration, which we just found to be 32.6. And then multiplied by the displacement, which was 402 meters. Okay, so the final velocity here, squared, will be equal to, let's just do some math there. All right, so 32.6 times 402 times 2. And we get a value of, and I need 3 significant figures here, so we get a value of I'm going to do some scientific notation, 2.62 times 10 raised to the 4. Times 10 raised to the 4. Take the square root. Right? Remember, anytime you take a square root, your answer will always be now plus or minus. Okay, so just take the square root now of square root of 2.62 times 10 to the 4th. And we get a value of 162. 162. So which one should it be? It should be the positive answer because the vehicle is moving, or the dragster in this problem is moving to the right. It's moving in the positive x direction. So let's just simply erase this little negative sign. And this will be this is the final velocity. So that's part B. So now part C. It says, why? Why is this final velocity greater than that used to find the average acceleration? And then it gives us some hints. We don't need the hints. So the final velocity that we just calculated in part B was 162, and I should have put the units, but I didn't. So this is meters per second. All right, but it told us in the first part of the problem, if you look back at the top, that dragsters can actually reach a top speed of 145. So the reality is dragsters reach 145 meters per second, but this is what we calculated. Okay, so why the discrepancy? Well, most likely it didn't take into account air resistance. Okay, so the dragster can only produce so much power, and the faster the dragster moves, the more air resistance that dragster experiences. So therefore, the more essentially backwards force that the dragster that there will be on the dragster. So one of the reasons why there is this discrepancy is due to air resistance. Okay, great. And then it says, okay, good. So that's fine. So that answers that. And then it says something about, if not, discuss whether the acceleration would be greater at the beginning or the end of the run. Right. So the acceleration should be greater again at the beginning. Okay, so acceleration, let me write that over here. Acceleration greater at beginning. Again, why? Because of air resistance. Okay, more power in the beginning of the drag race, more power can be given to increasing the velocity. And as the velocity keeps getting faster and faster, air resistance keeps increasing. So now more of that power that the dragster is producing will have to be allocated to overcoming air resistance, then being allocated to increasing the velocity. Number 38. A bicycle racer sprints at the end of a race to clinch a victory. The racer has an initial velocity of 11.5 meters per second and accelerates at the rate of 0.5 meters per second squared for 7 seconds. What is his final velocity? Okay, so let's draw a little, let's draw a little bicycle here. Sure. And pretend the problem is about skateboarding, because the picture looks closer to a skateboard than it would ever to a bicycle. Okay, so for letter A, it's asking what is the final velocity. So he's starting with an initial velocity, as it mentions in the problem, right, of, 11.5, right? So the initial velocity here would be 11.5 meters per second. Okay, and he's accelerating now because he's trying to win the race. So his acceleration now, let me move it down a little bit. His acceleration now is going to be 0.500 meters per second squared. And he's going to be accelerating at 0.5 meters per second squared for 7 seconds, right? So it says that the time value here should be 7.00 seconds. Okay, and what we're looking to find now at the end of this, the final velocity. All right, so do we have an equation now? We have to think about this. We need an equation that will relate initial velocity, acceleration, time, and final velocity. And we do, right? It's number 1 here at the upper right. So let's do that. So letter A is going to be the final velocity is equal to the initial velocity plus the acceleration times time. The final velocity is what I'm looking for. The initial was 11.5. The acceleration, they told us, was 0.500, and the time was 7 seconds. Okay, so let's just plug it into the calculator. So it's 11.5. Take, well, don't even need a calculator, right, because it's just half. So this comes out to 3.5. So 3.50, because I need 3 sig figs. And now when I add these two values together, so I have the final velocity now, just be careful about the value you're going to obtain in terms of significant figures. Okay, so this should now be 15, right? 0.0, right? Because I have to cut the answer at the at the tenths place instead of the hundredths place. Okay, so the units here would be meters per second, and that now completely solves for the final velocity. Let's move on now to letter B. So letter B. It says the racer continues at this velocity, okay, so the velocity we just found, to the finish line. If he were 300 meters from the finish line when he started to accelerate, how much time did he save? Right, so how much time did he save? Okay, so let's add in some context to the picture. All right, so he's traveling, okay? And he has to cover now to get to the finish line, which is here, right? This is the finish line. He has to travel 300 meters, okay? So I know that the displacement here is going to be 300 meters, okay? Now, it says, so the question is asking, how much time did he save? Well, in comparison to what? So let's say there's two scenarios here. In scenario number 1, the bicyclist doesn't accelerate. Right? He just travels at his initial velocity of 11.5 and he'll eventually reach the finish line. And that would take a certain amount of time, right? Now, if he though starts to accelerate like it was in question A, and he starts to accelerate, do you think that he would reach the finish line sooner? Yeah, he would, right? He would reach it sooner. How much sooner? That's the question. So what we can do is we can first find, and we'll first assume no acceleration, okay? So assume no acceleration. So that means his initial velocity was 11.5 meters per second. The final velocity would be the same, right? Because there is no acceleration. The acceleration 0. My displacement here, he had to travel 300 meters. Okay, and the time, we don't know either, right? So time is question mark. So again, what we want to do is we want to try to find time. So we need to consider, do we know any equation that can relate these variables? And I think the easiest one might be the last one here. Okay, so if I have my change in displacement will be equal to 1/2 the initial velocity plus the final velocity, right, multiplied by time. I mean, we don't even need this written out equation. We can even use a simpler one, but it's just here, so let's use it. So this is x is 300. Then it's 1/2 of the initial velocity, which is 11.5, plus the final, which is 11.5, times my time. So this is 300 is equal to 11.5 plus 11.5, and half of that would simply be 11.5 t. So this actually works out to be just a simple x is equal to vt formula. Okay. Now just divide out the 11.5. So now the time value, assuming no acceleration, right, it would work out to be 300 divided by 11.5. So 26.1, we got to have 3 significant figures here, so 26.1 seconds. Okay, Now, what happens when he does accelerate? So we have to think about this in a couple of ways. All right, there's really two parts now to this problem. So the first part we have to consider actually exactly what we considered in the part here in the picture in black. Okay, what I need to though do is I need to then find the distance that is covered here. Okay, so the distance is the question mark. Okay, and what I can do then is if I can find the distance here in black, then I now know once he obtains this final velocity that we calculated of 15, right? This is really, instead of equaling a question mark anymore, it really equals 15 meters per second. I know though from this particular point to the end, he's going to be traveling that at a constant, what's the word? A constant velocity, right? There's no more acceleration. So essentially this works out to be a two-part problem here. This is like a part A and this would be like a part B. Okay. So let me just put this part in red. Okay, so this is my part A finding, okay, and this is part B. All right, so let's take this in pieces. So I'm going to do the work right beneath this. I'm going to just close this off a little bit. And now let's say this is assume that there is an acceleration. Okay, so for part A now, what we would like to do is, well, actually, do we even need to? Yeah, no, we do have to find the distance because we have to figure out how much left is to cover. So what I want to do is first find the distance here. Okay, so how do I do that? Well, I need to figure out an equation that relates initial velocity, right? Acceleration, time, final velocity I did find, so I can even use that. But do we have an equation that might be representative of those variables? Well, if we go back and we look, right, it looks like we can probably use equation number 2 for our purposes here. Okay, so let me just actually backtrack those circles off. Let's keep it a little neater. And let's write that equation down. So change in displacement is equal to the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. So the displacement here will be equal to 11.5 multiplied by the time, which was 7 seconds, plus 1/2 of the acceleration value, which is 0.500, times the time again squared. Okay, so my displacement here, let's clean this up a little bit. Let's multiply some stuff across, times 7. So this is 80.5. This first part, 80.5, plus now, let's calculate the second. So 0.5 times 0.5 times 7 squared. So 12.25, but I need 3 sig figs, so this is going to be 12.3. Add those two together. Right, so this should simply come out to be 92.8. And this is meters. Okay. So 92.8 meters, he would have traveled now. Let me just go back to the picture. Let me erase this. Okay. So this part right in here now, this distance from this location is 92.8 meters. Okay, and remember, in order to cover this distance that we just found, it took him 7 seconds. Okay, the reason why I had to find that distance is because now I need to find the remaining distance in part B. So how do we do that? Well, you might say, well, if the whole length of the thing is 300, and he already traveled 92.8, just do a subtraction, right? So that'd be correct. Take 300, subtract 92.8. So this should be about 207, and we got to consider significant figures here, so it'd be 207. 207 meters would be left. Okay, so now what we need to do is now this is essentially my part B. Remember, this is the dividing point. So what's the velocity here? Well, the velocity here was the final velocity of the first part, right? So that's just 15. This is now my displacement that I just found, right? And remember the acceleration over this time frame. Let me just get rid of some of these circles here. Okay, this is just x. And remember the acceleration now in this part is 0. Why? Because, where does it say? He accelerates at a rate of that only for 7 seconds. So he doesn't keep accelerating. So once the 7 seconds is up, he stops accelerating. So now what I need to do here is essentially I know my initial velocity, right? The final velocity once the bicyclist reaches the end of the line, it will be the same, right? It'll still be 15 because there's no acceleration. So I can use the same formula I did for the part where I assumed no acceleration. Okay, so let's now move over to here, the bottom right for part B. But I can break this down into an easier formula, right? I can just do x is equal to vt, okay, just to save some space. So my displacement was 207, right? The velocity is 15.0, and I'm looking for now the time. So just divide out the 15.0. So now my time value, I'm going to put it up here. So my time value for part B is 207 divided by 15. 3 significant figures, it works out to be 13.8. 13.8. Okay, so this is the time for B. All right, now let's think about this. Okay, let's think about this. So the time for part A was 7 seconds, right? This is the time for part A. And then I just found now the time for part B to be 13.8 seconds. And this is for part B. So what would be the total time? Right, just simply add them together, right? So the total time will now be 13.8 plus 7. I don't even need a calculator for that, but I used it anyway, is 20.8. So 20.8 seconds. That is now the total time with the acceleration. Okay? So now we have to remember, what do we even want to solve? Remember, the question is asking how much time did he save? So let's go back over to here where I just started on the right-hand side. This is the time in which he would have crossed the finish line, assuming he didn't accelerate at all. It would have been 26.1 seconds, which should be longer than if he did accelerate. And it is, right? We just found it to be 20.8. So how do we find how much time he saved? All right, it would just be a subtraction, right? So let me do that. I'll do it right down here. Okay, so the time he saves now, so the time, I'll say saved, is equal to the time where we assume no acceleration minus the time of acceleration. So the time saved should then be simply 26.1 minus 20.8. So the time saved here, let's just plug it into the calculator, 26.1 minus 20.8. And this is 5.3. So this works out to be 5.3 seconds. I just need a quick drink of water. Excuse me 1 second. Okay. Man, this is a long problem. Okay, so this is finally the answer to part B. Okay. Now, oh boy, part C. One other racer was 5 meters ahead when the winner started to accelerate, but he was unable to accelerate and traveled at 11.8 meters per second until the finish line. How far ahead of him in meters and in seconds did the winner finish? All right. Either my brain is fried at the moment or this question isn't making too much sense. So one other racer was 5 meters ahead of when the winner started to accelerate. Okay, so let me draw a little sketch. I'm going to draw a sketch in the upper left-hand corner. Okay. So here we have a racer, right? He was 5 meters ahead when the winner started to accelerate. So I assume that the winner came from behind, right? So here, this distance is 5 meters. They're separated. Okay, and I'm thinking that the finish line will be somewhere over here. Okay. Okay, so one of the racer was 5 meters ahead when the winner started to accelerate. But he was unable to accelerate. Who's he? These questions are sometimes not detailed enough. But he was unable to accelerate and traveled at 11.8 meters per second until the finish line. How far ahead of him in meters did the winner finish? Okay, so I will assume, so by some friends, clinch. Okay, so the person that we just calculated all the information for, sorry it take me a second, but there's too much he and him and this and that, and there's not enough definition in what they're talking about. So it's a little hard to wrap your head around. But what we just calculated, if we go back in the problem, we just calculated information about the winner, right? So this guy's the winner. And we just calculated everything we needed to know, okay? Meaning that his acceleration, how much time he saved, and all this, the total time it would have taken him to get from the point where he is to the finish line, etc. So, and now it says the other racer, though, was 5 meters ahead, so this is the loser, right? Poor guy. And so he's 5 meters ahead when the winner started to accelerate. But I'm going to assume the loser was unable to accelerate. All right, now let's make it a little more sense. See, they really need to give you more context. So the loser was unable to accelerate and traveled at 11.8 meters per second until the finish line. So this guy is traveling at a velocity of 11.8 meters per second until he reaches the finish line. Now remember back to the prior problem that the total distance from the winner to this finish line was 300 meters. Okay, and that means that the distance from now the loser, right, to the finish line would then be simply 295 meters because he's 5 meters ahead of the winner. Okay, so how far ahead of him did the winner finish? Oh, okay. So how far ahead of the loser did the winner finish? Okay, so now we can do this. All right. Man, these are really, the wording is terrible. So, okay, so we know the velocity. Okay, we know the displacement. What we need to now do is solve for time. Okay, so a simple velocity formula, right? Velocity is equal to displacement over time. So his velocity was 11.8 meters per second. He had to travel a total of 295 meters. And now I want to solve for the time it took him. So just doing some math, just do a cross multiplication. So really it's going to be 295 divided by 11.8. So this works out to be 25 seconds. Exactly. So 25.0 because I need 3 sig figs seconds. Okay, great. Now, that's the time it would have taken the loser to go from his position to the finish line. But if it took the loser 25.0 seconds and the winner, go down to the bottom of the, not the bottom, the middle of the page, and it took the winner 20.8 seconds to complete his to travel his distance. It's now asking how far ahead, right, of him in meters. Now I don't know how far. I'm sorry, in meters and in seconds. Okay, so in seconds we can calculate this, right? So to find now the difference, we would just have to take the difference, right? So what I would do here is now simply take how far, in order to find how far ahead, it would simply be the 25.0 seconds and subtract out now the 20.8. Okay, so this is now the time ahead that the winner finished. So this is 25 minus 20.8. Okay, so 4.2. So he finished 4.2 seconds, 4.2 seconds ahead of the loser, right? So now what we can do is we know that we know that the loser now will have to travel an additional 4.2 seconds after the winner crosses the finish line. So now, in order for me to figure out how far behind the loser is, I can just use a simple v equals x over t formula. So I'm going to do that, and I'm running out of space. I'm going to do that down here on the bottom. Okay. So again, velocity is equal to displacement over time. I know the loser's velocity was 11.8 meters per second. And I don't know the distance he has to still cover, but that's what I'm trying to find. But I do know he's going to have to travel 4.2 seconds longer, right, than the winner. So if this should hopefully make a little sense here, that in order to find the displacement that he needs to travel or how far behind he is, I found then the time difference, right, or the additional time he would have to travel, and then all I need to do is multiply it by his average velocity there. So let's just do the math. So this works out to be 11.8 multiplied by 4.2, and 4.2, yeah, only two significant figures here, so this answer should be 50. So 50 meters. So the loser is 50 meters behind. Okay, so this one is the answer to letter C, as well as this is the answer to letter C as well. And man, we finally completed this whole problem. Complex problem, difficult problem, many difficult steps, but I hope it kind of makes a little sense. We just have to kind of get some context to letter C. We got to tweak the he's and the hims and all this to winners and losers and try to be able to differentiate it a little better. Number 39. In 1967, New Zealander Burt Munro set the record for an Indian motorcycle on the Bonneville Salt Flats in Utah with a maximum speed of 183.58 miles per hour. The one-way course was 5 miles long. Acceleration rates are often described by the time it takes to reach 60 miles per hour from rest. If this time was 4 seconds, meaning the time it took to go from rest to 60 miles per hour, and Burt accelerated at this rate until he reached his maximum speed, how long did it take Burt to complete the course? Okay, so it sounds like eventually we're looking for a time. All right, so we have a motorcycle. All right, I don't know, hopefully my drawings will get better by the end of this, but that's some type of, it looks like he's being impaled by something, but okay. Let's just pretend that that's a motorcycle of some sort, and he is accelerating from rest, so his initial velocity is 0, and it says he's going to reach a maximum speed eventually of a final velocity here of 183.58 miles per hour. Okay, and this track is going to be, I don't know, 5 miles long, right? So the total distance here will be something like 5 miles. Okay, 5.00 miles. And okay, great. And he's accelerating, right? Because he's somehow getting from an initial value of 0 to this velocity. So that we don't know directly, but they did give us enough information in the problem here that I'm underlining in red to solve for that acceleration. Okay, so in order to find the acceleration that this motorcyclist is accelerating with, we have to take we have to calculate it by knowing that from rest let me rephrase. So the initial velocity is going to be 0 in that case. Right, the final velocity, it says he's going to reach 60 miles per hour. And this will be obtained in 4.00 seconds. Okay, so why don't we I'm going to convert everything into meters and seconds. All right, I think it's just easier when we deal with this. So what I'm going to do first is let's convert this 60 miles per hour into meters per second. All right, so and again, here I'm looking for the acceleration. So I'm going to do that down here. 60 miles per 1 hour. And I would need to convert that into meters per second. All right, so let's first get rid of the mile value. And we know that there is approximately, for every 1 mile, there's approximately 1,609 meters. Okay, so the miles would cancel. My answer would now be in meters per hour. Okay, instead though, now I got to get rid of hours and I want to get down to seconds, right? So the hours have to go on the top so that they cancel. That's a little opposite because I'm dealing with the unit in the denominator. But then I'm going to put the hours in the numerator and then minutes in the denominator. So this is 1 hour for every 60 minutes. And then do the same thing again. Minutes in the numerator, seconds in the denominator. The minutes will cancel. If you notice, the units that are left are going to be meters per second. Okay, so let's actually do that calculation now. So 60, so let's take 60 multiplied by 1,609 and divide that by then 3,600. So this will work out to be approximately, and I'll do, 3 significant figures should be good. So 26.8 meters per second. All right, great. So I'm just going to write that over here, 26.8 meters per second. Okay, so now I have enough information in order to solve for the acceleration value here, right? So thinking about this physics formula of the final velocity is equal to the initial velocity plus the acceleration times time. I know the final velocity was 26.8. The initial velocity was 0. The acceleration is what I'm trying to find, and now my time is 4.00 seconds. Right? So this simply breaks down to 26.8 is equal to 4.00a. Divide out the 4 from both sides. So now a will be 26.8 divided by 4. Hold on, 26.8 divided by 4 comes out to 6.70, 3 significant figures, meters per second squared. Okay, wonderful. So that is the acceleration. So 6.70 times 10 to the, 6.70 meters per second squared. Okay. So now it says, okay, great. So we found the acceleration. So the acceleration here will be, again, it'll be 6. Let me just get rid of actually that, that question mark. Okay. So let's write it in. So it's 6.70 meters per second squared. Okay. All right. So now let's read the last sentence. So it says, if this time, if this time was 4 seconds and Bert accelerated at this rate until he reached his maximum speed of the 183.58 miles per hour. Right? How long then? Okay. So now that's exactly what I'm showing here. This is the acceleration. He's eventually going from 0 to some final velocity. So why don't we do this? What we need to do first is now consider how long. We can consider it in terms of time, but why don't we do it in distance? Because we really have to check to make sure that he reaches this speed before the end of the track. Okay, and let's see if that's the case. So what I really need to do for this part in black, essentially here, I want to find the displacement. Okay, so again, initial velocity is this, final velocity is this. This is the acceleration. So how do we find displacement? We can use now this physics formula, right? We can use the formula Vf squared is equal to Vi squared plus 2ax. So the final velocity was 183.58. The initial was 0. The acceleration was now 6.70. And now the displacement is what I'm looking for. But remember, you got to be careful here. The problem here is now, can I use this number? I want to see if you guys are paying attention. I can't, right? I can't because this is miles per hour. And what are the units here? Meters per second squared. Okay, so I have to do a conversion. All right, so let me just leave that as a little x for now. And what I need to do is I need to convert this value into meters per second. So let's do that on the bottom again. So let's do 183.58 miles per 1 hour. Now I basically did this already, so the conversion is going to be the exact same as on the left-hand side. So we got 1609 meters over 1 mile. then 1 hour over 60 minutes, then 1 minute over 60 seconds, right? And all the units would cancel. So let's do this now. So 183.58 multiplied by 1609, and then divided by 3600. So this comes out to, I'm going to have, actually in this case, we're going to do 4 significant figures. So 82.05, this would be meters per second. Okay, so this is the number that now I can plug in. Okay, so let me just erase. Let's erase this. Okay, we'll get rid of this. Goodbye. And now let's plug in our 82.05 value. So now we should be able to calculate from here, okay? So let's do 82.05 will be equal to 2 times 6.7, so 13.4, x, right? Divide out the 13.4, divide out the 13.4. So now my displacement value is 82.05 divided by 13.4, what do we got here? 6.12, right? 6.12, okay. 6.12, and that's meters. Okay. So, yep, I had to backtrack one step because I'm looking at that and I'm like, wait a minute. That would only be a short amount, right? So what did I forget, guys? What did I forget? All right. So I'm sure some of you caught it. Right? Please be careful with this formula because I forgot the squared. That'll make a huge difference, okay? But if you notice, look, I make mistakes. Everybody makes mistakes. We're human. There's a lot going on in the problem. But what's most important is that what's always trying to play in my mind is the answer reasonable? Does it kind of make sense? So when I got that number, I'm thinking to myself, I'm like, 6 meters. Something doesn't sound right. It sounds too short, right? So I was like, did I make an error anywhere? So I'm backtracking, and I did. Right now, that skill will help you on the test, okay? And that's the most important place to, well, I don't know if it's the most important place, but it's an important skill that will help improve your grades, okay? So now let's square this value. So now it becomes 6732. Okay, so that will now equal the 2 times 6.7 again, which was 13.4. 13.4x. Now divide out the 13.4. Divide out the 13.4. And now the displacement, it'll make a lot more sense. This is 6732 divided by 13.4. That sounds a lot better. Okay, so it'll obtain its top speed in 502 meters. Okay, that's starting to make a lot more sense. All right. So now, great, we got our meter value of when it will. So we know that this x right here that we calculated was 502 meters. Well, how does that relate to 5 miles? Well, again, we can just simply convert those miles into meters, and then we'll be able to tell, right? So just take that value and multiply it by miles on the bottom, meter on the top, and remember that there's 1,609 meters in a mile. So just do that calculation. So 5 times 1,609, 8,045. So technically I should have 3 significant figures here. So it has to work out to be 8,000 and 8,050, no decimal. Okay, that'll be it in meters. So the car reaches its top speed of 183.58 miles per hour in this distance, right? 502 meters. Okay. Now we know that the track is 8,050 meters long, right? So that means now from this particular point all the way to the end of the problem, right, would just be the difference. So to find that value, it would be 8,050 minus the 502, right? And now what does that come out to? What does that work out to be? At 8,050 minus 502. So that works out to be 700 7,548, but I got to have three significant figures there. So 7,550, I have to round. So this is the amount that's left now. And now remember that when the motorcyclist, Mr. Burt here, travels this distance, he is traveling it now at his top speed. Okay? So now if I need to now figure out, so remember, the whole question is asking me how long did it take Burt to complete the course? Okay? So I need to know time. All right? Now the reason why I had to find this distance is so that I could find this distance. All right, the distance that's remaining. And now I know that for this frame of the problem, from this location to this location, there is constant velocity. Okay? So I can easily now solve for the time. All right, so I'll call this part, let's call this part in red. This is part B. Okay? So let's do time calc for part B. All right? And then I'll go back and do part A. So we can use a simple formula here, right? Velocity is equal to displacement over time. So the velocity, remember I want to use meters per second, so I'm going to use the calculated value at the bottom. So it's going to be 82.05. That's equal to the displacement of 7,550 meters over then my time. Okay, so just now do the math. So it's going to be 7,550 divided by 82.05. And it comes out to 92.0, three significant figures, 92.0 seconds. Okay, so that's how many seconds now in the in part B. All right, so in other words, to go from this point, right, to the end, it took him traveling at the constant velocity of 183 miles an hour, took him 92.0 seconds. Now the only question is, right, I got to figure this out. How long did it take Burt to go from that point to here now? So we have enough information, right? We want to be thinking about this frame of the problem now, all the information that we know there. Okay? So in order to find time, we can do this a couple of different ways. Easiest way might be to use a very similar formula to what we used over here. Okay? So remember, I know the initial velocity. I know the final velocity of that frame. I also do know the acceleration, and I want to find time. So therefore, I can use now my VF is equal to VI plus AT. Now this is the time calc for part A. So the final velocity, again, I got to do it in meters per second. So it's the 82.05 is equal to the initial velocity was 0. The acceleration we found to be 6.70, right? And then we're looking for t. Okay, so this works out to be 82.05 is equal to 6.70 t. Divide out the 6.70, divide out the 6.70. So now t will be, we got 82.05 divided by 6.7. So again, three significant figures, so 12.2. So 12.2 seconds. Okay, great. Now remember, this is the time for part A. This is the time for part B of the problem. Now how do we find the total time? Yep, very simple, right? So in the upper right-hand corner, I'll put it that the total time should be equal to the time from A plus the time from B. So the total time it took him would be 12.2 seconds plus then 92.0 seconds. Right, so the total time now, the total time will work out to be, that looks like, right, it's going to be 104.2 seconds. And I always like to just double check because I'm prone to making silly errors. And that looks good to me. So that'll be the total time. So this is the answer to the problem. Now it's a very complex problem, but in physics it's very important to consider how to frame the problem. What I mean by that is consider your initial and final frames, okay? You want to break the problem up into pieces. And then from there, when you break it up into manageable pieces, we can start putting those pieces together to get the answer. Number 40. A world record was set for the men's 100-meter dash in the 2008 Olympic Games in Beijing by Usain Bolt of Jamaica. Bolt coasted across the finish line with a time of 9.69 seconds. If we assume that Bolt accelerated for 3 seconds to reach his maximum speed and maintained that speed for the rest of the race, calculate his maximum speed and his acceleration. Okay. So this is a difficult problem. So let's draw a picture. I think a picture we'll be able to simplify this. So here we have Bolt, and he is going to be running in this 100-meter race. So it says initially, right, he's going to be accelerating. Okay, with some value we don't know, but his acceleration will equal something here. Okay, we know he's starting from rest at this point, so VI is 0. Remember the whole race is about 100 meters long, so let's just say it's going to be something like that. So this will be the 100 meters. Okay. And what else does it tell us? And Bolt accelerated, it told us though, he accelerated for 3 seconds. Okay, so the time, we know the time here would be 3 seconds. All right. And at that particular point, he reached his maximum speed. So at this location right here, we'll consider this like his final velocity, okay, of the first part, or this frame in black. Okay, and we don't know what that final velocity is. But then they said that moving on forward, right, he's going to maintain this final velocity, or this maximum velocity now for the rest of the problem until he finally reaches the finish line. Okay, so if I think about now, what does it look like? What does this frame of the problem look like? We already know the time, right, for this particular frame in gold. It would be the total time of 9.69 seconds minus the 3 from the first part, right? So that should make sense. So let's do that in the calculator. So 9.69 minus 3. And why do you need a calculator for that? I don't know. But just to be safe, 6.69, that'll be in seconds. Okay, great. What else do we know about this? Well, we also know that the velocity value here. So think if I'm considering this my this frame, the gold frame, right? This really is my initial velocity because that's the start of my gold frame, okay? And then this would be considered the final velocity. But remember that we don't know either of these, but they're both going to be the same, right? Because there's no acceleration in this part. And the final velocity of the first part is equal to then the initial velocity of the second. Okay, so that's cool. And what else could we do here? Well, we could also talk about the displacements, one other thing, right? So let's dot a line down here. Now what I can think about is I can consider now this distance here, okay? I'm going to call it x1, right? Because I really don't know what it is. But I do know that if I call the left-hand side x1, and I call this side x2, well, they should both add up to 100, right? So that'll essentially be my first formula, okay? My first formula here is going to be that that x1 plus x2 equals 100. Okay, so now from here, what I'm going to do is I'm just going to start. I mean, it might be hard to plan this out, all right? And it might be difficult to try to see where to go, and no big deal. Just start picking some formulas and start writing some stuff in. Okay, if you're lost, don't worry about it. Just try to push forward. So on the right-hand side, let's take a look at some of these formulas, and let's just write in some stuff. Let's start writing stuff down. Okay, so let's first talk about the frame in black. All right. So for the frame in black, I could write a formula of VF is equal to VI plus AT. Now, for the frame in black, do we know the final velocity? No, we don't, so just leave it as the final velocity. Do we know the initial velocity of the frame in black? Yes, we do. It's 0, right? So that essentially drops out. Do we know the acceleration of the frame in black? No, so just leave it. Do we know the time? Yes. So that's a 3. All right, so let's clean this up a little bit. So we know the final velocity should be essentially 3 times the acceleration. Okay, now that's fine, but that's not an answer. All right, that's just a simplified equation. So now, maybe can we do some other things, or maybe is there anything else another equation we might be able to use to describe the part 1 scenario here? Well, maybe. So I already used the top one. Okay, maybe why don't we use, and let me change these a little bit. Let me use the second one now, all right, to describe the frame in black. And why am I doing this? Why am I choosing these two? Well, part of it could be a little random. I'm just seeing what works. But also I know that the initial velocity is 0. So when I choose these formulas, I know I can get rid of a term. So it helps simplify things. So now let's take a look. So the displacement of now this is important. You got to think about your frames, okay? So the displacement of the first frame should equal the initial velocity of the first frame times the time of the first frame, plus 1/2 times the acceleration of the first frame times the time again of the first frame squared. Okay, so we got all these ones. So the displacement of the first frame is just, as I called it, x1. Okay, so that just is x1. Now, what's the initial velocity in the first frame? 0, so this whole term goes bye-bye. And now that's equal to 1/2. The acceleration in the first frame, do we know it? No, so that's fine, so just leave it as a. Okay, and then the time of the first frame, do we know that? Yeah, we do, they told us, right? 3 seconds. So it's 3 squared. Okay, clean it up a little bit, do the math. And 3 times 3 is 9, times 1/2 is 4.5, right? So x1 equals 4.5 a. Okay, interesting so far. So now you might say, well, wait, can I solve anything here? Can I do something with these two? Well, not really, right? The problem is we have 3 unknowns. We have a, x1, and vf, but only 2 equations. So we can't do anything yet. All right, no big deal. Well, you might say, well, wait a minute, I know this third equation over here. Can I plug this in and do something? No, same thing. We're going to just substitute the x1 for the x2 now in this problem. So no. Okay, so don't worry. So we can't do anything here yet. So maybe now we have to jump to the gold frame. All right, maybe we got to start writing some stuff down over there. Maybe we got to start thinking about formulas that may include the x2. And let's see if we can, right? So let's see. Maybe, well, let me think about this one. Maybe I'll use this same equation again. Let me use this equation to now describe the gold frame. Okay, so let's write it carefully. The change in displacement of the second frame will be equal to the initial velocity of the second frame, right, times the time of the second frame, plus 1/2 times the acceleration of the second frame times the time of the second frame, squared. Okay, so what's the displacement of the second frame? Well, I just said it's x2. All right, so just leave that x2. What's the initial velocity of the second frame? Well, here's the key. Here's the initial velocity. I said we don't know it, but remember, before I said that the initial velocity of the gold frame, or the second frame, is going to be the same as the initial velocity, as the final velocity of the black frame. So what I'm actually going to do here, instead of writing the initial velocity of the second frame, I'm going to write the final velocity, okay, of the first frame. Okay, that's then multiplied by the time of the second frame. Do we know that? Yeah, we do, 6.69. So that's 6.69. Plus then 1/2, right? Actually, let me not write it out yet. So let's think about it. 1/2, right, times the acceleration in the second frame. What is it? We know it. It's 0. So guess what happens? That whole term drops out. Again, why did I pick this formula? Because I realized that the acceleration is 0, so I can simplify it a little bit. All right, so let's clean this up now. So we got x2 is equal to the final velocity of the first frame. Actually, you know what? I'm going to reorganize it. 6.69 times the final velocity of the first frame. Now, do you have this variable any other place in your other equations? We do, right? I just didn't mark it as a little 1 down there, but remember, I did do this formula for the first frame, so I can put up my little 1 down there. Okay, and this is really A1 as well. We mark them all 1s. So what I can do here is maybe I can do a little substitution, right? Maybe what I can do is maybe relate these two together or something like that, right? So let's see what happens when I plug one in for the other, all right? Maybe what we'll do is why don't we take essentially this value, all right? Since that's equal to VF1, let's take that and then plug it in to here. What do we get? So we're going to get, this is now, let me just write a different sign. So this is now x2 is equal to 6.69 times 3 times the acceleration of the first frame. Okay, does that help me at all? Well, maybe not. I don't know. I don't think so yet. I can't really simplify it. All right, let's try something else. Maybe what about this now? Well, I notice I have an A1 in here, right? And I notice I have an A1 here. So maybe what happens if I solve this thing for A1, right? And then plug that in. All right, so remember, to solve that for A1, you would just have to divide out the 4.5, right? So then that would mean that A1 is equal to x1 over 4.5. Okay, well, let's take this now and plug it in for here. All right, let's see what happens. So I'm going to take now, let me change the color. So we're going to take now, so this is going to be equivalent to x2 is equal to 6.69 times 3 times x1 over 4.5. Okay, all right, so look, it's getting a little crazy now, right? We got a lot of numbers. Let's just simplify it a little bit. We can do the math between these numbers, right? So let's try to clean it up. So we got x2 then is equal to 6.69 times 3 divided by 4.5. So it comes out to 4.46. 4.46 times x1. Okay, well, oh, man, we still didn't get it. What do we got to do? Well, wait a minute. Go back and look at what I drew in red. Now look at this. Interesting. Okay. What do I have here in the box where I start? I have an initial equation. And how many unknowns do I have in this equation? I have 2, both x1 and x2. Now notice, in the new equation I just created, how many unknowns do I have? I have 2, both x1 and x2. But guess what that means? Now we have 2 equations with only 2 unknowns. And this is wonderful because now I can actually solve for one of them. Okay? So let's do that. So let me just write them here at the top again. So x1 plus x2 is equal to 100. What I'll do here is I'll solve this thing for x2. So just subtract the x1. All right, so x2 now is equal to 100 minus x1. Okay, great. And let me rewrite the equation that I came up with at the bottom. Right, so we said x2 is equal to 4.46 x1. So now look what I can do. Since this term equals x2, right, since that equals x2, what I can do is just plug it in. And lo and behold, look at what happens. Now I have 100 minus x1 is equal to 4.46 x1. Hooray, right? Thank goodness. Now I have one equation with one unknown. This is amazing because now I can actually solve for x1. So I add one of the x1s on over. So we get 100 is equal to 4.46, excuse me, not 4.46, 5.46 x1. Now this thing looks kind of like a multiplication sign. I didn't mean for it to, but it has to be an addition sign, right? Because we're adding it. Okay, now just divide out the 5.46 x1. Not x1. Don't bring the x1 over, please. Divide out the 5.46. All right, and now we realize that x1 is equal to 100 divided by 5.46. So we get an answer of approximately 18.3. Okay, great, and we'll have 3 significant figures. So 18.3, and that number is in meters. Interesting. So where is x1 in the picture, this is x1. Okay? So here's x1. Now, I know that this distance, x1 here, is, the distance here is 18.3 meters. Wonderful. Okay, so can I now solve for the acceleration? Well, we can, right? We can, but we don't even need to. We don't even need to really go back that far. We don't even have to think about a new problem. All right, I got initial. I don't know the acceleration. I got time. I got this. How do we solve it? Look, we already created a nice equation here. Take a look at this. I'm going to box it in red. Bottom. Look at this equation I created. Right? What does that equation say? That equation says, and I'm going to write it over here on the right-hand side, that equation says that the displacement of the first part will be 4.5 times greater than the acceleration of the first part. So remember, it's asking us to calculate the acceleration in the problem of when the acceleration that he's obtaining for 3 seconds at the beginning of the race. So we do know x1, right? We just found it. So we'll just plug it in. So 18.3 is equal to 4.5 a1. How do you solve it? Divide out the 4.5. And let's see what we get. A1 is then equal to, let's give it a go. So we got, and I think I should have had, I probably should have had another sig fig here, I think. Because this was really the number here was 3.00. Okay, so this should have been 4.50. So we got 18.3 and then divide it by 4.5. And wow, cool. So the answer comes out to be 4.07 meters per second squared. This is an answer. That is our answer, right? So that works great. That's the answer that's the one answer to part A. Okay, so we did the acceleration. Now look back at the problem. We need to find the maximum speed. How do we do that? Well, look at some of the equations that you generated already. Right? Bottom left-hand side, take a look. We know this. Right? We found this equation before. What does this equation tell me? This says that the final velocity of the first frame, which is essentially the maximum velocity, right, he will obtain, will be 3 times greater than the acceleration of that first frame. So we just found the acceleration of the first frame, right? So upper left-hand corner. So the final velocity of the first frame, which is the same thing as the maximum velocity, will be 3 times the acceleration of that first frame. So the final velocity of that first frame is equal to 3 times the value we just found, 4.07. So let's calculate that. So 3 times 4.07. 22.1. So we got 20. Oh, no. What am I talking? 22. Look at it. I just have to open up my eyes. 12.2 meters per second. Okay, and remember that the final velocity of the first frame is equal to the maximum velocity, right? So we can say that Vmax now is equal to 12.2 meters per second. And that would now be the answer to part A. Now, I ran out of room, but let me walk you through part B. So during the same Olympics, Bolt also set the world record in the 200-meter dash with the time of 19.3 seconds. Using the same assumptions, meaning that he accelerated to his maximum speed in 3 seconds, right? What is his maximum speed for this race? So you would literally do the exact same thing, okay? So what do I mean? You would first set up the problem, draw a picture, challenge yourself here. Set up the picture just how I did here, okay? Set that up. And then you can do the exact same steps. Set up your distance equation, okay? Then set this equation up, set this equation up, set this one up. Then start plugging stuff in just like I did. All right? And you will arrive at your answer. I promise. I realize I left the box out there. All right? But I think So in that particular problem, I believe he reached a maximum velocity of about 11.2. So check your work. You have the answer. All right, give it a go. Number 41. Calculate the displacement and velocity at times of 0.51, 1.5, and 2 seconds for a ball thrown straight up with an initial velocity of 15 meters per second. Take the point of release to be y equals 0. All right, so let's draw a ball. And there's the ball. And it's going to be thrown upwards. And eventually it'll come back down to Earth. Right? I don't know at what particular point. Depends on the conditions. But I do know that the velocity imparted on the ball initially, as the problem mentioned, would be 15.0 meters per second. Right? We'll assume that this is the ground over here. And it's going to travel a certain distance, right, or displacement. So let's just frame out the first problem. So let's say it reaches this particular point right here. So the velocity at this point would be considered its final velocity, which we don't know. And the height at which it obtained would be known as its displacement, right? Which we also don't know. Okay. Now, this is a free fall problem, meaning the ball is, the only force acting on the ball is just the force due to gravity. And therefore, we do know the acceleration. So the acceleration is going to be negative 9.80 meters per second squared, right? And in terms of letter A, we do know the time, right? So I'll put the time here. It said for 0.500 seconds, right? So now what I need to do is I need to think of relationships between my variables. I know the time, I know the initial velocity, I know the acceleration. So can we find final velocity first, maybe? And we can, right? If you notice, the first formula on the upper right has all of the variables we need. So final velocity is equal to initial velocity plus acceleration times time. So the final velocity will be equal to the initial, which was 15. It's positive because it's pointing up in the positive y direction. The acceleration, again, is gravity, so it's negative 9.80. And the time was 0.500 seconds. Okay, great. So let's just do the math here. So it works out to be 15 plus negative 9.8 times 0.5. So this works out to be 10.1, and this was really 15.0. So, yep, I'll have three significant figures. So it's going to be 10.1 meters per second. So that would be the part for part A, given the time. Okay, now we would need to look for the displacement. So here I'll do the calculation here for x. It now wants to find the displacement. Okay, so what do we need to do? We need to find another formula, right, that has this time x in it that we can utilize. So there's a couple of ways you could approach this. What might actually be, whoa, sorry about that. What might actually, I guess he's excited to do physics. What might, sorry, I got distracted. In any case, what I notice is I'm given the initial velocity, acceleration, and time. Those are given, and I want to calculate x. So what I'm actually going to choose for this is I'm going to choose the second equation. You could have chosen a different one, but the reason why I'm going to choose the second equation is because all those variables in the second equation are given to me. I don't have to rely on doing calculations and plugging them in. Like, for example, I could have used a formula that involved VF, right? It could have been number 4 here. But the thing is that I better make sure that I calculated VF correctly, otherwise my error, if I did make an error, would propagate through to the second part, which we want to try to minimize the mistakes. So let's write out that second equation, 1/2 AT squared. So the displacement is what we're looking for, right? And the initial velocity was 15.0. The time is 0.500 plus 1/2 the acceleration, which is negative 9.80, and multiplied by the time, again, it's 0.500 squared. Okay, so now the displacement will be, let's do that in the calculator. So half of 15 is going to be 7.5, right? So we don't even need to So we got that. Plus now, let's do the other part. So it's going to be half times negative 9.8 times 0.5 squared. So negative 1.23, because I need 3 sig figs. And then my displacement now, just add them together. So 7.5 minus 1.23. And it works out to be 6.27. So we got 6.27 meters. Great. That's how you would now solve a letter A. Right, so for letter B, I'll do one more, and then that's pretty much, I think you guys will see the pattern. Right, so let me change the color for letter B. It will be, so we're going to use the same 2 equations to start. We're going to use the first one to find the final velocity. So final velocity is equal to initial velocity plus acceleration times time. Right, so the final velocity is what I'm looking for. The initial was 15. Right, the acceleration is again negative 9.80 because it's the acceleration due to gravity. And now the time in this problem is going to be 1 second, right? Because that's for letter B. So just plug it into the calculator. So we get 15 plus negative 9.8 times 1. Well, that's just negative 9.8, right? So 5.2 meters per second. Okay, great. And then for the second part, to find now the displacement, we're going to use the same equation. Change in x is equal to the initial velocity times time plus 1 over 2 at squared. Okay, so again, let's write that out. The initial velocity is going to be 15. The time is now 1 second plus 1/2 negative 9.80 times 1 squared. We'll just plug that into the calculator. So we get, so this, obviously this is 15. And now this is going to be minus, so 0.5 times negative 9.8 comes out to be negative 4.9. Negative 4.90. This would be 15.0. And now just do the subtraction. So now here we go. So we got now, and this was going to be 1.00. Okay, great. So now let's do the subtraction. So we got 15. I was just checking the sig figs there. Minus 4.9. Great. So we got now the displacement here is going to be 10.1 meters. Okay, great. So that's the displacement for letter B. Now, if you notice, it's greater than the displacement for letter A. So that should make sense because there's more time that has elapsed. It hasn't reached the highest point yet. And also the final velocity was less than the final velocity of part A. That should make sense too because the higher the ball goes, the slower it gets because there's an acceleration due to gravity, pulling it back down. Number 42. Calculate the displacement and velocity at times of 0.5, 1, 1.52, and 2.5 seconds for a rock thrown straight down with an initial velocity of 14 meters per second from the Verrazano Narrows Bridge in New York City. The roadway of this bridge is 70 meters above the water. All right, so quick sketch. Here is our bridge. Okay, and the water, let's say, is down here. And the height of the bridge, it says, or the roadway from the bridge all the way down to the water is going to be 70.0 meters, right? That's essentially the displacement. Now, what's important is that we have to consider where the rock is being thrown from. So the rock is being thrown from the top of the bridge, and the rock will now be traveling right downwards. Okay? I know I curved the arrow there a little bit. I probably shouldn't have because they said it's just straight down, right? So let me move it over here. So it's just going straight down. So since the rock is moving in the negative y direction, my displacement here should be a negative value. Okay, I'm going to take this point to be the y is equal to 0 mark. All right. Okay, great. So now the initial velocity they told me, which would be representative of the beginning point, the initial velocity would be, again, negative 14.0 meters per second. It's negative because the direction of motion is down in the negative y direction. Okay, so that takes care of that. Now they want me to calculate the displacement, right, of the rock itself. Okay, so meaning, let's say in the first case for letter A, the rock only reaches this height. Right, so what I would be finding here would be the displacement of that. And I also want to find the velocity, let's say, at this particular point. That would be considered the final velocity in this context. Okay? And it also tells me the time it's going to take to get to that point. All right, and they say that the time for part A is going to be 0.500 seconds. All right, so let's see what we can do here. So for letter A, all right, we know the initial velocity. Oh, there's one thing I didn't mention, but I need to mention, right? This rock is in a free fall. So that means that we will know the acceleration, and the acceleration is always then due to gravity. That's really important. So we do know the acceleration due to gravity, negative 9.80 meters per second. So now we should have enough in order to calculate. So I know the initial velocity of the rock. I know the acceleration of it. I know the time also. And I want to find the final velocity. So do we have an equation that relates those four variables to one another? Yes, number one. Right? So let's write that down. So the final velocity is equal to the initial velocity plus acceleration times time. So the final velocity here will be equal to the initial, which was negative 14.0, plus the acceleration, which was negative 9.80, multiplied by the time, which was 0.500. Okay, very simple. So we just got to plug it into the calculator now. So negative 14, so negative 14 plus negative 9.8 times 0.5. So the final velocity there will be negative 18.9 meters per second. Okay, great. So that takes care of that. Now, we found the velocity, okay, at that particular time, 0.5 seconds after it was released. Now I'm going to look to solve for the displacement. So basically what I'm looking for is now a formula that will relate the initial velocity, the time, and the acceleration to now the displacement. And do we know of a formula? Yes, we do. The second one, right? I'm going to choose the second one because it allows me not to rely on my answer to the first part. Maybe I made a mistake and I don't want the mistake to propagate into the second part. So we have the displacement is equal to the initial velocity times time plus 1/2 at squared. So the displacement will be the initial velocity, which was negative 14.0, multiplied by the time, which was 0.500, plus then 1/2 of the acceleration, negative 9.80, times then again the time, 0.500, and that's now squared. So let's plug it into the calculator. So negative 14 times 1/2 is going to be negative 7.00, 3 sig figs there. And then now we're going to plug this into the calculator. Right? So we got 0.5 times negative 9.8 times 0.5 squared. So we get negative 1.23. I got to round to 3 sig figs. And now when I do the subtraction, it's going to be negative 7 minus 1.23. Great. So then this works out to be negative 8.23, and that is again in meters. Okay, so it's about 8 meters below the height of the bridge. Okay, wonderful. Let's take a look at B. And I think after B, you guys are going to start to see a pattern. All right? So for letter B, I'm now just, instead of calculating it for half a second, I'm now calculating it for a second. So the formulas are not going to change. All right, the only thing that's going to change is the time. So the first one I used, right, was the first equation. So that's final velocity is equal to initial velocity plus acceleration times time. So the final velocity here will be equal to negative 14.0 plus the acceleration due to gravity, which is negative 9.80, multiplied by the time of 1 second. So now the final velocity should be, so let's calculate that, negative 14 minus essentially 9.8. So negative 23.8. Negative 23.8 meters per second, and that makes sense, especially when I compare it to my first answer of negative 18, right? The rock should be traveling faster now because it's traveling downward and gravity is pulling it downward even harder. So that makes sense. Then the second part, we're going to use the same equation. Displacement is equal to initial velocity times time plus 1/2 of the acceleration multiplied by the time squared. Okay, so the displacement now is going to be negative 14.0 multiplied by the time, which is just 1 second, right? I'm just going to leave out the zeros, but keep in mind that there are 3 significant figures there. Plus then 1/2 of the acceleration, negative 9.80, times 1 squared. 1 squared. Okay, great. So now let's do the calculation. This works out to be negative 14.0. And now this will turn out to be negative 4.9, I think, 1, right? Oh no, 4.90. What am I talking about? 4.90. And now I'm just going to do that math. Okay, and when we add those two together, right, it's going to be negative 18.9 meters. Right? Now this should also make sense, but the distance from the bridge should be now getting bigger in relation to the part A. So now thinking about how to do C, and then how to do D, and then how to do E, it would literally be the same thing. Use the first equation. Okay, let me actually highlight it on the upper right. Use the first equation to find the final velocity, and then use the second equation to find the displacement. Okay, the only thing that's going to change here are the times. That's it. Number 43. A basketball referee tosses the ball straight up for the starting tip-off. At what velocity must a basketball player leave the ground to rise 1.25 meters above the floor in an attempt to get the ball? All right, so let's draw a little picture. All right, so here's Kareem Abdul-Jabbar, and he's going to jump, right, to some height, okay? Now, it tells us the height, right? It tells us that the height that he's going to jump is going to be, I'll call it x because it's the displacement, 1.25 meters, right? And he's moving in the positive y direction, therefore my displacement will be positive. Okay, so that sounds great. Now, they want us to figure out, well, at this point, as soon as he leaves the ground, what is the initial velocity at which he has to impart to himself in order to jump the 1.25 meters? Okay, so it almost sounds like we don't have enough information, but we have to make one other assumption, and we have to also make note of what the acceleration is in the problem. So as soon as Mr. Jabbar leaves the ground, right, he will now be in free fall. Okay, so what that means is that as soon as he leaves the ground and his body's floating in the air, all right, the acceleration that his body will be experiencing will be the acceleration due to gravity, which is negative 9.80 meters per second squared. So that's an important underlying fact that is not mentioned in the problem, but you must know that. So basically that has to be memorized. The other part that it's not totally clear, but it has to be the assumption, is that eventually when he reaches the top point of his jump, right, for a fraction of a second, that velocity there is 0, right? So the final velocity in this problem will be 0 meters per second. Okay, so all freely falling bodies have this, pattern to them, meaning if something is thrown upward or moving upward, it'll eventually reach a high point and then come back down. And at this high point, you will always know that the velocity here will be 0. Okay, this will be a final velocity if you're talking about this particular point here as the start, right? Assuming it travels up this way and then comes back down on that side. Okay, or it might be an initial velocity if you're considering the path from the top to then the bottom, just this half. So it depends, all right, what you want to call it. Remember, it's all relative. All right, so let's just erase that. So now, we should have enough information that we need to know in order to solve the problem. So now the question is, all right, what is his initial velocity. So here's the initial velocity, that's the question. And let's see what we're given. So we're given the final velocity, acceleration, and a displacement. So take a look at the formulas on the right-hand side. Are there any formulas that relate those four variables together? And yeah, there is, right? Number 4. Great, so let's write it down. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So final velocity is 0, so that's 0 squared. Initial velocity is what we're looking for. Then it's 2 times the acceleration, which is negative 9.80. And then the displacement, they said he jumped, right, 1.25 meters. Okay, wonderful. So this is 0 is equal to vi squared. And now this comes out to be a negative term. So let's multiply it. So it's going to be 2 times negative 9.8 times 1.25. The answer comes out to be negative 24.5. Got 3 sig figs, so that's great. Now add this on over, 24.5 to the left-hand side. That cancels, right? So now we have 24.5 is equal to vi squared. To solve for vi squared, to solve for vi, you have to get rid of the square, and therefore we take the square root. And what we do to one side, we got to do to the other. So now the initial velocity will be, so simply just take the square root of 24.5. And now remember, anytime you take a square root, the values always come out to be positive and negative. Right? So the answer that comes out here will be positive or negative 4.95 meters per second. Now think about this. In what direction is he jumping? Is he jumping up in the positive y direction or in the negative y? Right, he's jumping up in the positive y direction. Therefore, you choose the positive answer. Okay? So that part you got to think about a little bit, but not too hard. Just consider the direction of motion. Up is positive, down is negative. To the right, it's positive. To the left, it's negative. All right? So in finishing this out, just writing the final answer, it should be 4.95 meters per second. You can put the positive sign there, or you don't have to. It's implied that it's positive if the positive sign is not in. Number 44. A rescue helicopter is hovering over a person whose boat has sunk. One of the rescuers throws a life preserver straight down to the victim with an initial velocity of 1.4 meters per second and observes that it takes 1.8 seconds to reach the water. List the knowns in the problem. All right, so first let's draw a picture. So we got this helicopter thing going on over here. and my drawings are absolutely pathetic. And it's hovering over the water, right? Okay, so now what they tell us is that that someone on this helicopter throws down a life preserver with an initial velocity, right, an initial velocity of 1.40 meters per second. And they observe that it takes 1.8 seconds to reach the water. So the time to go from the helicopter all the way down to the water is a value of 1.8 seconds. Okay, great. So now what they want us to do is they want us to list the knowns in the problem. So there's one thing that's also known in the problem that's not actually stated in the problem, is the acceleration due to gravity, right? You have to realize that as soon as this life preserver is released, it's just floating in air. Anytime an object is just floating in air, you will always know the acceleration in the problem, okay? It's the acceleration due to gravity. Well, assuming the problem is on a planet, okay? Or some type of body with a decent amount of mass. So I will write in also that we do know the acceleration due to gravity, and that's negative 9.80 meters per second squared. Okay, so that works. So those are my knowns. That's what I know. Okay, what are the unknowns? Well, the unknowns would be the height, right? So what's the height difference between the helicopter and the water? I don't know. And the other variable that I don't know would be the velocity, right? At which the velocity, it looks like a U, the velocity at which this life preserver hits the water with. Okay, so those are my unknowns. Great. So now question B, part B is saying, how high above the water was the preserver released? Okay, so it looks like we're looking for the displacement, right, or the x. Okay, we know the initial, we know the time, and we know the acceleration. So take a look on the right-hand side. What equation relates those four variables together? And yeah, it would be number 2, right? So let's use equation number 2. So it'd be the displacement is equal to the initial velocity multiplied by time plus 1/2 acceleration times time squared. Okay, so the displacement will be now, be careful about how you plug in your numbers, okay? I do want to be very clear that right now that this initial velocity has to be a negative value, okay? The reason why it has to be negative is because the object is moving in the negative y direction. Okay, so anytime it's moving downward, you always got to remember to plug in the negative signs. Otherwise, or to the left, that is. Otherwise, answers are not going to come out very well. Okay, so the initial velocity is negative 1.40. The time is 1.8. I'm leaving out the units because I know I have consistency in them. I looked them over before I plug them in here, so we're good to go. Negative 9.80 for the acceleration, and the time again was 1.8, and that'll be squared. Okay, let's just do some math now. So, negative 1.4 times 1.8. So it comes out to, and we're going to have two significant figures here because of this number. So negative 2.5, all right, and that'll be now minus. So we're going to have 0.5 times negative 9.8. Times 1.8 squared, and that should work out to be right. I already put in the negative sign there, so negative 15, and we're going to have two sig figs again, so actually negative 16. Okay, great. Now when I do the math here, all right, sig figs are important. Not really, but and they're important for doing well in your test. So negative 2.5 minus 16. All right, we get a value of negative 18.5, but the value would actually be negative 19 because since this number here only goes out to the ones place, okay, and then the number here goes out to the tenths, I can only take the value with the least number of decimal places. So my number would only go out to the ones place. All right, so technically this is the right answer. All right. I didn't fully mean that significant. I feel actually a little bad. I mean the significant figures aren't important overall. They do mean something in science, but you know, I know a lot of people don't like them. Number 45. A dolphin in an aquatic show jumps straight up out of the water at a velocity of 13 meters per second. List the knowns in this problem. Okay, I'll do that. And then how high does his body rise above the water? All right, so let's take a look at a dolphin here. Okay, so here's the dolphin. Looks more like a submarine. So the dolphin is going to jump out of the water, right? And it says that essentially the initial velocity of this dolphin jumping out of the water is going to be, let me just clean that up a little bit, is going to be 13.0 meters per second. All right. And that's all it tells us, right? So now so we know that, okay? But we actually know a couple more things, all right? We just have to remember these things. So, and as soon as the dolphin jumps out of the water, the dolphin is floating in air, right? So anytime an object is floating in air, I mean, it's not really floating, it's moving, but anytime it's freely in air, okay, you will always know the acceleration. And the acceleration will always be that due to gravity, negative 9.80 meters per second squared. So that's also known. Okay. The third thing that's actually known in this problem, and the second thing that we have to kind of think about, is the dolphin will eventually reach all objects that are thrown upwards will always have this type of trajectory, right? Assuming there's nothing impeding their travels back to the starting point. All right. So what this is showing is that eventually it will reach its highest point, right? And the highest point, you always have to remember, that point will always have a velocity of 0. Okay? So we actually will know that in this problem. Okay, and that's actually an important thing to know, that the highest point, and I'll write this down, the highest point is the point, right, in which the velocity is 0. Okay, this is for, right, free fall problems. For free fall. Okay, so I know that once the dolphin reaches, let's say, this point here, it's going to start moving back down, and therefore I know that the velocity of this dolphin must have stopped for a split second. So the velocity would be equal to 0 meters per second. And if I say that this is the initial down at the bottom, then I know that this has to be the final. Okay, wonderful. Great, so I think I have everything I pretty much need or whatever. And now it says discuss blah, blah, blah. Okay, let's move down to, I still have to solve how high, right? So we have to solve for the displacement essentially, correct? So I'm thinking of a formula that I need, that will relate, I should say, the final velocity, the initial velocity, the acceleration, and the displacement. So which one on the right-hand side will do that? Right, equation number 4. Okay, so let's write that down. So this is part B. So we got the final velocity squared is equal to the initial velocity squared plus 2 times a times x. Okay, final velocity we're going to assume is 0 because it wants to know how high, and we know the highest point is at the point in which the velocity is 0. So the initial velocity is 13, and that's going to be squared, plus 2 multiplied by the acceleration due to gravity, negative 9.80, times now my displacement, which is what I'm trying to solve for. So let's clean it up. Let's do some math. So square the 13. Okay, that works out to be 169. That's 3 significant figures. Okay, then this is going to be minus now. So 2 times 9.8, right, which works out to be negative 19.6. That's 3 sig figs, and that'll be x. So add this on over to the left-hand side, 19.6x. Right, so what do we get down here? So now we get 19.6x equals the 169. Now all we have to do is just divide out now the 19.6. All right, so I'll write it a little neater over here. So let's write 19.6x is equal to 169. And now just divide out the 19.6, right? Divide out the 19.6. So my x value will now be 100. Uh-oh. He really likes to do physics. Every time he can't get in here, he always cries. He's such a good boy, though. And then most people cry when they have to do physics. He cries when he doesn't. I don't understand it. I cry when I have to do physics. Anyway, so the x value here, the displacement will be 8.62. All right, and that is in meters. So that's how high that the dolphin will actually jump. All right, he's going to jump about 8.5 meters out of the water. All right, and now, so for part C will be to now find how long the dolphin is in the air. All right, so what we're doing now is we're looking for time, right? We need to solve for time here. So what I want to do is I want to think, do I know an equation that relates time, initial velocity, acceleration, and final velocity? And I do, right? It's the equation at the top. So the final velocity will be equal to the initial velocity plus the, well, actually why he's crying because it's bedtime. But I like to think it's because he wants to do physics. So in any case, so we have our formula. So let's start plugging things in, right? 0 is the final velocity. The initial velocity will be 13.0. The acceleration is due to gravity, negative 9.80. And then multiplied by the time, which is what we're trying to find, right? So let's clean it up. 13.0 minus 9.80t, right? Add the 9.80 to both sides, right? So add that to this side as well. And that's t, right? So that cancels. Oh, man. So now this gives me 9.80t is equal to 13.0. Divide out that 9.80 now. Divide out the 9.80. And now the time then just simply becomes, so take out your calculator, do 13 divided by 9.8. And when we get the answer we get there is going to be 1.33. We're going to have 3 significant figures, and that's in terms of seconds. So that'll be the total time that the dolphin is in the air. Number 46. A swimmer bounces straight up from a diving board and falls feet first into a pool. She starts with a velocity of 4.00 meters per second, and her takeoff point is 1.8 meters above the pool. Letter A. How long are her feet in the air? So in terms of how long, what they're asking us for is a time. All right, so how long in terms of seconds are her feet in the air? All right, so we're looking for time. So let me just write that over here. So we're looking for time. And as you can see, I drew the picture already. So here's the swimmer. I'd say he looks like Michael Phelps, but that's just me. So there's a swimmer. His height above the diving board is 1.80 meters. And he is leaving the diving board at a velocity straight up of 4.00 meters per second. So we want to know how long are his feet in the air. So if we had to frame out the problem, we would want to be thinking about, well, what is the initial point of the problem and what would be the final point? Well, his feet are in the air this whole path, right? So that being known, this would represent the initial point, and then this would represent now my final point. Okay, so if this is my initial point over here and this is my final point, let's label some things that we know and some things that we don't know. So we do know the velocity at the initial point, right? We do know that that velocity is 4.00 meters per second. So let's write that down, 4.00 meters per second. We also know the displacement, correct? Now the displacement is the difference, right? If you remember the change in displacement, I'll call it y here, since we're dealing with a y problem essentially, right? It's a vertical problem. It's a free fall problem. So remember, change in displacement is simply the final value, right, minus the initial value. So the displacement of the final value minus the displacement of the initial value. So what I'm looking for is I'm looking for the difference between this point and this point in terms of the height. And that was actually given to me already, right? That was given to me in the form of 1.80 meters. Now the thing is, if he's starting high and ends low, that number will be negative. If he were to start low and end high, that number is positive. So I do know that this value right here should be now negative 1.80 meters. Great. I don't know the final velocity. The final velocity would be the point here at which he hits the water. I don't know what that is yet. And what's another variable? Also the acceleration, right? We have to remember that that is in the y-axis, and therefore, since this is a free fall problem, it should be negative 9.80 meters per second squared. Now let's think. Given the facts that we know the initial velocity in the y direction, right? We know the displacement in the y, we know the acceleration in the y, and now we're looking for time. Do we know a formula on the right-hand side that relates those variables? And we do, right? The upper right-hand side, equation number 2, fits the bill. So let's actually write that down. So the change in the displacement, I'm just going to, instead of using x, I'm going to call it y, is equal to the initial velocity in the y direction multiplied by time plus 1/2 of the acceleration in that y direction times time squared. So this should be now negative 1.80 is equal to the initial velocity in the y direction, which was positive 4.00. Why is it positive? Because it's pointing upwards in the positive y direction, times time plus 1/2 negative 9.80 times time squared. Great. So let's just clean this up a little bit, right? We get negative 1.80 is equal to 4.00 t. Then this would now be minus 4.90 t squared. And I already start to begin to realize I'm probably going to have a quadratic here, right? I got a squared term, I have a non-squared term or raised to the first power, and then I have a constant over here. So realizing that, what I want to do is I want to try to put this into a form where I set the equation equal to 0. So what I will do here is I will add this term on over to the left, all right? And I'm also going to then subtract this term on over to the left as well. All right, so what that will give me now, that'll give me a positive 4.90 t squared minus 4.00 t, then minus 1.80, now that equals 0. The reason why I do this is so that I can find my coefficients, right? If I know this is in the quadratic form, this is my a value. This right here, including the negative, is my b value. Now that's my c value. So what we would look to do is, if you don't have a program on your calculator, you're going to have to go about it the old-fashioned way. That, well, it's x equals, right, but my variable here is t, so we'll call it t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So you just plug in your b, your A and your C, and you're all done. You just plug it in, and then you get two answers, right? One, you'd have to add the two terms in the numerator, and the other one, you would have to subtract the two terms. Instead, what I'm going to do is I have a program on the calculator. I'm just going to plug in the A, B, and C value. I have a TI-84, and if you wanted to know how to do that, maybe we'll put out a video in a little bit, or you can just search it online. It's pretty easy, but it's very handy. So the A value is 4.90, the B value is -4, and the C value is -1.8. So you're going to get two answers because it's a quadratic. Well, not all quadratics, by the way, have two answers, but usually these will give you two answers. So I get T is equal to 1.14 seconds, and then I also get T is equal to -0.323 about. Just always disregard the negative times. I'm starting time at 0. So if I'm assuming right the clock starts as soon as the as soon as the swimmer jumps. So that being the case, I can always get rid of the negative time because it won't make any sense. So I have a time value. So this is how long his feet will be in the air. So that takes care of letter A. All right, so now let's take a look maybe at letter B. So now it says, B, what is her height? I guess it can't be Michael Phelps then, right, if it's a her. So what is her height, highest point above the board? So basically now what they're asking us is, if in terms of my picture, right, they want me to find the difference. Hold on, what is her highest point above the board? So that's the important term, above the board. It's relative. So what they want me to do here is they want me to find the height difference between this point and, if I were to dot a straight line down, this point. Okay? Now it's important to note that because this will tell you what your initial and final conditions should be. For example, I can say that this is my initial set of conditions, and this would now be my final set. No longer is my final when the swimmer hits the water. Okay? So now let me just backtrack here, make it nice and neat. So right here now, this is going to be my new final value. Okay? So let's see if we can write down some knowns and unknowns about that new frame. So again, the initial velocity in the y direction, it's still the same, right? It's 4.00 meters per second. That hasn't changed. The acceleration, since this is a free fall problem, that's still the same. It's 9.80 meters per second squared. Right? The displacement in the y direction is what I'm trying to find. I don't know what that is. That's what we're looking for. The time, I also don't know the time here, right? That's equal to 0. Not equal to 0. That's equal to some value, but I don't know what it is. And what about the final velocity in the y direction? So remember, this point in your picture is really important. That's the point at which the object stops going up and just begins to come back down. What does that mean? That means for a split second, the velocity is 0, specifically in the y direction. So I actually know this piece of information is 0 meters per second. Now what I'm going to do, I know I want to find my displacement. I know the initial velocity, I know acceleration, and I know final velocity. So now pick one of the 5 formulas on the upper right-hand side. Looks like we're going to go with number 2. So let's plug that in. So we got final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. And instead the displacement I'll just put as y. Okay. So the final velocity is 0. The initial velocity was 4.00, and that's squared, plus 2 times the acceleration, -9.80, times now my y. Great. So this is 0 is equal to 16, right? Minus now 19, minus 19.6y. Add the 19.6y to the other side, so then we get 19.6y positive now is equal to 16. Simply now divide out the 19.6. And now y will equal, let me give myself a little more space. So y will equal 16 over 19.6. And the y value now comes out to be, and it's positive, which it should be. Why? Because remember, you're starting low and ending high. Okay. All right, so 0.816, and that is in terms of meters. So wonderful. Part B is done. Now let's move on to part C. What is her velocity when her feet hit the water? So remember, what's the frame? Where's the initial? Where's the final? So the initial I'm still going to consider at the beginning of the problem. All right, and the final velocity I'm going to now talk about when she hits the water. All right, so those two red circles represent my frames. So now let me write C on over here. Let's list what we know. The initial velocity is going to be the same, 4.00 meters per second. The acceleration is still the same because it's a free fall problem, so negative 9.80 meters per second squared. What else we got? We're looking for the final velocity, so that's our unknown. We do know the time because we just calculated that before over here, right? So that, and it was in the same frame, so that means it should be the same time. So 1.14 seconds. And I also know the displacement, right? The displacement was the same as in part A. It should be negative 1.80 meters. Okay, so what I want to do is I want to find final velocity. I know the initial, I know the acceleration, and what I'm actually going to do, I could choose either one with time or one with the displacement in it. I'm going to choose one with displacement because that's what was given. I'd rather not use one with time if I can help it, because I don't want, in case I made an error here, I don't want it to propagate now into my third part of the problem. All right, because then I get two wrong instead of just one. So let's now look for one of those equations. So it looks like equation 4 here is going to fit the bill. All right, so let's do that. So we got final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So we got the final velocity squared, which is what we're looking for. The initial velocity is 4.00, that's squared, plus 2 times my acceleration of negative 9.80, multiplied by the displacement. I just have to put it down here slightly because I'm running out of room. Negative 1.80. So now we get the final velocity squared should be equal to, so let's just do the math there. So 4 squared is 16, and then 16 will now be added to 2 times negative 9.8 times negative 1.8. And we get a value of 51, right? 51.3 when we take it all into account. So 51, hold on one second, 51, make the 5 a little neater. And that was less neat. There we go, 51.5, excuse me, 0.3. And again, to find just the final velocity, I got to get rid of the square. So therefore, now I'm going to take the square root of both sides. So now the final velocity here, when she hits the water, so take the square root. Now we get 7.16, but remember, anytime you take a square root, you get both the positive and the negative answer. Okay, so it's going to be positive, negative 7.16. That's meters per second. But what should the answer be? Should it be positive or negative? Focus on her direction. What direction is her velocity moving in? Is it moving up or is it moving down? If it's moving down, that means it's in the negative y direction, and that means the velocity should be negative. All right, so let's just go back. Let's just erase these two signs now, and let me put in the right one of negative. So that would be the final velocity, negative 7.16 meters per second. Number 47, letter A. Calculate the height of a cliff if it takes 2.35 seconds for a rock to hit the ground when it is thrown straight up from the cliff with an initial velocity of 8 meters per second. All right, so let's just draw a picture. So here's our rock. It's going to be thrown up, and it's probably going to come back down something like this. And let's assume that this is the cliff right here. Okay, and the ground will be obviously below that over here. So now it says that calculate the height of the cliff, right? So we're essentially looking for this variable right here, right? We want to find the height of that cliff. If it takes 2.35 seconds for a rock to hit the ground. Okay, so that time is the time between when the rock leaves the cliff all the way down to when it hits the ground. So this whole arc represents, or the time of that whole arc is 2.35 seconds. All right, so I'm just going to write that here. Time is 2.35 seconds. And then it also says that the rock is thrown up at an initial velocity of 8 meters per second. Okay, so we know that going straight up here, the initial velocity is 8.00 seconds. Meters per second. Meters per second. All right, so on these free fall problems, especially when the heights of the starting point and the ending point are at different heights, I like to think about this in two parts. All right, I'm going to divide the parts right in the middle of where the height is the maximum. Okay, so the part to the left-hand side will be considered part A, and the part to the right-hand side will be considered part B. Part A and part B are connected, well, they're connected via time, but they're also connected by this point, the highest point. There's something special about the velocity at the highest point, and it will be 0 meters per second. Now this point would be considered the final velocity of part A, because this is the initial, right? And then, considering for part B, that same point becomes the initial of part B, because part B is starting at the top and it's ending at the bottom. Okay, wonderful. So now it's asking us, what is the, calculate the height of the cliff. All right, so we're looking for this. So let's first try to, I think the first best step would probably be to try and find, the only thing we can really do is if we think about this, if I am considering part A, then I'm going to call this my final velocity now. And I know the initial velocity, I know the final velocity, and remember, we also know the acceleration in this problem. It's always going to be, since the object is in free fall, negative 9.80 meters per second squared. So that's always going to be the acceleration. So, do I know an equation that relates those 4 variables that I just circled? Yes, right? If we look at the top equation, yeah. Right, sorry, no, not the top one, the 4th one. I mean, I could use that to solve for time, but I want to solve for the displacement. So let's use that one. So this is for part A here. Let's say that the final velocity of part A squared is equal to the initial velocity of part A squared plus 2 times the acceleration times the displacement of part A. Okay, final velocity was 0. Initial velocity was 8.00, and that's squared, plus 2 times A, which is negative 9.80, and times the x, right? So this should work out to be 8 squared is 64. This would be, this is now negative 19.6. I said negative 19, right? But I wrote 16, negative 19.6x. Add the 19.6x on over to the left. And now I think you can see how to solve this. 19.6x will be equal to 64. I really should have 3 sig figs there, so there should be a 0.0. And now just divide out the 19.6 from both sides, right? So when we do that, let's just plug it into the calculator, 64 divided by 19.6. And we'll have 3 significant figures, so 3.27. So 3.27 meters. Okay, great. So that is about, that is how high the rock will be thrown up, okay? So it's going to, from this point of the cliff to now this point, okay? It rose up 3.27 meters. Okay, so now when thinking about how to answer the question, if I can just find the total height, right? If I could find now the total height from the highest point all the way down to the lowest point, then what I can do is if I find that, I can subtract this piece out to get this piece, right? So that's basically what we're looking to do, all right? So now, how do we go about this? Well, I don't know anything about the height yet of the cliff, so I can't really calculate anything for part B yet. I don't know the final velocity. I don't know how high it is. I don't know much. I know the total time though, right? So now the next step will involve the total time somehow. What I want to do next is I want to now calculate the time it takes to go from the cliff all the way to the highest point. Because then if I can find that time, I can subtract that from the total time. And then that will tell me the time of just part B. And then if I know the time of part B, I can then finally calculate probably the total height. Okay, so that's my next step. So now for part A, I want to calculate time. So if we look on the upper right-hand corner, I'm going to use the first equation. Okay, so the final velocity is equal to the initial velocity plus the acceleration times time. Final velocity of part A again was 0. The initial velocity of part A was 8.00. Right, the acceleration is still the acceleration due to gravity. And now I just want to find time. So add the 9.80 t to both sides, add 9.80 t, cancels, right? Now we have 9.80t is equal to 8.00. Divide out the 9.80. And now t will equal, so 8 divided by 9.8. And that works out to be, 8 divided by 9.8. And that works out to be 0. And we'll do 3 sig figs, 816 seconds. And remember, that's the time for part A. Okay, so now let's consider now the total time that I have, right? And let's remember that the total time of this problem, since I broke it up into 2 parts, the total time would equal the time it takes for the rock to go from the cliff to the highest point, which would be part A, plus then the time it takes to go from the highest point all the way back down to the water, that would be time B. Now the total time was 2.35 as they mentioned in the problem. The time for part A I just calculated to be 0.816. And now I'm going to be looking for B. So simply just subtract this out. And that's what we were saying before, right? So we can see how the math works. 0.816. That cancels, leaving me with now, make a big T, a little b, and we get 2.35 minus 0.816. And it comes out to be, and we need 3 sig figs again, 1.53. So 1.53 seconds is the time for now part B. Okay, now that's an important finding because now I do know the time it takes, looking back at the picture, I know the time it takes to go from the top now to the bottom. And if I know that time, I actually will be able to now finally find the big displacement here of part B. Okay, so let's write our knowns. All right, let's write the knowns. And actually, I'm just going to change the color here so we can follow maybe a little better. So now I'll write the knowns right here. So this is all for part B. Okay, so I'll write, we know the initial velocity of part B is going to be 0 meters per second, right? Because it's starting, remember, part B starts at the top. We don't know the final velocity of part B. That's fine. We don't need to. We don't know what velocity it hits with. We do know the time for part B. We just calculated 1.53 seconds. We always know the acceleration because it's in free fall. And we don't know x, right? So I have to find a formula that relates now these 4 variables. Which one does that? Well, looks like the second one will be a good candidate, right? So let's choose that. Okay, so I'm going to do the work now. Let me just box this in a little bit. I'm going to do the work right on over here. So let me write out the formula. Change in displacement is equal to VIT plus 1/2 AT squared. Displacement is what I'm looking for. Right, the initial velocity was 0, so who cares what the time is? That whole thing's going to go to 0. Plus 1/2 times the acceleration, negative 9.80, times time multiplied by time squared, and we know the time is 1.53. Okay, great. So now just throw it into the calculator. So we get 0.5 times negative 9.8 times 1.53 squared. So this works out to be negative 11.5. 3 significant figures, and this is in meters. Now, it should be negative, okay? Don't be concerned, you calculated it correctly, but it should be negative. Why? You got to consider where the object started and where it ended. It started high, ended low. That's always going to be then a negative displacement, negative velocity, negative acceleration, all that stuff, okay? Because it's traveling in the negative y direction. Okay, so we're almost there. I just found the total height from the highest point all the way down to the lowest point. So now how can I finally find the height of my cliff? Remember, I also know this height of part A. Right, so we can probably come up with a simple formula here saying that I'll say the total height, right? The total height was equal to the height of the cliff. So I'll say x of cliff, right? I'll put a little c there. So the x of the cliff plus the height of part A. So the total height we just found. And here's the thing. you got to consider the signs because in this particular case now, I would actually just be taking the absolute values, okay? Because I'm not thinking about it in terms of physics anymore. I'm just thinking about it in terms of math, all right? I am just setting up a simple relationship between them. So it's very important to just think about this in terms of absolute values, all right? And also, I mean, it should make intuitive sense. If you calculated, right, if you left it negative, if you plugged this in and left it negative, your answer is going to be pretty far off. The A would be larger than the total, which wouldn't make any sense. Right, so always just double check and make sure it's making sense. So 11.5 should be equal to then the x of the cliff plus 3.27. Right, so minus the 3.27, and this is what we expect it to look like. So the height of the cliff, finally, is going to be 11.5 minus 3.27 and 8.23. So we get 8.23 meters. Great. So this is now the answer to part A. Thank goodness. A lot of steps here. A lot of parts, a lot of steps. It almost seems like we don't have enough information, but we do, and we just have to piece it all together. So let's take a look now at part B. Oh my God, this is one of those that seems like it won't end, but it will. So letter B, how long would it take to reach the ground? All right, so how long would it take to reach the ground if it is thrown straight down with the same speed? Okay, so this problem becomes a little easier actually, because if you, I'm going to draw it over here. Let me just box this area in a little bit over here. So let me just draw what they're talking about now. So here's the cliff, okay, and remember the cliff height now. We know what it is, but the cliff height is going to be this part right here. It's going to be 8.23 meters. Okay. The rock now, instead of it being thrown up and coming down, it's just going to be thrown straight down. So we don't have essentially two parts of this problem anymore. It's going to hit the ground beneath it. And it says that it's going to be the same initial velocity. So I know that the initial velocity here is going to be, now got to be careful with the sign, it's going to be negative 8.00 meters per second. Before, if you look back to the other picture, it was positive. Why? Because it was traveling in the positive y direction. Why is it negative now? Because it's traveling in the negative y direction. Okay, so we know that. We know that the acceleration is negative 9.80 meters per second squared. Because the body is in free fall, that's always the acceleration. And what we're looking for is we're looking for time, right? So remember that this value right here that I wrote before the displacement is my x value. Just be careful when you start plugging it in that you have it be a negative number. Okay. And so the question now is, do I have enough information to solve for time? And I think we do, right? Look for a formula that relates displacement, acceleration, initial velocity, and time. And you will come up with the second equation here. So let's write that down. So the change in displacement is equal to the initial velocity times time plus 1/2 acceleration times time squared. So the displacement is negative 8.23. Now, if you miss the signs here, it probably is going to come out wrong, so you got to be very careful. The initial velocity is going to be negative 8.00. Actually, I'm just going to write 8 because I'm running out of room. All right, so I'm not going to really consider significant figures, but so it's going to be negative 8t, right, plus 1/2 times negative 9.8 t squared. So let's clean it up a little bit. Negative 8.23 is equal to negative 8t, right? Minus now 1/2 times 9.8, so this should be 4.9 t squared. Now, how do you solve this thing? Well, it has the feelings of a quadratic, right? So what I like to do is, in order to solve quadratics, we got to set it equal to 0. I always like to have a positive coefficient, a positive a. So I'm going to subtract this, I'm going to add this value on over to the left, and I'm also going to add this value on over to the left-hand side. All right? So when I do that, the negative 4.9t squared becomes now 4.9t squared. The negative 8t becomes a positive 8t, and then it's just subtracted by 8.23, and that will equal 0. So from here now, here's my a value, here's my b, and here's my c. Okay, and also include that negative sign with it. You probably have to use the quadratic equation here, which would be that t would be equal to 1/2. No, not 1/2. What am I talking about? T is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Almost sounded mechanical there, right? That's because it was beaten into my head long ago. So you can use that formula, plug everything in, and you'll be able to solve. But what I'm going to do is I have a program in the calculator, and you can, I think, find resources online to figure out how to program the quadratic in your calculator. It's pretty neat. So all I got to do is type in 4.9, 8, negative 8.23, and then I hit solve. And there's two answers that will get spit out, so you should get two answers here. So time is either going to be 0.715 seconds, or the other answer is negative 2.35 seconds. So which one makes sense? Remember what I was talking about before. The negative ones don't make sense. Okay, only the positive answers in terms of time will make sense, assuming you're starting at time 0, which we are. All right, so you get rid of this. So the positive answer is the answer now. So this should be now the final time, or the total time it would take for the rock to travel from the top of the cliff all the way down to the ground below, and traveling at the initial velocity of negative 8 meters per second. All right, so notice how the time is significantly less than the time for part A. Right, the total time for part A was 2.35. Now we're talking about 0.175. So the answer sounds reasonable. Might there be a slight error in there? Who knows? I mean, maybe, but I don't think so. But I always do a double check at the end, make sure the answers sound reasonable, and it does. He's going to actually, let me extend his arm a little better. Let's say he's going to shot put all the way up here. Okay. I'll go a little longer. There we go. Okay, so he's going to extend his arm all the way up here, and he's going to shot put it. He's going to put it on up, so it travels straight up, and then it's going to eventually come back down. Let's say it comes back down this way, right? Because it wants us to try to find. He has to get out of the way, right? So we've got to figure out how much time he has. So instead of it coming down on his head, we have to figure out how much time he has to get out of the way. So it says that he imparts an initial velocity here of 11.0 meters per second. We also know, remember, that the highest point here will have a velocity of 0 meters per second. That's important. We always know, since this object is in free fall, that the acceleration is the acceleration due to gravity, negative 9.80 meters per second squared. And we also know a couple of things about the height, right? So they're giving us the heights relative to the ground. So we know that the shot putter's height, says here, is 1.80 meters. Okay. We also know that he releases the ball, we'll say right from the bottom, all the way down, will be 2.20 meters. Okay. So just with that information alone, it might be beneficial to try to calculate here, right, the height differential between these 2 points. Okay, so how do we do that? Simple, right? Just do a subtraction, 2.2 minus 1.8. So it works out to 0.4. So the height in here is going to be 0.4 meters. All right. So now so whenever I have a problem like this in free fall where the object goes up and then it comes back down, I like to think about this in two parts. Okay, first part is going to be from his hand to the top point. All right, I'll label that as part A of the problem. The second part of the problem I'm going to label as part B, and that's going to be from the top point on down, okay, to the bottom. I think that should be good. So that'll be part B. I may actually have to wind up breaking this further down into maybe a part C, where I cut B off at this point and then call the remainder here part C. But we'll see as we go. All right, so let's just think about the second part there as part B. All right, so now we have to figure out how much time does he have to get out of the way. So basically we're looking for total time. Okay, that's what we're looking for. So we're looking for total time. Now total time will be equal to the time of part A plus the time of part B. Okay, if I further subdivide part B into, let's say, part B being up until this point and then this being part C, all right, it would just look something like this then. Total time would be equal to time of part A plus time of part B plus time of part C. I don't know which one I'm going to choose yet. We'll see as we go. All right. So let's take a look now at what I can solve for in terms of part A. Now part A, I know the initial velocity, I know the acceleration, I know the final, and can I find time then? Yeah, we can, right? Because we know an equation that relates those three variables, the first one at the upper right. So let me write that down. So the final velocity is equal to the initial velocity plus the acceleration times time. Final velocity is 0. Initial velocity is 11.0, and it's positive because it's moving in the positive y direction. The acceleration is then negative 9.80, and the time is what we're looking for. So add the 9.80 to both sides. That cancels. Now we have 9.80t is equal to 11.0. Simply divide out the 9.80 from both sides, and now we're going to find the time. Okay? So now it's going to be 11 divided by 9.8. So it comes out to be, we'll do three significant figures, 1.12 seconds. All right. So that's the time it takes to go from his hand all the way to the top point. All right. So that's the time of part A, and I'll put a little a here. Okay, so in terms of my formulas over here on the left, I just found this part. I just found this. Okay, that means that if I want to find the total time, right, I need to focus now on finding the time for part B. And if I can do that, I just add them together. So the question to myself now is that I'm asking, how do I find the time for part B? Well, I need to essentially know some other information, right? I can't just find it right away, because if I'm thinking about my part B, all right, all I know is that the initial velocity is 0. And I know that the acceleration is still negative 9.8. I have no idea what the velocity is like at the end, nor do I know what the distance this object has to travel in full. So I can't even solve for time yet. Okay, but that's my goal. But wait a minute, maybe if I can find the total distance here, then I can find the time. Yeah, I can do that. Well, now how do I find the total distance from the top of part B all the way down to his head? Well, we already know this little piece, right? That it's 0.4 meters. But wait a minute, how does this connect to part A? Well, if you notice, right? Let me just backtrack. This piece right here would be the displacement of part A. And if I can take that, look at the symmetry here. That's the same as this distance, right? So if I can find the displacement of part A, I'll know part of the displacement for part B. And then I can simply add this little piece that I found over here to that. So then I can find the total displacement of part B. Okay, that's my approach. So let's just backtrack. All right. Let's now take a look at then finding. So this was finding the time of part A. Now let's find the displacement of part A. So let's take a look at the formulas. What are we going to use? Looks like the fourth one is going to be a good one to use. All right, because we know all those variables for part A. So the final velocity squared of part A will equal the initial velocity squared of part A plus 2 times the acceleration of part A. Let me not put in the numbers yet, times the displacement of part A. So the final velocity in part A, remember, was 0. The initial velocity was 11.0. That's squared. Plus 2 times the acceleration, which we said was always going to be negative 9.80 because it's in free fall. And now finally multiplied by x. So what do we get here? 0 is equal to 121 plus, well, it would be minus, right? Minus 19.6x. Add the 19.6x to both sides. Great, that'll cancel. Now what I'm left with is 19.6x. That will equal 121. Simply divide out then the 19.6. And now x will equal, so take out your handy dandy calculator, 19.6. And the displacement here works out to be 6.17 meters. Okay, perfect. So now I just found the displacement here in my picture. So I know that that displacement will also be the same as this displacement. So how do I then find the total displacement of part B? I have to include this little area, not area, that little length. So I'm going to be taking this length into account, right? So I could say this, I'll make a little formula over here on the right-hand side, that the total, I'll say, let me do this. The total displacement of part B, okay, should be equal to the displacement of part A plus 0.4, right? That should make sense. So the total displacement of part B should be now equal to the displacement of part A, which we just found. So we can plug that guy on in. So 6.17 meters plus 0.4 meters. All right, we're getting somewhere, I think. So now this, when we do the addition here, this becomes 6 point. Now I should have went out two significant figures here in terms of my math before. So it should be, we'll have 3 in total in this problem. So it should be 6.57 meters. Okay, so that now is the total distance of part B. So remember that this is this whole distance from the top down to his head, from the top down to his head. Okay, that's very important. So now, let me now shift my focus to finding finally now the time of part B. Okay, so let me change the color here. And what I'm going to do now is I'm going to write the knowns for part B. Okay, the initial velocity of part B is 0 because I consider part B as the top, the highest point, and we know the velocity is always 0 there. The acceleration for part B is the same, negative 9.80 meters per second squared. We know now the displacement of part B. Now you just have to be careful here, okay? The value I found before in terms of the distance or the height or the displacement, whatever, of part B, which I just found to be 6.57 meters, I'm just considering that to be a positive number because I'm just trying to find the actual length. But now once you start plugging these values into physics formulas, you have to be very cautious of the sign. So just remember, since the object is starting at the top, okay, and traveling down in the negative y direction, right, is going down, your displacement has to be negative. So this is a negative 6.57 meters. That's definitely where I see most students have trouble. So just, it's the signs in physics and it's the framing that's really difficult. So make sure you understand that. So, okay, great. So I have all those pieces. Now I'm looking for time. Okay. Do we know a formula that relates these 4 variables to one another? Yeah, right? Take a look at equation number 2 on the upper right. That looks good. So let's see. Let's write it out. So the displacement is equal to the initial velocity times time plus 1/2 the acceleration multiplied by time squared. The displacement here is negative 6.57. The initial velocity is 0, right? So that whole thing just goes to 0. Plus 1/2 of the acceleration, which was negative 9.80, multiplied by time squared. Okay, so negative 6.57 is equal to 1/2 of negative 9.80, which should be negative 4.9, right, t squared. And now divide out the negative 4.9. And now this is where, really should be a 0 there in terms of sig figs. Now this is where you won't get the magnitude will be right, but the sign would have been off if you forgot to put this negative sign there. All right, because now my answer works out to be positive, right? So when I take negative 6.57 divided by negative 4.9, it comes out to be a positive 1.34. And then I can take the square root of that, right? We can't take square roots of negative numbers, so it wouldn't have worked out. The magnitude would have been fine, but it just wouldn't make any mathematical sense. So now when I take the square root of 1.34, I get a value of 1.16. Now remember, whenever you take the square root of a number, it's plus and minus, okay? So it's plus and minus 1.16 seconds, but only one of them makes sense. Just the positive answer will make sense. The negative answer will not make any sense because we don't have negative time in this problem. We're starting at time 0. All right, so what I'm going to do is I'm just going to erase the negative sign down here. All right, and that will be my answer for time. Okay, so this is now the time, don't forget which is the time for part B. Now, I know the time for part A. Let me box them in. Here's the time for part A. Now I finally found the time for part B. So how do I find the total time? Right, we use our formula that we came up with over here first. Right, so the total time is equal to the time of part A plus the time of part B. So the total time in this problem will be equal to 1.12 seconds plus 1.16 seconds. And that should make sense, right? If you think about it, the time for part B should be slightly longer than the time for part A, right? Because it had to travel, this ball had to travel just past where it started. It had to travel this extra little distance of 0.4 meters, right? So everything's sounding pretty reasonable to me at the moment. So I think we're on the right track. So the total time now, you don't even need a calculator for this, but you can just double check. So it's going to be 2.28 seconds. And that will be the final answer now. So this is how much time the very strong but inept shot putter has to move out of the way. Hopefully he's not that inept where he can move out of the way that quickly. Number 49. You throw a ball straight up with an initial velocity of 15 meters per second. It passes a tree branch on the way up at a height of 7 meters. How much additional time will pass before the ball passes the tree branch on the way back down? Okay, so let's try to sketch a picture. Now this is one of those problems where the, where the framing is going to be really important of the problem. So there's going to be a ball, it's going to be thrown upwards. So let's just detail the ball here. And it's thrown upwards with an initial velocity of 15.0 meters per second. And on the way up, it's going to pass this tree branch, right? So let's just say the tree branch is here, okay? So it's going to pass the tree branch. Okay, so it's going to look something like this then. And I'm sure eventually it's going to reach its highest point and then come back down. Right? So this is the tree branch. So what they want us to calculate, now, by the way, it also tells us that the height of the tree branch is 7 meters. Now, it doesn't say, well, 7 meters with respect to what? But I have to make an assumption that it's 7 meters with respect to the ball. All right, so the height here, all the way down to the ball, is going to be 7 meters. Okay? That should be a safe assumption. So what they're trying to say is they want to now know how much additional time will pass before the ball passes the tree branch on the way back down. So essentially they want us to find, the question's a little vague, but I believe what they're looking for is they're looking for us to find the time between the time when it passes the branch on the way up and the time when it passes the branch on the way down. So they want us to find this time, okay, that I just outlined. This is the time they want. All right. So now, if that's the time that they want us to find, notice how there's some symmetry here, meaning that the point at which what are they throwing? A ball. The point at which the ball passes the tree on the way up will be symmetrically the same as the point in which the ball passes the tree on the way down. So this is an important fact, because basically what I'm going to think about here is there's essentially Well, I can think of this as two parts. All right. So I was going to say 3 parts. I could break it up into 3 parts if I'd like, but I'm just going to do 2. All right. So the 2 important parts of this problem are this. The first part here will be from the time the ball is released to this particular point right here. Okay, I'll call that part A of the problem. And then part B of the problem will be this symmetrical loop that it'll make. Okay, so I'll consider that now part B. All right, so first, let's talk about part A. Okay, so let's label some things that we know for part A. Well, we know that the initial velocity for part A was 15.0 meters per second. Right. We also know that the acceleration due to gravity is going to be negative 9.80 because the ball is in free fall. We also know that the displacement that ball is traveling is going to be 7 meters. Right. So the x value, that's not a negative sign, but the x value is 7 meters. And specifically, it should be 7.00 meters. Right. It's positive because the ball is moving in the positive y direction. That's basically all I know, right? My unknowns then are the time it takes to go from essentially where the ball's starting to then this point. And I also don't know the final velocity here, right? Which would be the velocity at this point right here. So the final velocity, okay? That's a question mark. But this is the important one to find. Why? Because the final velocity of part A is going to be the initial velocity of part B. That's how the 2 frames are connected. Okay? They're connected via the velocity. And you're going to see this pattern come up a bunch. If you watch some of the prior videos, the questions are hard. They're all connected basically via this idea of the final velocity of one part is the initial velocity of the other. That's how we can jump frames. So, this is what I'm going to be looking to solve for, my final velocity for part A. So I know the initial acceleration and the displacement. I want to find the final velocity. So what equation are we going to use on the right-hand side? Yeah, it looks like the 4th one would be the best one. So let's write it down. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity, I don't know what it is. Let's leave it as the variable. The initial velocity is 15 meters per second, so 15.0 squared, plus then 2 times the acceleration, negative 9.80, times then the displacement, and it said it's going to be 7 meters, right? Okay, so let's clean it up. Let's do some math. So I think this 15 squared is 225, but never be too sure. Yeah, check the calculator. 2.25, and the second part now, just plug that into the calculator. It's going to be 2 times negative 9.8 times 7. Works out to be negative 137. And I got to have 3 sig figs, so that looks good. And now I just have to do the subtraction here. So the final velocity squared would be 225 minus that answer. So this works out to be 87 point, well, not point, but 88, right? 88. Okay, and this is, it's only 2 sig figs because both values go out to the ones place. And then I just have to take the square root of that. The final velocity of part A, I'll call it, is square root of 88. So 9.38. 9.38 meters per second. And remember, the important fact now is that this is also equal to the initial velocity of part B. Okay, this is how the 2 frames are connected. So now, and actually, let me change the color here. I'll say that this is equal to the initial velocity of part B. So now, I did just find the final velocity, right? But that's also representative of the initial velocity, okay, of part B. So final velocity, I'll say, of A, let me just write that in here, is equal to then the initial velocity of part B, and they were both equal to 9.38 meters per second. Okay, so here's the thing. Now, we know the initial velocity of part B. What else do we know? So let's now write down for part B things that we know. We know the initial velocity of part B is going to be 9.38 meters per second. I also actually know the final velocity, right, of part B. You might say, well, how do you know that? There's symmetry, meaning whatever velocity, assuming no air resistance and stuff, whatever velocity the object had going up at this point will literally be the same velocity at this particular point, assuming the heights are the same. The only difference will be the sign. It's traveling up here and it's traveling down here. So the signs will change, but the magnitude stays the same. So the final velocity is negative 9.38 meters per second. The displacement, right, for part B, I don't know, right? I have no idea what that is. So that's a question mark. I also don't know the time. That's another question mark, but I do know the acceleration, right? It's, again, in free fall, so negative 9.80 meters per second squared. Now, remember, they're asking us, go back to the question, it says how much additional time will pass before the ball passes the tree branch on the way back down. So remember, I'm looking for the time it takes to go from this location to this location. So that's this variable right here in my givens. So what I'm thinking about now, do I know a formula that relates initial velocity, final velocity, and acceleration and time? Yeah, right? Look at the top formula, the first formula. We know that. Okay, so the final velocity is equal to the initial velocity plus the acceleration times time. So the final velocity, again, was negative 9.38. The initial velocity was 9.38, plus the acceleration, which was negative 9.80, multiplied by t. So this is negative 9 point, let's clean it up a little bit, equals 9.38 plus, well, minus, right? Minus 9.80. What's going on? There we go. So now what am I going to do? Let me subtract this value on over. 9.38 minus 9.38. That gets canceled, so just take out the calculator, 9.38, and itself again should work out to be negative 18 point, we got to round, 18.8, we got to have three significant figures, is equal to negative 9.80 t. And look, when we take the signs into account, notice how now the value of the time is going to become positive, which we know it should. So the time value here is going to be, so 18.8 divided by 9.8. So we get 1.92 seconds. And that will now be the answer for this, because this is how much additional time will pass before it passes the tree branch on the way back down. Number 50. A kangaroo can jump over an object 2.5 meters high. A. Calculate its vertical speed when it leaves the ground. All right, so let's draw a little picture here. There's no chance I'm drawing a kangaroo. So for some reason, the box will represent a kangaroo. And it's going to jump now over an object that is 2.5 meters high. So let's just say this little object here. All right, this thing is 2.5 meters high. So 2.50 meters. Okay, so the kangaroo is going to jump. It's going to go hip hop, hippity hop hop, right over this thing and come back down. Okay. Now let's assume that it just clears the height of this object. All right, so it jumps exactly 2.5 meters. You might say, well, it might have to jump slightly more. Yeah, but we're going to simplify it, so let's just keep it at 2.50. And now what it wants us to do, it wants us to calculate the kangaroo's vertical speed, all right, when it leaves the ground. So it wants to know essentially the initial velocity here. Now, framing in this problem is extremely important, okay? I'm going to break this up into two frames, okay? I've done this before in the past, so those of you who have been tuning in should be familiar. But what I'm going to do is I'm going to take the highest point as the point in which I'm going to divide this problem up into the two parts. To the left of the point will be part A, to the right of the point will be part B. And this point here is special. Reason being is because not only is it the highest point of the problem, but it's also where the velocity of the object is equal to 0. All right. Now that's important because in terms of part A, if I consider this to be the initial state, this would then be considered the final state. So I would then know the final velocity for part A. Okay. If I consider my part B as the frame I'm interested in, then this particular point becomes now the initial value, because now at the bottom it's the final. Okay? So it tells me another piece of information that's extremely important. So let's see. So what do we know now specifically for part A? Okay, because remember, it's asking us to find the initial velocity when it leaves the ground. So that's really what's important. So for part A, all right, for frame A, the initial velocity is something. Don't know what it is. The final velocity, we do know, it's 0 meters per second for the reasons I just discussed. We do know that the acceleration here is going to be negative 9.80 meters per second. And we also do know something else, right? How high does Mr. Kangaroo have to jump? Mr. Kangaroo has to jump 2.50 meters to clear it, right? So that's essentially the height from the kangaroo to the top. Okay, so that's the displacement of part A. Now you might say, well, wait a minute, Andrew, you kind of drew the picture. Look, here's the height of the kangaroo, and this is a little lower. Yeah, I know. I guess I was a little sloppy there. But assume that they are at the same height. Okay, because if they're not, we don't have enough information in the problem to calculate it. More information would have been given, so I'm fairly confident that that should be the case. So now we do know the displacement here, since Mr. Kangaroo is jumping in the positive, or he's propelling himself in the positive y direction. We know that that displacement is a positive value, so it's just going to be 2.50 meters. All right. Now let's take a look. Do we know an equation that relates these four variables together? Yes, equation number 4. So, wonderful. I can literally use equation number 4 to calculate my answer. So, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. Final velocity is 0. Initial velocity is what we're looking for. The acceleration due to gravity is negative 9.80, and the displacement we just discussed was 2.5. So now we get the initial velocity squared minus, so just do the math. So 2 times negative 9.8 times 2.5. And we'll get an answer of negative 49.0. Okay, now add that on over. 0, add it on over. 49.0. Now the initial velocity then squared is now 49.0. So how do we solve? Got to get rid of the square, so we've got to take square root. So the initial velocity here of part A is 7 meters per second. 3 significant figures. So that solves part A. That's all that there is to part A. Not only part A of the problem, by the way, but also frame A. Okay. Let's take a look at now part B. It says, how long is it? Oh, don't call it Mr. Kangaroo. How long is Mr. Kangaroo in the air? Well, we can do this in a couple of ways. We can think about this problem as still 2 parts, right? I could solve for the time it takes for frame A, meaning the time it takes to get from the bottom to the top, and then realize that there's symmetry, and therefore the time of part A should be the same as the time of part B. So I would just add them, right? I could do that. That's fine. That's one way. Another way would be, since the problem is symmetrical, you can use another formula to help you out. What we could use here, so which one might we use? And this formula will help connect the frames. Remember, we are trying to look for time here in this problem. So which one you thinking? Take your time. Remember, also, we know something else, right? If we consider that, if we know the initial velocity of part A right now, so consider the problem to be this. Kangaroo jumps up, comes back down. Okay? It leaves with an initial velocity of, we just calculated 7.00 meters per second, right? It travels a height of 2.50. And if now I consider this whole thing to be my problem, from the start point over here to the end point over here, I actually do know the final velocity in this location. Because it's symmetrical, it has to be the same, all right, as it was initially, just negative. So that might make it even easier now, right? So we know that. Now remember, if I'm considering this to be my starting point and this point to be my ending point, what's the displacement? Is it 2.50? No, right? It won't be. It'll be 0. Why? Well, look at the start and the end point. Are they at different heights? No. So therefore, no displacement. Cool. All right, let's move on. So now we know the initial, we know the final, we also know the displacement is 0. Okay, so that can help us. So the x here is going to be 0 meters. We also know that the acceleration, right, is negative 9.80 meters per second. So we want to find then the time. Okay, so maybe choose an equation that relates initial, final, and acceleration and time. Equation number 1 fits the bill at the top. So the final velocity is equal to the initial velocity plus the acceleration times time. So the final velocity here is negative 7.00 meters per second. The initial velocity is 7.00 meters per second, plus the acceleration, which was negative 9.80 t. Okay, great. So it looks like to solve this, I got to subtract the 7.00. Notice how it'll be additive. So negative 14, right, 0.0 is equal to negative 9.80 t. So now divide out the negative 9.80, and look, the signs worked out beautifully because we get a positive time, which we should have. So now it becomes negative 14 divided by 9.8. By negative 9.8, that is, right? So it'd be positive 1.43 seconds. And that is how long Mr. Kangaroo is in the air. Number 51. Standing at the base of one of the cliffs of Mount Arapiles in Victoria, Australia, a hiker hears a rock break loose from a height of 105 meters. He can't see the rock right away, but then does 1.5 seconds later. How far above the hiker is the rock when he can see it? All right, so little sketch here. Here's the cliff. Oh, here's the cliff. And the height of the cliff, it says, is going to be 105 meters. Okay? Some rock is going to break off right about here, right? It's going to break off. And that's the sound a rock makes when it breaks. And it breaks off, and it's going to just start traveling down, obviously, because gravity's pulling on it. So now there's a hiker down here on the ground. So here's the ground. And there's a hiker here. Now, I know the hiker has some height, but we're going to assume that he doesn't have any height to it, any height to him, because it didn't mention that in the problem, and if I choose an arbitrary height, it's probably going to affect the answer. So we'll just assume that even though there is a little height here, that he's literally just at the ground height. Okay, probably won't even make a big difference in terms of timing anyway. It's probably a fraction of a second difference. But so let's just assume he doesn't have any height. And now he looks up, right? So let's just assume once the rock reaches right here, he's finally able to see it, right? So now the hiker detects the rock, okay? So he heard it. Now, I mean, we can go nuts with this problem. What was the speed of sound, right? How long did the sound take to reach him and stuff? But we'll just assume that the sound that the rock made was instantaneously transmitted to his ear, all right? Otherwise, the problem becomes much more difficult. But not insolvable or unsolvable. Yeah, not unsolvable. Insoluble is the terms from chemistry. Unsolvable, even though they're two different things. Don't mind my rant. Anyway, okay. So, so he sees it, all right, 1.5 seconds later. So the time, so let's say that this would be considered something like t0. And now the time here would be something like t is equal to 1.50. Okay. And so what they want to find now is how far above the hiker is the rock when he can see it. Well, we know the total distance, right, from the top of the cliff to the bottom. So maybe if I can find this distance or this displacement, I can then use the total in conjunction with this to find this, right, which is really what they want. Now, I know it's really going to his head, but just assume he's at the bottom of the cliff. All right. So this is really what we're interested in right now. All right. And in order to do that, we have to first find the displacement that the rock has fallen. So let's call this part of the problem part A. So let's write down some knowns for part A or frame A. Okay. The initial velocity of the rock, it just fell off the cliff, so it's 0 meters per second. The acceleration due to gravity, since this thing is in free fall, it will be negative 9.80 meters per second squared. We know the time that it took for the hiker to detect it would have been 1.50 seconds. We don't know the final velocity of the rock at the end of part A. And we also don't know x, right? That's really what we're trying to find. So let's think. Do we know a formula that relates initial velocity, acceleration, time, and displacement? And we do, right? It's going to be equation number 2. So let's write that down. So the displacement is equal to the initial velocity multiplied by time plus 1/2 of the acceleration times time squared. Okay, so the displacement here is going to be the initial velocity, which remember, it was 0. So I'm just going to, this whole thing just cancels. So that's just 0 plus 1/2 times the acceleration, right, which was negative 9.80, and multiplied by the time, which was 1.50 squared. Okay, so now the displacement will be, just plug it into the calculator. So it's 0.5 times negative 9.8 times 1.5 squared. Okay, so this works out, and we're going to need 3 significant figures here. So this works out to be negative 11.0, and that is in meters. Okay, now that should make sense. It should be a negative displacement in terms of physics, right? Because the object is traveling in the negative y direction. It's starting at the top, ending here, that's negative y. Okay, so that means it's going to be a negative displacement. But what I'm going to do here when I plug it back into my picture, all right, I'm just going to put it in as a positive number for now, just because now what I'm going to do is I'm not really doing a physics problem. I'm doing more, I mean, it's physics, but it's more math-based. This is the total distance. This is now part of the total. And what I want to do is find the missing piece. All right, so we can think about a simple formula now that the total, I'll say the total displacement, so x sub t, will be equal to x sub part A plus then x sub part B. So I'm going to call this part, the part in gold here, part B of my problem. All right, and I'll just put that in gold here, x sub B. Okay, so the total now, the total height was 105 meters. The height of part A was 11.0. And now I can find x sub B, right? Just subtract the 11 minus 11.0. So now x sub B, right, becomes, what is that, 94? 94. And we can't put the decimal there, so it's just 94 meters. Okay, great. So now this is the part in gold. All right, so 94. So this piece here we now just found. Let me erase the question mark because it's not a question anymore. We know what it is. So the x value here is going to be 94 meters. Okay, wonderful. So now that is the answer to now part A, right? If we go back for part A, if we go back and we identify the question, it says A, how far above the hiker is the rock when he can see it? It's 94 meters above him. That's the answer. Now the question is this: how much time does he have to move before the rock hits his head? So now this is where it's important now. So now I need to consider my frame of part B. Okay, this is the initial point of part B, and this is the final point. How do I know that? Because that's the direction of the rock is traveling. It's going to go through this point before it gets to this point. Okay, so let's try to define some knowns and unknowns about this particular part. Now, so for part, not only is this frame B, but it's also for letter B of the problem. Do we know the initial velocity of that at the moment? No, we don't. Right? We don't know what the velocity is here. We didn't calculate it before. Now remember, the important point between these two parts is going to be that the final velocity, let me put it in red, okay, the final velocity of part A will be equal to the initial velocity of part B, because this is where the frames meet. Okay, that's a very important fact. It'll help us in terms of problem solving here. So we don't know the initial velocity of part B, but maybe I might be able to use the final velocity of part A. Maybe I have to calculate it. You see, we haven't calculated it yet, but we could probably find it. So we don't know that. We do know the acceleration of part B, right? It's negative 9.80 because it's in free fall, meters per second squared. We do know now the displacement, which would be now technically, once we start thinking about this, it has to be negative 94 meters because the object is traveling in the negative y direction. We do not know the time, right? And we also do not know the final velocity. So I'm missing too many variables here. I just know acceleration, I know displacement. I got to find something else in order to help me solve this. Okay, now remember, we are looking for time. So if I think about it, go to your formulas, take a look now at the second equation again. What this equation tells me is that if I know the initial velocity, and I know the displacement, and I know the acceleration, I can simply find the time. So if you notice here, the initial is the only thing that's missing. So if I can find the initial velocity first of part B, I can then use that equation I just highlighted to finally find the time. All right, so let's do that part first. So remember, the initial velocity of part B, okay, is equal to the final velocity of part A. So actually what I'm going to do is I'm going to find the final velocity of part A. So I'm going to use these knowns and unknowns, okay? Now I want to solve for this, and I realize I have a whole bunch of stuff. I know the initial, I know the acceleration, I know the time, so it looks like I can use equation number 1 there, right? So final velocity of part A is equal to the initial velocity of part A plus acceleration of part A plus the time of part A. Notice all the consistencies. So the final velocity of part A is equal to 0, right, because that's the initial velocity of part A, plus the acceleration, negative 9.80, multiplied by the time, 1.5. So let's calculate that. So negative 9.8 times 1.5. So we get negative 14.7, and 3 significant figures is good, negative 14.7 meters per second. Now remember that this number is also the same thing as the initial velocity of part B. Okay. Now we have enough information. Now this number here, we can take it and now plug it in. Okay. Let's now write out that formula number 2 now. So now this again is calculation for part B. So we have the displacement is equal to the initial velocity times time plus 1/2 of the acceleration multiplied by time squared. So what's the displacement of part B? Look back to the knowns and unknowns. Okay. We know that it is negative 94. That's important. The initial velocity, now we just calculate. Again, signs are important here, so negative 14.7. What's the time? Well, that's what I'm solving for. So that's the variable. Plus 1/2. The acceleration is negative 9.80. And again, t squared. Okay, so let's just clean it up a little bit. Negative 94 will equal negative 14.7t, right? Minus now 4.9 t squared. I always like to have a positive a, just out of habit. So what I'm going to do, if you notice, it's a quadratic. So I'm going to bring this term on over to the left-hand side. I'm going to add it. And same thing with this term. I'm going to bring it on over, and I'm going to add that as well. So since I'm running out of room, I'm just going to write the answer. So the value should be now 4.9 t squared plus 14.7 t minus 94 equals 0. Okay, now from here to solve this, you would have to just make that a little neater. Equals 0. From here, you'd have to use your quadratic equation. Here's your a value, here's your b value, here's your c value. Okay, I have a program in the calculator. I'm just going to plug it in. So let me plug in the a value of 4.9, the b value of 14.7, and the c value of negative 94. And it comes out, again, you're going to get 2 answers, quadratic, so there's 2 solutions. So the time value, I'll write them both down, 3.13 seconds. and the other time is going to be negative 6.13 seconds. Only one of these are going to make sense. The negative time doesn't make any sense because we started at time 0, so that doesn't make any sense whatsoever. So here now, this will be the time. Okay? So this is the time now for part B, right? And now let's see if this is indeed the answer we're looking for. So it says, how much time does he have to move before the rock hits his head? So remember, he just notices the rock at this point when the rock is at that height. So I use that particular height to solve for the time. And I also use the initial velocity at the point there. So it sounds good to me. We just found the answer. So he has a little over 3 seconds to get out of the way. 1 1,000, 2 1,000, 3 1,000, boom! Hopefully he moved. Number 52. An object is dropped from a height of 75 meters above ground level. Determine the distance traveled during the first second. All right. So we have an object, right? And it's dropped, okay, from a height, it tells us, of 75.0 meters. So let's just assume it goes to here. And it says it's just dropped, right? So that means that there is no initial velocity imparted on it. So therefore, its initial velocity should be equal to 0 meters per second. We want to then calculate the distance traveled in the first second. Okay, so let's just assume that this is the part, or this is the for letter A. All right, let's say this is the location at which it would have reached during 1 second of its travel. Okay, so the time to go from the start to here is going to be 1 second. All right, so t here is going to equal 1. I'm just going to do 1 second. I was going to write 1.00, but whatever. So now they're asking me then to calculate this part of the height, right? This x value here. Okay, so what else do we know about this? Well, we also know the acceleration, right? It's a free fall problem, so it's negative 9.80 meters per second. All right, great. So do we have enough information now in order to solve for the height? We have the acceleration, we have the initial velocity, we have time, and now we need to find x, right? Look at the equations on the right-hand side, and we do, right? It would be equation number 2. So let's write that. So letter A here, we're going to do the displacement is equal to the initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared. So the displacement is what we're looking for. The initial velocity was 0, so that whole term just cancels. Multiplied by 1/2 times the acceleration, which was negative 9.80. And the time they said was 1 second, so that's squared. So the displacement now will be, just plug that into the calculator. Well, it's half. I mean, 1 squared is 1, right? So then half of 9.8 is negative 4.9. I'll just do 3 significant figures. This should be meters. So that's how far it travels in the first second. Okay, great. So that takes care of part A. Now it says determine the final velocity at which the object hits the ground. So now the frame is slightly different, meaning that the starting point will be the point up at the top here. Okay, and now the ending value is going to be down here at the bottom. Okay, so again, my initial is still the same. It's still starting at 0 meters per second. And what I'm trying to do down here now is find the final velocity. That's the question mark. What else do I know about this frame in yellow? I also know its acceleration, right? That would equal negative 9.80 meters per second. And I also know the height, right? The total height here. The total height here is 75, okay, meters. Now just be careful. The height is 75 meters, but when you plug in this number into your calculations, you got to make sure it's negative. Why? Because it starts high, ends low. You got to have a negative sign, okay, for the height. It's traveling in the negative y direction. So, do we know a formula that relates displacement, initial velocity, acceleration, and final velocity? Yes, we do, right? Equation number 4. So let's use equation number 4 here that I just boxed in to help us solve for B. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is what I'm after. The initial velocity was 0, so that's just 0. Plus then 2 times the acceleration, negative 9.81. Well, in some books they use 9.81, but this one uses 9.80. And the displacement now, again, this is important. You got to be negative 75. Okay? And you'll see it's important. Actually, in terms of the magnitude, it won't, since there's no initial velocity, the magnitude will be right, but the sign would be a little messed up if it weren't negative. So 2 times 9.8 times 75 is now going to be, okay, so we have, right, I'm just making, yep, okay, so the number's a little bigger. So we have a value of 1,000, and I'm going to do 3 significant figures, 470, no decimal. So now when I take the square root, I can take the square root since it's a positive number. So the final velocity here will be plus and minus. Okay, anytime you take the square root, you get both plus and minus answers. So now when I take the square root of that, I get 38.3 meters per second. Now only one of those values, positive or negative, will make sense. Which one do you think? Right, the negative one. The negative one is the one that makes sense. Why? Because it's traveling in the negative y direction. So since velocity is a vector, you have to you have to also give its direction. Okay, so it's going to be a negative value. So let me just erase then the positive here, okay, since I don't want to accept that answer. And this would now be the final velocity when it hits the ground. So that's the answer to part B. Now C, it says, okay, so C, it says determine the distance traveled during the last second of motion before hitting the ground. Okay, so this one's a little more involved. There's a couple of steps. So let me actually redraw the picture, all right, just because it's getting a little messy. So again, here's the object. It travels down with a certain initial velocity, and that's 0, right? It's going to, the whole thing is 75 meters until it hits the ground over here. And what we're looking to do now is we're looking to find the distance traveled during the last second. So if we were to imagine, the last second would be around here. I mean, I'm making it up, right? But as this rock travels down here, this would be considered now the last second of travel. So from this point all the way down to this point. Okay? So here's the last second of travel, right? Right in here. Let me just change the color. Right in here. That looks like a 3, but I think you get it, right? This would be the displacement. This is what we're after. So I'm now framing the problem. If you notice this, I'm trying to frame this pretty well here, right? I have a clear, if I'm trying to find the displacement, I can do this in a couple of ways. I mean, I can, in order to find this displacement, right, what I could do is I could find the displacement from the start all the way down to this point, and then just subtract it from 75. That's one way to go about it. There's other ways to go about it too, but I'm just thinking, that might be the best way to do it. Let me just think. I mean, we could also go about it by finding the total time and whatnot, but let's do it that way. So let's focus. Well, actually, no. Actually, we do have to find the total time anyway. Yeah. So the first step is, so I know that also the time to go from this point to that point is going to be 1 second. Okay, so the time value in here is also 1 second. So really what I need to do is I got to find some information out about this point. All right, I know what the final is here, but I don't know what the initial conditions are like. So how am I going to find that information? Well, I'm going to find that information by finding the total time of the whole thing, right? The whole thing, and then subtract out 1 second. That'll tell me the time to this location. Once I know the time to this location, what I can then do is solve, let's say, the velocity at that point. All right, and that should help me along now. Okay, so let's calculate that. So let's find, so the first step here for part C, it's going to be multiple steps. So first step is, so part C, let's say number 1 is find total time. Okay, so to find the total time, I'm considering the total frame, meaning from the start all the way to the end. Okay, so the initial velocity for that whole thing is going to be 0. The final velocity we actually just found, right? That was the whole point of part B. So we know that that will be negative 38.3 meters per second. We also know that the acceleration is still negative 9.80 meters per second squared. We do know the total displacement, remember, negative 75 meters. So I can easily solve the time. I get a whole bunch of ways to do it. Probably the way, let's see, which way should we? So the initial was given, right? The acceleration we know for a fact, and the x was given. So do we have an equation that would relate it to time? I want to try to avoid using this because maybe I made a mistake in my calculations, and I don't want it to, I mean, I don't think I did, but if I were to have made a mistake, I wouldn't want it to propagate into this part. So that's why I'm only looking back to the givens. So yeah, I do know an equation that will relate these four variables, and that equation will be the second equation again here. Okay, so let's write that down. So change in displacement is equal to v initial velocity times time plus 1/2 at squared. So the displacement here was negative 75. The initial velocity was 0, right? So this whole thing just goes to 0. Plus then 1/2 multiplied by negative 9.80 times t squared. So negative 75 is equal to negative 4.90 t squared. Divide out the negative 4.90 on both sides. T squared becomes, so just plug that into the calculator. So 75 divided by 4.9. The answer is going to be positive, and it should, because we got to take the square root. So this would be 15.3. And take the square root. Remember, when you take the square root of a number, it's always plus and minus. So second square root of 15.3 comes out to 3.91. Now only one of them will make sense in terms of sign-wise, and that'll be the positive one, because the time can't be negative here. We're starting at time 0. So what I'm going to do is just erase that little negative sign. All right, so it's 3.9 seconds from the top to the bottom, right? The whole thing. So if this, going back to the picture on the left, so if the time from this location, I'm going to say is 3.91 seconds, all the way down to the bottom, how do I find the time to this point? Right, it would just be, you would have to subtract 1 from it, right? Because they told us during the last second. So to find the beginning of that last second, if I know the total distance of 3.91, just subtract 1. Okay, so what I'm going to do now is I'm going to do that. I'm going to take, and let me put it in a different color. All right, let me put it in, I'll put it in black. So we'll do 3.91 seconds minus 1 second. Should be then 2.91 seconds. Now this value, okay, is the value of the time from the beginning here all the way down to this point. That's the time. So if I know that time from this location to this location, right, I can now start solving for, let's say, displacements. Okay, so let's write down what we know about that frame. The initial velocity at the start there was still 0. That's still the same. The final velocity I don't know. May be trying to solve for that. We'll see. The time we just solved, it's 2.91 seconds. Okay, the displacement I also don't know. And the acceleration we do know, right? These are all the variables. I labeled them all out, negative 9.80 meters per second squared. So now what's the important variable here? It's really the displacement, right? That's really what I'm after. So I know the time. I know the initial velocity. I know the acceleration. If I want to find my displacement now, can I use an equation on the one of those 5 equations at the top? Yeah, I can, right? Just erase all that. I can use the second one again. This one's very popular in this problem. So let's write it down. So the displacement, okay, is equal to initial velocity times time plus 1/2 acceleration times time squared. So the displacement is what I'm looking for. The initial velocity was 0, so that goes bye-bye. Then it's 1/2 of negative 9.80 times the time of 2.91. Now hopefully I didn't make a mistake with that because it will propagate on in, but I'm pretty sure I'm good. All right. By the way, all my self-doubting is not because I'm not confident about it, but I always like to doubt just to always keep double-checking are the answers reasonable and whatnot. Okay, because you want to try to avoid silly mistakes. We're all human, but you want to come up with systems to avoid that. Right? That's how you'll get the A. So 0.5 times negative 9.8 multiplied by 2.91 squared. Okay, so the displacement here comes out to be negative, which it should, 41.5 meters. Okay, so we're almost there, guys. We're almost there. So what did I just find? I found the displacement. Now I know this picture's getting a little, filled with stuff. But I found the displacement from the top now to the bottom. Okay, so that x value now is equal to, I know it's negative, but I'm just going to make it positive in the picture because I'm going to do a little math to solve. Now think about it. If I know the value, from this location to this location, and I also know the value from this location to this location, how do I now find that little x I'm looking for in red? How do I now find the difference? Oh, I just told you, right? The difference between the two. Okay. So in order to find, then I'll call it x, right, in red. So the x that I'm solving for is going to equal the 75 meters minus the value I just found, the 41.5 meters. All right, so the x that I'm looking for, meaning the distance or the displacement that it travels in the last 1 second of its travel will simply be 75 minus 41.5. And thinking about sig figs, this was really 75.0. So I'm going to have 3 sig figs, so this is 33.5 meters. Okay, determine the distance traveled, right? So they didn't, so it's totally fine to leave the answer in the positive form. That should be 100% acceptable. All right, so notice in the last 1 second, it travels almost half, right, of its total distance. Right, the whole time it was in the air was about 4 seconds. All right, but during that last second, it traveled the most. Why? Because the gravitational force is now accumulated essentially on the object. All right. Number 53. There is a 250-meter high cliff at Half Dome in Yosemite National Park in California. Suppose a boulder breaks loose from the top of this cliff. How fast will it be going when it strikes the ground? So that's part A. So let's just take a look at that for now. So we have a cliff. All right. The height of the cliff here is going to be 250 meters. Great. Here's the ground below. And a rock is going to break off, or what does it say? Boulder, rock, whatever. And it's just going to break off, right? So if it just breaks off by itself, we know that the initial velocity here should be equal to 0 meters per second. We also know once it breaks off that the acceleration of the rock will be equal to that of the acceleration due to gravity, which is negative 9.80 meters per second squared. Right? We also know the displacement that this rock will be traveling, right, is going to be traveling negative 250 meters. Why negative? Well, because the rock is moving in the negative y direction. Therefore, the displacement will be a negative value. What else do we know here? Well, let's write down some of our unknowns. Right? We don't know the total time it'll take, nor do we know the final velocity. Okay, but now the question A, remember, is asking us how fast will it be going when it strikes the ground. So we're being asked a question about the final velocity. So what I want to think about is, do I know an equation that relates the final velocity to the initial velocity, acceleration, and displacement? And we do, right? We know that the fourth equation does on the right-hand side. So let's write it down. So for A, we know that the final velocity should equal the initial velocity squared, plus 2 multiplied by the acceleration, then by the displacement. So the final velocity squared will equal the initial, and the initial was 0, right? So 0 squared is obviously 0, plus 2 multiplied by the acceleration of negative 9.80, multiplied by the displacement of negative 250. Okay, so the final velocity squared is 2 times negative 9.8 times then 250. And the answer comes out to be positive because of the double negative. So we get 4,900, right, a value of 4,900. And it's positive, which should make sense because we have to take the square root of it, so it had to be positive. So now the final velocity here, just taking the square root of that number, should work out to be simply 70, right? So this comes out to be 70. I'll do 3 significant figures, meters per second. So at this particular point right here, okay, as soon as it hits the ground, the velocity at this location will be equal to 70.0 meters per second. Okay, so that's the answer for part A. Now for part B. So let's go, let's get the highlighter. So now it says, assuming a reaction time of 0.3 seconds, how long will a tourist at the bottom have to get out of the way after hearing the sound of the rock breaking loose? Neglecting the height of the tourist, which is negligible, and it tells us that the speed of sound is 335 meters per second. So let's just think about what's going to happen first, essentially, in this part B. So let's just draw, I'm going to draw another picture. All right. So, so here's the cliff. This is again 250 meters. Okay. The rock breaks off, right? And the rock is still traveling down at an initial velocity of 0. There's a person down here, right? Oh my goodness. So there's a person down there, but we're going to consider the height to be negligible. So I'm just going to represent this person as a dot, which by chance would be his shape if the rock does hit him. So what I need to now do is I need to now think about what's going to happen first. So the rock breaks off, right? And then is the person going to react? Well, no, not yet, right? Because what are they going to react to? They're going to react to the sound. Okay, so the speed of sound was given. So as soon as the rock breaks loose, the person right at that particular moment in time, the person down here, has no idea that the rock is broken loose, assuming that they're not looking up and they can't see it. They're just going to work off of their hearing. So what happens is as soon as this rock breaks off, the clock starts. Okay, the clock starts. T is equal to 0. Now, the person down here doesn't hear the rock at time E is equal to 0 because it takes a certain amount of time for the sound here, right, the sound waves, to reach the person. How long is that time? Well, we can find that out, right? So let's look back. So let's think about so let's write this down. So this is the time for the sound, ND, to reach person. Okay, so let's write down what we know. We know that the initial, so now remember, this is now for the sound. So I'm not talking about the rock. I know the initial velocity of the rock is 0, but what's the initial velocity of the sound? Right? It's either there's no sound or there is sound. Okay, it's for simplicity in this problem. So assume that there's no acceleration, right? Gravity doesn't pull down on sound, it's a wave. So assume that the initial velocity of the sound is the 335 meters per second. That means also that the final velocity of that sound, it's not accelerating, right? It's not an object being pulled by gravity. So therefore it should also be 335 meters per second. Again, the acceleration for this would be 0 because the sound is not affected by gravity. And what else do we know? We do know the amount, the displacement that this sound has to travel. Now, just thinking about these signs here, remember the velocities are going to be negative. Okay, the reason why is because the sound is traveling down in the negative y direction. Therefore, the displacement will also be negative. So the sound has to travel 250 meters. And now from here, I could probably figure out the time. So now what we want to do is let's see if we can find an equation that gives us the time and that also mentions, the initial and the final and the displacement. And it looks like I can use equation number, I can use another equation other than this, but I'll use equation number 5. So let's write that. So the displacement is equal to 1/2 times the initial velocity plus the final velocity multiplied by time. So the displacement, as I mentioned before, was negative 250. Equals 1/2 multiplied by the initial velocity, which was negative 335, minus another 335, then multiplied by time. So this is negative 250. Adding those two numbers together, the negative 335 times 1/2 should just be itself, 335 t. And notice, because of all the signs, it's going to turn out to be positive, which we should anticipate. So the time value here is not totally insignificant, so it actually will make a little difference. So this is 250 divided by 335. So, okay, so it takes 0.746 seconds. Okay, so it takes 0.746, or about 3/4 of a second, in order for the person down here to even hear the sound. Okay, so right now, where's the rock then in reality? So the rock probably moved down to here somewhere now, right? It definitely moved downwards. I mean, the rock fell. The person just didn't know it until he heard the sound. So now the rock is not at its original starting point. It's some point below that. Okay. How far below? Well, we could find that if we needed to, right? But not yet, because this is just the time that we found is just the time that it took for the sound wave to reach the person. Now remember, that's not the time that the person is going to perceive the sound. How do I know that? Because it says assuming a reaction time. Well, actually, I shouldn't say that. That is the time that the person will perceive the sound, but they're not going to react yet. Okay, so they might hear it and they might take a fraction of a second to figure out what to do. All right? So that's what I'm most concerned about. How much time does this person, as the question's asking, how much time does this person have to move out of the way? Okay, so not only does he need to wait to hear the sound, but he's also going to have to react to the sound. Okay, so the time now, so how much time has elapsed from the start? Okay, in order before this person can even react. So let me give you a little formula here. So let's say the time until I can't even spell. That's why I tutor. That's why I teach physics and math and science. So the time until he can move, all right, should be equal to the time that the sound takes to get to him plus the reaction time. That should make sense. Right, so the time until he can move, I'll say until UM, is equal to then the time that it took for the sound to reach him, which we just found to be 0.746, plus then his own reaction time, which is going to take a little over 1/4 of a second. So the time until he's able to do something, or until he's able to move, should be equal to 0.746 plus 0.3. So that should be equal to 1.04046 seconds. So now already the rock now has moved even a little bit further. Maybe it's moved now down here. So right now the rock is somewhere in this second part. Okay, so let's just assume the rock is here now. And now finally the person down here, let me just erase that little box around him. So finally now the person down here is finally not only detecting the sound, but he's also going to now be able to move. Okay, it's not until the time of a little over a second has passed until he's able to move. So the time it took to go from the rock breaking off, right, to now when he finally is able to move, this time in between here was, and let me just erase this part, not to make it too messy here. So the time it took is going to be 1.046 seconds. Okay, so now the question is, again, let's think about the question. How long will the tourist at the bottom have to get out of the way? Well, in order for me to find that, essentially what I'm trying to find now is I'm trying to find the time, right, between, so the time from this point right here until it hits him. So what is the time value? What is this time? How can we solve it? Now, there's a bunch of ways to do this, but I think the easiest way would be, since I already found this time, the easiest way to do it would be now to focus in on finding the total time from the top all the way down to the bottom. Because then if I can find that whole time or that total time until it gets to the bottom, then to find this little piece of it, I could just subtract this on out. Okay? So that's my shift now. So now what I'm going to do is now I'm going to shift my focus here to finding the total time. I'll call it total time for rock or boulder, whatever it is, to hit the ground. Okay, so how do we do that? Well, remember, the frame of the problem is now here's the start at the top in terms of the picture. Take a look, guys. And here's now the bottom. So the initial is up here, right? And my final values are down here. Okay, so let's state some knowns and unknowns about those two positions. So I know that the rock, the initial velocity of the rock is 0 meters per second. I know the rock is in free fall, so therefore it's negative 9.80 meters per second squared. What else do we know? We know that the rock has to travel a distance of negative 250 meters. Okay, got to keep the sign, take the sign into account there. What else do we know about those frames? We also do know the final velocity, right? Because we just calculated it over there. So we do know the final velocity of this boulder is going to be negative 70.0. Actually, I realized I forgot to put in the 70 negative. Oops. So this has to be negative here. Why is it negative? So, oh man, I say this all the time. Anytime you take a square root, see, you can even repeat it all the time and still you may forget. So anytime you take a square root, it's always positive and negative. Which value are we going to take? We're going to take the negative one. Why? Because the object is traveling in the negative y direction. So this answer should be negative there, technically. Okay. So anyway, I fixed that. That's always the benefit of looking back, and I got to put a little negative there in my other answer. Okay. So, all right, so we got that. Not to get too distracted. So where are we now? And right, we're trying to find the total time here. So the time is the question mark. So what we want to think about is do we know some variables that relate these things together? And I'm actually going to choose, because maybe I made a mistake in calculating my final velocity. I'm sure I didn't, but maybe I did. So I don't want to include that in my calculations here because all of these other values were given to me that I just boxed. So let's look at a formula that might relate those four together so as to minimize the chance of errors propagating throughout your work. So I just boxed something at the top. All right, it's going to be this equation that we're going to want to use. So let's write it down. So change in x is equal to VIT plus 1/2 AT squared. What's the displacement? Negative 250. The initial velocity was 0, so that whole thing goes to 0. Plus 1/2 of negative 9.80 multiplied then by the time squared. That's what I'm trying to find. So it's negative 250 is equal to negative 4.90 t squared. Just divide out the negative 4.90, divide out the negative 4.90, and now the t squared is equal to, so take out the calculator, 250 divided by 4.9. The answer is going to be positive, so it works out to be 51.0. 51.0. Now take the square root of both. So the time here is going to be, so second square root of 51, 7.14. So 7.14 seconds. Now here's the thing. This is the total time, okay, that it will take for the rock, the boulder, to go from the top up here all the way down to the bottom. Okay, so now that we know that total time, remember the formula I mentioned before. I'm going to go to the upper left-hand corner, right? That the total time it takes for the rock to fall will be equal to the time it takes for the person until he's able to move, right? That we just found in the prior part, plus the time it takes to then hit him. Okay, that should make sense. Those are the two parts. So the total time we just found was going to be 7.14 seconds. The time it takes until he's able to move by the time he hears the sound and then by the time he's able to react was found to be 1.046 seconds, right? Yep. And now I'm finding the time it's going to take before it hits him. Okay, so all I got to do is subtract this out as I was mentioning before, minus the 1.046. So when we do that, the time it takes until it's going to hit him, okay, would be 7.14 minus 1.046. So 6.09, and I have to stop it there at 3 sig figs, 6.09 seconds. So this would be the time he has, right? Time to get out of the way. A lot of these problems deal with boulders falling on people. But anyway, so hope this helped, guys. A lot of parts of this problem, and part B was a little more difficult because there's a lot of pieces. But remember, the important part here is in terms of framing it. Think about the different parts of the problem. Think about the different objects you're solving for, and always try to be consistent. Number 54. A ball is thrown straight up. It passes a 2-meter high window, 7.5 meters off the ground, on its path up, and takes 0.312 seconds to go past the window. What was the ball's initial velocity? All right, so it gives us some hints, but let's try to work without them. So let's just draw a picture, okay? So there's a ball. So let's draw the ball here. And it is thrown straight up. So it's traveling up. What we want to find, right, it wants us to find the velocity initially that was imparted onto it, okay? And it says that it's thrown up, and it passes a window, right? So let's draw the window. So here's the window. And now it says the window is 7.5 meters off the ground. So it didn't say, part of the ambiguity is, it didn't say what point of the window. Is the bottom part of the window 7.5 meters above? Is the top? Is the middle? So I have to assume that the bottom is. All right. Not that I have to, but I'm going to choose that that's the point that in which they're talking. So 7.5 meters to the bottom of the window. Okay, great. And now it says that it passes a 2-meter high window. So we also know the height of the window here, right? We know that this from here on down is 2 meters. Okay. So given the diagram that I drew, right, if we just think about then the total distance from the ground, let me change the color, the total distance from the ground on up to the highest point here, right, what should that be? It would be the 7.5 plus 2, right? Maybe it'll come in handy, I don't know, but I'm just looking at things I can put together already. So this will be 9.5 meters, okay? And now it says that it takes 0.312 seconds to go past the window. All right, so meaning that by the time the ball reaches the window here, right, it's gonna pass through the window, and the time it takes to pass through this window here is going to be 0.312 seconds. All right, so let me just get rid of some of these dots here. Okay, so from this point to this point, it takes the ball, I'm going to write the time in here, 0.312, right? 0.312 seconds. Okay, so now if you notice, I'm already kind of framing the problem here, right? Maybe these points will be important. Maybe in terms of this particular frame here, maybe this will be considered my initial velocity. Not to be confused with this initial velocity. They're at two different points. So I can call them both initial velocities because they're relative terms. Initial to what? Right? So this initial velocity is the initial point when I'm describing from this location to that location. All right? So let's call this, and let's say that has an initial velocity, and then the point up here would have a final velocity. And these would equal some numbers, but we don't know what they are yet. What we do know is focus in here. We do know the time, right, that it took for the ball to pass through the window. And we also know the height of the window. So let's write some knowns and unknowns, okay? So let's talk about like from the window's perspective, okay? So from the window's perspective, the initial velocity here was, I don't know, something. The final velocity was going to be something. By the way, do you think the final should be less than the initial? Yeah, it should be, right? Because the final point is higher. So remember, the ball's in free fall. That's going to be important for this variable coming up. What's the acceleration on the ball? Free fall, so it's negative 9.80 meters per second squared. We also do know the time that it's going to take to travel past the window. Right, so there's 0.312 seconds. And we also know the displacement of the window, which is going to be 2 meters. Okay, so notice how all of these variables must correlate with 2 points. Okay, the initial point, the final point, the time it takes to go from the initial to the final, and the displacement from the initial to the final, as well as any accelerations that are experienced by that object during that time. Okay? All right, so always think about that consistency, okay? That's actually the key. So, why don't we, so it might be hard to connect, well, how the heck do I get it down to my answer? Don't worry about it for right now. Just start solving some stuff, all right? We can solve whatever we want here. So it doesn't really matter. Maybe I'll just solve for the initial component of it if I can. Well, can I? Well, let's see what we're given. We're given the acceleration. We're given the time, we're given the displacement. Do we have an equation that relates all 4 of them? Yes, we do. Equation number 2. So let's do it. So we have the displacement is equal to the initial velocity times time, right, plus 1/2 of the acceleration times time squared. So the displacement here is 2 meters, right? Specifically, they told me it was 2.00, so just considering sig figs here. Now it's positive because the object is moving upwards. The initial velocity is what I'm looking for with respect to the window. The time value then was given, right? It was 0.312. Then it's plus 1/2 times the acceleration due to gravity, 9.80, times then the time squared, so 0.312 squared. Okay, so now let's clean it up a little bit. This is then equal to 0.312 VI, and this whole term will be negative now. So let's take out the calculator, 0.5 times negative 9.8 times 0.312 squared. Okay, so this works out to be negative 0.477, 3 significant figures. So now let's add this on over, right, because we got to isolate the variable. So this is just math from here on out. Well, it was math from before too, but whatever. So this becomes 2.48 now, considering significant figures. I have to cut the answer right here. Okay, is equal to 0.312 VI. Ooh, VI. And now just divide out the 0.312. 0.312. Come on, there we go. Okay, so the initial velocity now is going to be 2.48 divided by 0.312. So we get a value of 7.95, because I have to round to 3 sig figs, meters per second. Okay, great. Now that's not the final answer. That's an initial velocity, but that's not the initial velocity that they want us to find. Okay, that's the initial velocity. Go back to the picture. That's the initial velocity at this point. Okay, now instead of saying initial velocity, because it's just what do you call it? Just relative. It's initial to something. Just pretend that now we're going to just write the velocity. Okay, so I'm not going to. Let me just erase. So I'm going to erase this initial term. Okay, and I'm now just going to write that the velocity here is equal to 7.95 meters per second. Okay, so now let's think about if we can maybe try to piece together an answer. So let's now look at the problem again. I'm just going to redraw a quick picture. So we have this window here. Okay, we have the ball down here. We know it's going to be traveling upwards to the bottom of the window, and we know once the ball reaches this point, its velocity here is going to be, as we just calculated, 7.95 meters per second. We know that the ball had some imparted velocity to it, the initial velocity, which we don't know what it is. We do know also the height that the ball traveled to get to the bottom of the window, That was 7.50 meters. And we also know something else, right? We also know the we also know the acceleration, right? Because the ball here is in free fall, so it's a negative 9.80 meters per second squared. Now, what can I call this velocity if I'm considering my frame to be starting here and ending here? It would be the final velocity, right? So, and I'll mark this as my displacement. Okay, they're all positive except for the acceleration because the ball is traveling up. So now, what are we thinking? Well, we're thinking, do we know a relationship between these four variables I just wrote? X, VF, A, and VI. Do we? Take a look at the formulas. It looks like we do, right? Equation number, and let me just change the color here, equation number 4, right? So let's write it. Final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times x. So the final velocity is 7.95. That value is squared. The initial velocity is what I'm trying to find. The acceleration is negative 9.80. And now my displacement was 7.50. Hooray! Now let's just not mess up the calculation, because if I can calculate this, I can get my answer. So this should be 63. So when you square the 7.95, it becomes 63.2, 3 significant figures, equals the initial velocity squared, plus now, so 2 times negative 9.8 times 7.5. So we get negative, and what I'll do is I'll just actually make this a negative sign, negative 147. So now add, and that has to be 3 sig figs, so add the 147 to both sides, 47. So we now have that the initial velocity squared is equal to, so 147 plus 63.2, so 210. Okay, so we get a value of 210. And now, I can put the decimal there. Now just take the square root. So remember, when you do this, you have both the positive and negative answer. So second square root of 210 works out to be 14.5 considering significant figures. And that's meters per second. Now, which value are we going to take, positive or negative? Well, what's the direction of motion here? The ball is traveling up. So we take the positive version. Okay? So what we'll do is we'll just erase this. And now what I can put in the positive sign if I like, or I can leave it out. It doesn't really matter. But now this is the initial velocity. Okay. Initial velocity of what? Well, the initial velocity, look back at the picture on the bottom left. Initial velocity of the ball. Okay, and this is the final answer now. And it should make sense that initial velocity should be greater than the velocity in which it's traveling at the window. So, sounds like it's reasonable. Number 55. Suppose you drop a rock into a dark well, and using precision equipment, you measure the time for the sound of a splash to return. Letter A. Neglecting the time required for sound to travel up the well, calculate the distance to the water if the sound returns in 2.00000000 seconds. Okay, so let's draw that out. So we have a rock, and it's being dumped into a well. Okay, so here's the water, and it is traveling down, right, with some velocity. Now, since it said it was just being dropped, we can assume that the initial velocity at the start is 0. There's no velocity imparted to it. And what's going to happen is it's going to travel, right? It's going to make a little splash sound here. And the problem is assuming that neglect any time for the sound to travel up the well, that the sound will return in 2 seconds. Okay, so that means that as soon as the rock hits the water, we perceive the sound, and we're just going to assume that the speed of sound was negligible. All right, so basically what that means is that the time it took the time from the point at which we hear the sound to the time at which we perceive it is exactly identical, or I should say the time at which the sound was created to the time at which we are going to perceive it is the same. So this should be 2.0000 seconds all the way back up. Okay, So what else do we know about this? Well, the rock is in free fall, right? So the acceleration is due to gravity, negative 9.80 meters per second squared. All right, let's also write some of the knowns. We know the initial velocity, as we said, was 0. We know the time also is 2.0000 seconds. And what else do we know? We don't know the displacement, nor do we know the final velocity when the rock hits the ground. But what are we looking for? Well, it says calculate the distance. So it sounds like we're looking for the displacement, right? The x. Now, we know the acceleration, we know the initial velocity, we know the time, and we want to find x. So which formula relates all four of those variables? Right, the second equation there on the top right. So let's write it down. The displacement is equal to the initial velocity times time plus 1/2 of the acceleration times time squared. So the displacement here, right, is going to equal the initial velocity, which was 0, so that whole term goes bye-bye, plus then 1/2 of the acceleration, which is negative 9.80, multiplied by the time, which they told us was 2 seconds, 0.0000, right? So the displacement now will just be, just realized as I was looking back, we got to square that result, right? Don't forget to do that. That's where you'll lose, that's where the points hurt, where you make a silly mistake. So 0.5 times negative 9.8 times 2 squared will come out to be about negative 19.6, right? So negative 19.6 meters. Okay, so that is the distance. Assuming that there's no, assuming that the sound time, the sound wave is negligible, okay? So now it says for part B, it says now calculate the distance. Okay, so same thing, we've got to calculate the distance, but taking into account the speed of sound now. Okay, so why don't we draw another picture here, all right? So we have this picture, again, the rock is being dropped. Okay, it's going to travel down and it's going to make a splash. But now remember, if I call this the time in which the rock is dropped as time 0, then we know that the rock is going to fall, it's going to make a splash, and then the sound wave that's produced has to come back up, right? So let me just, that sound wave has to come back up. And till finally when we hear the sound, up here, H-E-A-R, when we hear the sound at the top, the time that has elapsed will be 2 seconds. Okay, so it's going to be the same as in the prior problem. Seconds. Now you might say, well, how does this calculation differ? Well, the thing is, if this whole loop took 2 seconds, meaning the loop from the point of release, it traveled down, and then the sound wave was produced, and that required time to travel back up, then what we realize is that the distance here, or the time it took to fall, right, from the point of release all the way down to the splash, should be less than the 2 seconds, right? So we calculated before in part A, let me just label that here, this was part A, we calculated the time, we calculated the distance, assuming that the time was 2 seconds that it took for the rock to hit the water, but it's not. It's not 2 seconds, it's actually less. Because if we're perceiving the sound in 2 seconds, that perception took 2 things. It took the time in which the rock actually hit the water, and then it also took the time for the sound wave to travel back up the well, right? So let me write a formula. Right, so I can create a formula that might sound like this. So the total time, okay, from the time of perception of the sound should equal the time it took for the rock to fall plus the time it took for the sound wave to travel up, right? Okay, so that should make sense. That's basically what we were just describing. So in terms of now, let me just plug in a number, right? We know the total time here, the total time from the point at which it was dropped to the sound wave being produced and returning back was 2 seconds, 2.000. Okay, and that should equal now, and I'm just going to abbreviate here slightly, the time for the rock to hit the water plus then the time for the sound wave to travel back up the well. Okay, so this is one equation that we're probably going to need. Okay, now the second part of this is actually really important. And I think this is, well, the first part here, identifying this thing about the time is important, but the second key critical part is, now how do I find out these times? And we have to find something in common between the time the rock fell and the time that the sound wave traveled up. So again, if I draw a simplified picture down here at the bottom, okay, now remember, the rock is going to fall some distance, right? So I'll call that distance x, okay? And since it's traveling downward, actually I'm going to call it negative x, okay? So it's traveling some downward distance. I mean, technically what I should be doing here, if I'm talking about y values, I should be using the term y, but I'm just being a little lazy. We'll worry about that in the next chapter. So now it's traveling downwards, right? So I'm just calling it negative x. And also then the sound wave that's being produced here is traveling back up. So how far did the sound wave have to travel back up? That's right, positive x now. So wait a minute. So what's in common between these two frames of the problem? Well, the commonality is the displacements, is the x's. That's the key. So watch what I'm going to write. So isn't it true that the displacement, by the way, the negative displacement, right, of the rock falling, shouldn't that equal then the positive, because the sound wave is traveling now upwards, the positive displacement of the sound wave rising? Right? That's true. The displacements are equal. That's the important key. So now we have an equation. So now what we're going to be looking for in the upper right-hand corner. So now we got to start thinking about some of these formulas, which formulas I can use to start plugging in to help me expand this formula a little bit. So this could be like a little bit of a guessing game or whatnot. But what we can do is we can kind of consider, let's think about what's going on in terms of the rock falling. Well, the rock is falling a certain displacement that we talked about here, right? It's falling a certain amount here, right? It's falling a certain amount. What else do we know? Well, we also know that the initial velocity, right, is 0. We also know that the acceleration is 9.8. Essentially, we know everything we did over here in part A, right? We just know that it's not 2 seconds anymore, okay? So those are the assumptions. And not the assumptions, those are the knowns. So what I'm going to do here is instead of actually writing this displacement function, what I'm going to do is substitute in the rest of equation number 2. So take a look at the top. I'm going to substitute this whole term in for my x. Okay? So now it's going to look like negative. So now I'm going to write the initial velocity of the rock times the time it took for the rock to fall, plus 1/2 times the acceleration that the rock is experiencing multiplied by the time that the rock took to fall squared. Okay, now what am I going to do? Why don't I use the same formula now for the sound wave rising? So let's see. So equals then, right? I don't even need the parentheses, equals the initial velocity of the rock rising, of the sound wave rising, okay, multiplied by the time it took for the sound wave to rise, plus then 1/2 of the acceleration of the sound wave rising, multiplied by the time that it took for the sound wave to rise squared. Okay, now let's see if we can cancel some terms or get rid of some stuff. So let's take a look at this. What's the initial velocity of the rock when it's released? It's 0. So guess what happens to that term? It goes away. So now let's see if we can start simplifying it a little bit. So now this is negative, right? 1/2. What's the acceleration that the rock is experiencing? Right, negative 9.80 because it's gravity. What's the time that it took for the rock to fall? I don't know. So just leave it tr squared. Okay, so it's getting a little easier. Now take a look at the right-hand side. What's the initial velocity of the sound wave? Well, the sound wave, it told us in the problem it's 332 meters per second. Okay, so is that the initial? Well, yeah, It's the initial speed. It's also the final speed. Why? Well, because sound doesn't experience an acceleration here. Gravity's not pulling on it. So the initial velocity of the sound wave is going to be 332, right? 0.00. What's the time? And then that's multiplied by, right, the time that it took the sound wave to rise up, which we don't know yet. That's fine. Plus then, what do you think about this term? What's the acceleration that the sound wave is experiencing? Zippo. There's no acceleration on that sound wave. So that's gone, right? Because it doesn't have any mass. So there's no, gravity's not pulling on it. So that whole term goes away. Okay, great. So now I'm left with this equation. So why don't we clean it up, make it look pretty? All right. So let's do some math on this side. Okay, so we'll get, I'm actually going to write the results on the upper right hand, right here, I'll write some results. So -1/2 times -9.80 should be then a positive 4.90, that's TR squared, is equal to now 332.00 TS. Now look at this. Here's one formula, and guess what? Here's my other one in terms of the star. I'm going to write them right next to one another. 2.000 is equal to TR plus TS. So what do you notice? Well, you might notice in one case I capitalized the T's, in one case I lowercased them, but that would be valid. But if you notice, the capital T and lowercase t, they're the same thing, but now I have two equations with two unknowns. We can solve this now. This is just a simple system of equations. So I can solve it. This is great. So why don't we do this? Let's solve this equation for TS. So subtract the TR. Okay, so now I would have TS equals 2.0000 minus TR. Now what can we do? Now we can take this result, since it's equal to TS, and plug it into this equation. Awesome. Great. So let's do that. So now that equation is going to become 4.90 TR squared is equal to 332.00 multiplied by 2.0000 minus TR. And let me just lowercase that TR, by the way, just so that they're all consistent now. Great. Let's do some distribution. 4.90 TR squared is equal to then, so this is just double it, right? And we're going to have, it looks like 5 sig figs. So this should be 664.00 minus, oh man, so many sig figs. So I'm just, forget about the sig figs. TR, I'm running out of space. Okay. Now what I realize is I'm probably going to be dealing with a quadratic. So let's get all of these terms on over to the other side. So we got to subtract them or add them. Right, so I'm going to write the result down here at the bottom. So we're going to have 4.90 TR squared plus 332 TR minus 664 is equal to 0. Now what can I do? Well, here's your A, here's your B, here's your C. Plug it into the quadratic. All right, so I'm going to plug it in. I got a program in my calculator. So let's plug in A is 4.9, B is 332, C is negative 664, and I get a value of now, so T, there's two values, but just reject the negative one. I'm not going to write the negative one because I'm running out of space. Just reject the negative one because the time has to be positive. So we got 1.94 seconds, and that's TR. Now that should make sense, right? So remember, the total time was 2 seconds between the time the rock fell and by the time we perceived the sound. But that includes the time it must have taken for the sound wave to be reflected, right, back up the well. So the true time that it takes the rock to hit the water is 1.94 seconds, which is slightly less than the 2. So finally, now it says to calculate the distance. So guess what we're going to do? We're going to do the same thing we did basically up here in part A, but instead of using my 2 seconds, I'm going to use now the 1.94. Okay, so I'm just going to rewrite the equation I used here. So the displacement is equal to the initial velocity times time plus 1/2 acceleration times time squared. Right, my displacement is what I'm looking for. The initial velocity was 0, so that whole thing goes to 0. Plus 1/2 of the acceleration, which is negative 9.80, multiplied by the time squared, which is 1.94 now, squared. Okay, just plug it in. So take out the calculator, and let's do 0.5 times negative 9.8 times 1.94 squared, and it's now negative 18.4. So this is now negative 18.4 meters. Okay, and that is indeed the answer. All right. As far as the distance, that's the technical displacement in terms of its sign, but the distance value would just be 18.4 meters. So notice that if we don't take into account the time that it takes the sound wave to travel back up, we overestimate the true height of the well here, or at least the distance between the rock and the water. Number 56. A steel ball is dropped onto a hard floor from a height of 1.5 meters and rebounds to a height of 1.45 meters. Calculate its velocity just before it strikes the floor. Okay, so we have a ball and it falls down, and it's just dropped, so we know its initial velocity here is 0. And it says that it falls a total of 1.50 meters until it hits the floor. We'll assume the floor is here. And we know since the ball is being dropped and it's essentially floating in air, it's not really floating, it's moving, but it's freely suspended in air, that we know the acceleration of the ball, and that is the same as gravity, so negative 9.80 meters per second squared. What else do we know here? It now wants us to find, and we don't know the time, right? We also don't know the final velocity, meaning when the ball finally strikes the floor here. We can try to find that though, and actually that's what the question letter A is asking. Calculate the velocity just before it strikes the floor. So we want to calculate the final velocity here. So how do we do so? Well, let's look for a formula that relates our displacement. Okay, now remember, when we plug in the displacement, it has to be negative because it's traveling in the negative y direction. Okay. Alrighty, so let's see. So we need to use a formula with displacement, initial velocity, acceleration, and then we have to solve for final velocity. So it looks like the best choice here would be equation number 4. Right, so we'll write final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration multiplied by the displacement. So the final velocity squared is going to equal the initial velocity, which is 0 squared, plus 2 times the acceleration, which is negative 9.80, multiplied by our displacement here, which is negative 1.50. Okay, so the final velocity squared will be, let's just plug that into the calculator, so 2 times negative 9.8 times negative 1.5. We get a value of 29.4, and then we take the square root to get rid of the square. So now we find that the final velocity will be equal to plus or minus, because remember, whenever you take the square root, it has to be plus or minus 29.4. So we get a value of 5.42 meters per second. Now, which value are you going to choose, or which sign, I should say, you're going to choose? You're going to choose the positive or the negative. Consider the direction of motion. Which way is it going, up or down? It's moving down, right? So we would choose the negative direction. Okay, so that's fairly straightforward. Let me just erase this and I'll put the negative sign there. Great. So that's the final velocity. And that completes letter A. So that should be fairly straightforward. So now let's take a look at letter B. Calculate its velocity just after it leaves the floor on its way back up. All right, so let's draw a new little diagram here. So now, after it hits the floor, the ball is going to bounce back up. All right, we want to find the initial velocity here. We don't know what it is. That's what it's asking us to calculate. We do know that it is going to reach an ultimate height, as it told us in the problem, of now 1.45 meters. Okay, great. So that's my displacement. This time it's positive because the ball's moving in the positive y direction. I also know it's going to reach an eventual, once it reaches its highest point, what's the velocity up here? What's the velocity when the ball gets to its highest point? 0, right? So for this problem, that's considered the final velocity, because that's my frame. And since the ball's in the air, right, we also know the acceleration. So it's negative 9.80 meters per second squared. So consider everything I wrote down, acceleration, displacement, final velocity, initial velocity. What equation relates all of them? Same one, right? Equation number 4. So for letter B, let's write it out. Final velocity squared is equal to the initial velocity squared plus 2 times AX. Okay, so the final velocity now is going to be 0 squared. The initial velocity is something. We're trying to figure that out. Sorry, VI squared plus 2 times the acceleration, negative 9.80. And now the displacement is a positive 1.45. Great. So 0 is equal to VI squared minus, let's do the math, 2 times negative 9.8 times 1.45. Value comes out to be negative 28.4. Okay, so I'll add this value on over to the other side, 28.4. Notice how now it becomes positive, which it should, because we have to take the square root now. 28.4 is equal to VI squared. Take the square root. Remember, your answer will be plus positive and negative here. Okay, that equals, okay, let me just try that again. That equals a positive negative now, square root of 28.4. Great, so 5.33. So we get 5.33 meters per second. Okay, great. So that takes care of letter C. So now let's move on to, that takes care of letter B. Let's move on to letter C. So now it says calculate its acceleration during contact with the floor if that contact lasts 0.08 milliseconds or 8 times 10 to the minus 5 seconds. Okay, so when we think about this, we can just think about a simple acceleration formula. So remember, basic acceleration is change in velocity divided by change in time. Okay, now the change in velocity value, is going to be the final velocity minus the initial velocity divided by time, right, or the change in time. Okay, so given the context of this question, what is the final velocity? Well, you might mistakenly say, oh, here it is. Right, this is it. And that's not the case. I mean, that was the final velocity, but that was the final velocity for part A. In part A, I ended the problem as soon as it made contact. So it actually won't be the final velocity for now this equation. Why? Because now I'm only considering, if I now zoom in here, and I'm going to really zoom, so the ball's coming in and it's just making contact. Right, it just made contact. What's its velocity? Well, that's what we found over here, negative 5.42. And then it's going to rebound, right? And all of a sudden it's going to come back up after it hits, and then it's going to be 5.33. So this is essentially the initial value, and now this is the final in terms of this frame. And they gave me the time in which the contact lasted, right? That was the 8 times 10 to the minus 5. Okay, so those are the values we're going to put in here. So we have the change in acceleration will be the final velocity, which is actually 5.33, then minus a negative 5.42 divided by 8.00 times 10 to the negative 5. So let's throw that into the calculator, and let's see what we get. So we get 5.33, essentially plus, because it's two negatives, 5.42, and then take that answer and divide it by 8 times 10 to the minus 5. And we get a value of approximately, I'm going to do 3 sig figs, 1.34 times 10 raised to the 5. So that's 5 meters per second squared. So that is the acceleration there. Okay, wonderful. Now, letter D. So how much did the ball compress during its collision with the floor, assuming the floor is absolutely rigid? So what does this word compress mean in terms of our physics variables? Acceleration, velocities, times, or displacements? Well, it's probably going to represent a displacement, right? Because that's the only thing, when we're talking about compressing an object, talking about squeezing it, right? and the length is changing. So it makes sense that we're talking about an x value there. All right. So for letter D, let me put that over here on the right-hand side. So we want to consider what we know, right? Remember, the frame of the problem is essentially right here again. Okay, so I'll redraw it. So the ball is just making contact with the floor here. It has an initial velocity of, as we mentioned, negative 5.42. Then as soon as it hits the floor here, it's going to rebound and come back up with a velocity that's considered now the final velocity of 5.33. We just calculated now that its acceleration is 1.34 times 10 to the 5, right? So what do we want to find? Again, the key here is knowing that the compression is all about finding the displacement. So this is simple now, right? If we look, we know the initial, we know the final, we know the acceleration. How do we find displacement? Man, it looks like, again, we're going to be using equation number 4. Popular equation in this problem. So we get the final velocity equals the initial velocity plus 2 times the acceleration times time. 2 times the acceleration times displacement. So the final velocity here was 5.33. That's squared. Then the initial was negative 5.42. That whole thing's squared. Plus 2 times 1.34 times 10 to the 5th, multiplied by then the x. I'm just going to shove it down there. So let's do it. 5.33 squared. That works out to be 28.4. Negative 5.42 squared. That works out to be negative, well, it would be positive, 29.4. And then 2 times that acceleration should be now 2 times 1.34 times 10 to the 5. Right, 2.68. So hold on. This is going to be 2.68 times 10 to the 5x. Okay. Let's subtract this on over. So we get 29.4 minus 29.4. Okay. So this should just be a negative 1. Negative 1.0 is equal to now 22.68 times 10 to the 5th. Right? And that's x. And then just divide this on out. 2.68 times 10 to the 5th divided by 2.68. 2.68 times 10 to the 5th. So the steel ball will change by this displacement. So negative 1 divided by 2.68 times 10 to the 5. Okay, great. And we have here, so it comes out to negative 3.73. Hold on one second. Yeah, 3.73 times 10 raised to the negative 6. And that'll be in terms of meters. And that sounds reasonable for a steel ball. Okay, it shouldn't really compress by that much. Number 57. A coin is dropped from a hot air balloon that is 300 meters above the ground and rising at 10 meters per second upward. For the coin, find A, the maximum height reached. Okay, so let's draw a little picture. So we have this hot air balloon. Okay, and it's rising it says it's rising at 10 meters per second, right? So the velocity here, and I'm going to start my problem with this. So the velocity will be initial, and it's going to be 10 meters per second, and it's upward, so it's positive. We also know that the balloon is 300 meters above the ground. Right, so this 300 meters from the ground. Okay, wonderful. Now it says a coin is dropped from the hot air balloon. So find the maximum height of the coin. Okay, so here's the coin, and it's just going to be dropped off the side. But the thing is, remember, the coin is moving with the balloon. So the coin is also moving with an initial velocity here of 10 meters per second upward. So it's positive. Okay, great. So once the coin is dropped, it's actually still going to move upwards. It's going to be in the air, so therefore it's going to be experiencing acceleration due to gravity, meters per second. And what else? And that's really it. That's actually all we need in order to figure out the problem. Now remember that this coin is eventually going to reach a high point, and then it's going to come back down, and then go all the way back down. So there's a special, this point is special, right? Because this is the point where the velocity is equal to 0. Okay, so for the part A, I'm going to call this the final velocity. So my frame is, here's the initial state, here's the final state. Okay, so now knowing all that, I know the final velocity, I know the initial velocity, I know the acceleration. Now can we find the displacement that the coin reaches, or the height that the coin reaches? Yeah, we can, right? We can use equation number 4 here to help us do that. So for letter A, let's write it in. Final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. Final velocity is 0. Initial velocity is 10, so that's squared, plus 2 times the acceleration, negative 9.80, times then the displacement, which is x. So this is 0 is equal to 100. Okay, then minus, right, 19.6x. Add the 19.6x to both sides. Great, that cancels. So we got 19.6x is equal to 100. Then divide out the 19.6. And now we find that our displacement value here is simply 5.10. Great, so this is 5.10, and that's in terms of meters. So we know that from this particular location to the highest point, it went 5.1 meters. Okay, now B. So now it says, for the coin, find its position and velocity 4 seconds after being released. So let's first work on its position 4 seconds after it's released. Okay, so we want to find the x value, right? I mean, it's really a y because it's moving up and down, but it doesn't really matter. X represents displacement. So, we're trying to find x, right? We're trying to find it then 4 seconds after it's released, so we know the time is 4 seconds. Again, we also know the initial velocity of that coin was going to be 10 meters per second. We don't know the final velocity. Actually, that would be one of the questions, right? Because it's asking us to find the position and its velocity 4 seconds after. So we don't exactly know. And then what else do we know? It's also in the air, right? So it has an acceleration of negative 9.80 meters per second squared. Okay, great. So I need to know x, and I know the time, I know the initial velocity, I know the acceleration. So what formula? Right, number 2. So let's write that on the right-hand side. So the displacement is equal to initial velocity times time, plus 1/2 times the acceleration times time squared. So the displacement here will be equal to the initial velocity of 10 multiplied by the time value of 4 plus 1/2 times the acceleration, negative 9.0, times the time squared, which is 4 squared. Okay, great. So now all we have to do is just plug it in, right? So it's going to be 10 times 4. I don't know why. That's 40. We don't need a calculator for that. So 40, now this is going to be minus 0.5 times negative 9.8 times 4 squared, negative 78.4. So the displacement now is going to be 40 minus that answer. So negative 38.4. So negative 38.4 meters. Now what does that mean? This means that it's 38.4 meters below the height, below the height of release. So if it was released here, it's going to travel up, then turn back down, and then it'll be somewhere maybe here after 4 seconds. 4 seconds it'll be here. Why? Because the displacement was negative. Okay, and it came out to be negative 38.4. Okay, wonderful. How do we now find the final velocity after it was released? So now that question is asking me for this part right here, the final velocity. So again, we can simply use equation number 1 to help us find this, right? Where the final velocity is equal to the initial velocity plus the acceleration times time. So the final velocity is going to be equal to the initial velocity, which is 10.0 meters per second, plus the acceleration, negative 9.80, multiplied by the time value of 4. So then the final velocity is now simply going to be negative 9.8 times 4, and then add to that 100. Oh, excuse me, just 10. Not 100, 10. So the velocity is now negative 29.2 meters per second. Now that does make sense based on the displacement I just found, because this is telling me, this negative sign is telling me that it is traveling down in the negative y direction. So this should make sense. All right, so we're good here for letter B. Now let's take a look at letter C. So it says the time before it hits the ground. Okay, so how can we think about this now? Well, how do I want to think about it? Actually, what we can do, we can do this in one step. Okay, so let's label some knowns. Remember, we have a balloon, right? It's traveling upwards. It has an initial velocity of 10 meters per second. 10 meters per second. We know the acceleration due to gravity here is negative 9.80 meters per second squared. We also know that the distance, the height between when the coin is released and the ground, right? So let me just draw actually the coin on this side. We know the distance between the height of the coin and when it's released and the ground is 300 meters. So that's actually my x value. Okay, and they are asking us for time. So do we know an equation? So T is the question. T is the question. Do we know an equation that relates displacement, time, initial velocity, and acceleration? We do, right? That's going to be equation number 2 again. So let's write it out. So the change in displacement is equal to the initial velocity times time plus 1/2 at squared. The displacement, now remember, it's negative because it's traveling down, right? The coin is eventually moving down in the negative y direction. So it's negative 300. The initial velocity was positive 10 because it's traveling upward initially. The time value is what we're looking for. Plus then 1/2, the acceleration is due to gravity, so negative 9.80. Again, multiplied by t squared. So let's just clean it up a little bit. So this becomes 10.0 t, and then this becomes now negative 4.9 t squared. Move both of these values over to the left. All right, so add this one, subtract that one. I'll write the result here on the right-hand side. So the result would be 4.9 t squared. All right, minus then 10.0 t minus 300 is equal to 0. You have your quadratic. So you'd have to use a quadratic formula, right? T would be equal to negative b plus or minus square root of b squared minus 4ac all over 2a. Or here's your A, here's your B, here's your C. Take a look at one video online and figure out how to program the quadratic formula in your calculator if you have like a TI-84 or something. So all I have to do now is plug in my A of 4.9, plug in my B of negative 10, and plug in my C of negative 300, and I get my T values. So I get 2 answers. Only choose for time, only choose the positive answer because the negative 1 does not make any sense. I started at time 0, I could not have gone backwards in time. So the positive answer is 8.91 seconds. So that will be the time before it hits the ground, 8.91 seconds. Number 58. A soft tennis ball is dropped onto a hard floor from a height of 1.5 meters and rebounds to a height of 1.10 meters. A. Calculate its velocity just before it strikes the floor. All right. So this problem is actually very similar to number 56. So if you want additional practice on a problem like this, please be sure to check out my other video on number 56. So soft tennis ball is being dropped. Right? So since it's being dropped, we know the initial velocity here is going to be 0 meters per second. And it's going to be dropped and eventually it's going to hit the floor. Right? So it's going to travel down. And it says that the height of the ball is 1.50 meters above the ground. Okay. And then it says it rebounds to a height of 1.1, but we don't need that for part A. So we know since the ball is being dropped and now it's in air, we do know that the acceleration of this ball is going to be equal to that of gravity, which is negative 9.80 meters per second squared. And now from here, right, also don't forget that this is the displacement, the 1.50. And now we can just simply plug in, we can find an equation now and plug in our variables to find our final velocity. So remember, I need an equation with displacement, initial, acceleration, and final. And it looks like equation number 4 will fit the bill. So for letter A, let's write that. Final velocity is equal to the initial velocity squared, right, plus 2a times the displacement. Now the final velocity is what we're looking for, so that's my unknown. The initial velocity is 0. The acceleration is negative 9.80. And the displacement here is going to be negative 1.50. Be careful because the object is moving down in the negative y direction, therefore its displacement must be negative. So let's just plug in the values into our calculator. So 2 times 9, negative 9.8 times negative 1.5. It works out to be 29.4. Right, so 29.4. Take the square root of both sides. We get rid of the square. And remember, whenever you take the square root of a number, it's plus or minus. Now take the square root of that. So it comes out to 5.42. 5.42, that's meters per second. Now we have to think about what sign is it, positive or negative? What do you think? Think about the direction in which the ball is traveling in this frame. Right, it's traveling down, so therefore it would be a negative velocity. All right, so let me just erase these signs, and I'm just going to put the negative version in there. So that should be the final velocity for part A. Let's take a look now at part B. All right, so now it says calculate its velocity just after it leaves the floor on its way back up. So this is where the 1.10 meters is going to be important. So let's just draw a another picture. Okay, so this is for letter B over here. So again, after it hits the floor, right after it makes contact, it's now going to be on its way up. And on its way up, it has some initial velocity, I don't know. But eventually it's going to travel up and it's going to reach its highest point. And what's so special about its highest point? The highest point that it reaches then, the special thing about that is that we know that the velocity at that location is 0. So if I frame that this is my initial velocity at the bottom, then the velocity up here when it's 0 should be my final value. Okay, great. Since the ball's in the air, I also know that the acceleration is the same as that due to gravity, so negative 9.80, okay, meters per second squared. And what we are looking for is we are now looking for the velocity just after it leaves, right? So that is what I already noted there with the question. And do we know anything else? Well, yeah, right? It told us the height at which it reaches. It says it reaches 1.10 meters above the ground. So that's my x value, right? So now think of a formula that relates these 4 variables: displacement, final velocity, initial velocity, and acceleration. And oh wait, it's the same formula again, number 4. So let's write it down. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So the final velocity is 0. The initial velocity is what we're looking for, plus 2 times the acceleration, which is negative 9.80. And now the displacement is a positive 1.10 because the object is moving upwards. So let's clean it up a little bit. And let's combine some terms. So 2 times negative 9.8 times 1.1. So we got negative 21.6. Okay, then add the 21.6 to both sides. Add the 21.6 to both sides. That cancels. Now we're left with 21.6 is equal to initial velocity squared. Square root both sides to get rid of the square. And we find that the initial velocity here should be simply the square root of 21.6. And that works out to be 4.65. So 4.65 meters per second. And yes, perfect. Okay, so that sounds good to me. All right. So part B is now out of the way. Now let's take a look at part C. All right, so part C now is talking about, part C is talking about calculate its acceleration during contact with the floor if that contact lasts 3.5 times 10 to the minus 3 seconds. Okay, so draw another little picture here. So here's the ground. And the ball, we're taking a really microscopic look at when the ball just hits the ground and then comes back up. So when the ball just makes contact with the ground, its velocity, as we calculated in part A, its velocity is negative 5.42 meters per second. Now I know that that was the final velocity that I calculated for part A, but in terms, these terms are relative, meaning final and initial. So in this part of the problem, the way I'm framing it, since I'm starting the problem with this, as the start of it is hitting the ground, that becomes my initial now. And then the ball is going to bounce back up, right? So when it bounces back up, that velocity is, as we just calculated, 4.65 meters per second. So in terms of relative to the initial, that should be the final now. So the final velocity here is 4.65 meters per second. And now what we're looking for is we're looking for the acceleration. And they also told us that the time it takes to go from hitting the ground to bouncing back up was 3.50 times 10 to the minus 3 seconds. So it sounds like we have enough information we need, right? Which formula are we going to use here that relates all four of those variables? It could be we could just use equation number 1 at the top, right? So let's write that. So the final velocity is equal to the initial velocity plus the acceleration times time. So the final velocity here was 4.65. The initial velocity was negative 5.42. The acceleration is what we're looking for, and the time was 3.50 times 10 to the minus 3. Okay, great. So add the 5.42 on over. Add the 5.42 on over. That cancels. So now when we do the math here, this should work out to be 10.07. And now that will equal 3.50 times 10 to the minus 3a. Divide this out. Divide the 3.5 times 10 to the minus 3. Divide the 3.5 times 10 to the minus 3. And now we're going to find a. I'm going to put it just down here. A is going to equal, so 10.07 divided by 3.5 times 10 to the minus 3. And it'll be 2.78, 2.87, well, a little dyslexia there, I guess. And actually I have to round, so 2.88, so I'm just wrong overall here. So 2.88 times 10 to the positive 3. Wow, I'm really off. I mean, this answer is right here. I just can't speak at the moment. And that's in meters per second squared. Okay, great. So now we know the acceleration. Last but not least, finally, hopefully we'll finish this problem. Letter D now. It says, how much did the ball compress during the collision with the floor? So what does this word compress mean in terms of a physics value here? Is it acceleration? Is it velocity based? Is it time? Or is it distance? Well, probably closest to distance, right? Or displacement. We're talking about compression, right? So we're changing the length of the object. Sounds like it'd be most similar to a displacement. So now let's consider what we know. Now remember, we're talking about the collision. So again, the picture, we're talking about this case where the ball just hits and then comes back up. Now we already talked about all the variables. We know the initial velocity. We just wrote it down before. Negative 5.42. We know the final velocity. That was 4.65. We now know the acceleration because we just calculated at 2.88 times 10 to the 3. Okay, we also know the time of the collision. That was 3.50 times 10 to the minus 3. So we can calculate this a whole bunch of ways if we like, right? We can use a bunch of formulas, but why don't we choose this one seems to be a favorite of the problem, number 4. So why don't we choose that? So we got the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity here is 4.65, and that's squared. The initial velocity was negative 5.42, and that's squared. 2 times the acceleration, which was 3.5, almost plugged in the time there, which is 2.88 times 10 to the minus 3. No, 10 to the third, Andrew. Man, it's getting late, as you can tell. And then multiplied by the displacement of x, and that's what we're trying to find, because that x will represent how much the ball was displaced or compressed. So let's do the math. So 4.65 squared. We need 3 sig figs, so it's 21.6. Take negative 5.42 and square it. It's positive now, right? So it comes out to 29.4. Plus then 2 times that acceleration. So 2 times 2.88 times 10 to the third should be 5.76 times 10 to the third times x. Great. Just subtract now the 29.4. Subtract the 29.4. And let's see what we get. So we get 21.6 minus 29.4. Comes out to negative 7.8. And that will equal really 7.8. It's only 2 sig figs now. That will equal 5.76 times 10 to the third x. I'm just running out of room, but now all you would do is just divide this out of both sides. Okay, so I'm going to put the x value on over here on the side. So you're going to take negative 7.8 divided by 5.76 times 10 to the third. And we get an answer, I'll put it in a scientific, we get an answer of negative 1.4, okay, because we can only have 2 sig figs now. 1.4 times 10 to the 3 minus 3. And that is in meters. So that's how much the ball, let me just change that line there. That's how much the ball should be compressed. Number 59, letter A. By taking the slope of the curve, verify that the velocity of the jet car is 115 meters per second at time equals 20 seconds. So this is essentially for figure 2.60. So first, look at the curve, the graph, and find time equals 20. So here it is. Now from there, let's just jot a line on up. We'll dot it. And right here is the position on the graph at time equals 20. Okay, great. So now, just make this a little neater, get rid of those dots. So what we want to do now is we want to find the line tangent to this point. So what does that mean? Well, the slope of the curve or the line tangent is the line that just grazes the graph at this point, but it actually doesn't cross the graph. So a tangent line would look actually something like this for this particular point. It would just barely touch the graph at that point. So just like that. That would be the tangent line. Okay. Now that looks like a fair tangent line. It doesn't look that bad. All right. Now what we're going to have to do here is we're going to have to make a couple of assumptions. So we may not land at this value of 115 meters per second exactly, but we should be close. All right. So now what I want to do is essentially this line will represent the slope at this point. Okay. It's close enough. It looks like it's off by a slight bit, but it should be reasonable. We should get around 115, somewhere around there. So now how do I calculate the slope of a line? So we use the slope formula, right? y2 minus y1 over x2 minus x1. Okay, great. So I have to find essentially 2 points on that line, right? So let's choose, this point seems easy. It looks like it's going to intersect the graph right about in the middle, right, of 5 and 10. So what would be the coordinates for this point? Remember, the x coordinates always come first. So it'd be about 7.5. And then we don't have to go up at all on the y axis, so that would be 0. Okay, so I'll call this x1, y1. And then I want to find a point somewhere over here. All right. So maybe I'll choose 30 here. This is where it looks like it's about 30. Right, so the coordinates here would be the x value would be 30. And then if I were to draw kind of a line on over to here, maybe it's about 2,500. That looks about reasonable. So it'd be 30, 2,500. And again, this would be now my x2, and this is my y2. So all we have to do is plug it in now to the slope formula. So my y2 value I mentioned was 2,500. The y1 value was 0. The x2 value was 30, and the x1 value was 7.5. So let's just do some math. So now this is 2,500 over what looks to be 22.5. And now let's do that in the calculator. So 2,500 divided by 22.5. I get 111. So that's pretty darn close. 111. This would be meters per second. Why is it meters per second? Well, what were the units of the y-axis? Right, the units of the y-axis here, okay, was position or meters. So I got an m, and m. What are the units of the denominator of the x-axis of these numbers? Well, that looked like time in seconds, right, on the graph. So seconds, seconds, seconds. Meters per second. Easy. Okay. So now that takes care of letter A. Now let's take a look at letter B. By taking the slope of the curve at any point on figure 2.61, verify that the jet's car acceleration is 5 meters per second. So again, we'll get an answer of about 5, but it might not be exactly 5. So on this curve, notice this is just a nice straight linear line. It doesn't have any type of curve to it at all. It's nice and straight. So I don't have to do this whole tangent line thing or whatever. I can just find 2 points on this line and calculate the slope. So let's choose the initial point here. That point has an x value of 0. And it looks like it has a y value of, it's a little tough, I don't know, maybe 17? Something like that. Let's call this x1 and this one y1. Now let's go all the way out to here. Let's go out to this point. That looks like it has an x value of about 30, right? And its y value probably is going to be about 160, right? So this should be about 160. Let's call this x2 and this y2. Same thing now for letter B. Slope is equal to y2 minus y1 over x2 minus x1. So my y2 value was 160. My y1 value was 17, my x2 value was 30, and my x1 value was 0. So let's do some math. So the numerator should work out to be 143 over 30. Okay, and now the slope will be, let's plug that into the calculator, 143 over 30, and it works out to 4.77. So again, like I said, it's going to be hard to get it exact because I don't have grid lines here. So I have to estimate it, but these are reasonable. These are way close enough. So this is meters per second squared. Okay, perfect. And why is the units here meters per second squared? Well, let's go back and let's think about what are the y units in the problem? Well, the y units, if you look back at the graph, is meters per second. So this is meters per second. Right, meters per second, and this is meters per second. And then what are the x values? The x units on the graph, the x units are seconds. So seconds, seconds, seconds. Meters per second is meters per second squared. Number 60. Using approximate values, calculate the slope of the curve to verify that the velocity at t is equal to 10 seconds is 0.208 meters per second. All right. So we have a curve of a position versus time graph. Okay, now we have to remember that the slope of a position versus time graph will be the velocity. Okay, so the slope is equal to v. Why? Remember, slope is equal to, slope is really m, right? So slope is really change in y over change in x. What are the units for y in this problem? Meters, right? So the slope here is really meters per, or divided by, what's the units for x? Seconds. Meters per second. What are the units for velocity? Meters per second. All right. So now the slope of this graph will equal the velocity. Great. They want to find the velocity at 10 seconds. So here's the point. Hold on. Here's the point 10 seconds on the graph. Now it looks like to me that this graph kind of comes in like this a little bit at that point. All right. This line doesn't look totally straight to me. But, I mean, we could probably just assume it's a straight line. It's really off by a slight bit. You know what? I'm just going to assume that it's a straight line. Because otherwise I'm going to be off by such a little amount. But it's how to calculate this is important, not getting the exact value. So I'm just going to find, so although I'm trying to find it at 10, I'm just going to assume that this thing is a nice straight line. So I'm going to pick my, probably pick my endpoints or somewhere around there. So I'm going to use this as 1 point, all right, to calculate my slope. So that has an x value of 0. And it looks like it has a y value of maybe 2.5 or 3. I'm going to say it has a y value of 3. So this is my x1 and y1. Now let's find another point somewhere. Maybe I'll choose this point over here at 60. Okay, so that has an x value of 60. And if I were to draw a little line on over, it looks like it probably would be just above 15. So let's call it 16. Okay, so this is going to be my x2 and my y2. So now remember, calculate the slope. We just mentioned the formula before. Change in y over change in x. Well, what does that mean? All changes, and almost all changes in science, we'll be dealing with, when they talk about change, they're going to talk about the final or the second value minus the first value, or the initial. Okay, so x2 minus x1. So my y2 value, as I defined up on the graph, is going to be 16. My y1 value is going to be 3. My x2 value is going to be 60, and my x1 value is 0. So now the slope here is going to be 16 minus 3, which is 13, over 60. Take out your calculator now and plug that in, 13 over 60. Cool, close enough. Right, so the slope here comes out to be 0.217, and again, I already went over the units, it should be meters per second. So I verified it. Like I said, guys, it's going to be off by a slight bit, but I'm not going to be able to get any more accurate than that. So as long as you know how to calculate, that's what's important. Number 61. Using approximate values, calculate the slope of the curve in figure 2.62 to verify that the velocity at t equals 30 is approximately 0.24 meters per second. All right, so we got to calculate the slope at t is equal to 30. So first locate t is equal to 30 on the graph. It's right there. Dot a line on up from there. And your point on the graph should be right about here. All right, so that's great. Now, in terms of calculating the velocity at this point, what we would want to do is draw a nice tangent line here. Okay, but I know this line that they drew in red is not totally straight, but it's straight enough, all right, for our purposes. So we're just going to estimate it, assuming that this red line is nice and straight. So we've got to pick 2 points. Let's pick the starting point here. That has a point value or coordinate value of the x coordinate is 0 and the y coordinate looks like it's going to be about 3. So let's call that our x1, y1. Let's find a point then out here at about 60. Okay, so that x value is 60. And it looks like, I don't know, the y value should be about 16 or 17. I'm just going to go with 16. All right, and let's call this my x2 and my y2 value. Why am I doing that? Why am I calling them y2, y1 and all? Well, remember, we have to calculate the slope. So the slope has a formula of change in y over change in x, which that breaks down into y2 minus y1 over x2 minus x1. So now just plug them in. So the y2 value we mentioned was 16, the y1 was 3, the x2 was 60, and the x1 was 0. So now this works out to about a value of, so what do we got here? So this is 16 minus 3, so that's 13, and this is 60. So now take out your calculator. Let's plug it on in. So we got 13 divided by 60, and that works out to about 0.22, right, if I were to round to two significant figures. And that again will be meters per second, because again, look at your units, change in y. What are the units of y? Well, meters divided by change in x. What was the x coordinate on the graph? Seconds. So meters per second. Number 62. By taking the slope of the curve in figure 2.63, verify that the acceleration is 3.2 meters per second squared at time is equal to 10 seconds. Okay, so first thing is, let's take a look at the graph we're dealing with. We're dealing with a velocity versus time graph. Remember that the slope of a velocity versus time graph is the acceleration. Okay, so slope of this graph will equal the acceleration. Why? Well, come down here to the answer section. The slope is equal to the change in y over the change in x. So what are the units of y in this problem? Well, it's velocity, right? Actually, instead of the units, I'm just going to write the letter v on the top. Then what are what's the value of the denominator? What's the x coordinate value? Well, that says time. So t. So what does this formula look like to you guys? Velocity divided by time, right? That may look familiar. That's acceleration. So if the slope is equal to v over t, and a is equal to v over t, then a must be equal to m. Simple syllogism. All right? Okay, so, all right, so that takes care of that discussion. Let's move on to now actually finding out what the slope is at 10 seconds. So let's go to the graph, and let's locate 10 seconds. There it is. Dot your line on up, and it looks like the point should be somewhere around here. Then erase all this stuff. Okay, great. So now remember, if I want to find the slope at this particular point, I have to draw a tangent line. A tangent line is a straight line that just grazes this point of the graph. It doesn't cross the graph at that point. It never cuts into the graph. It's just going to graze. It's just a little graze, like that Sebastian Maniscalco skit. It's just a graze where his wife bangs up the car or something like that. It's hilarious. You should check it out. Anyway, back to physics. So we have to draw a tangent line at this particular point. Okay, so let's do so. I'm going to try my best here. It looks like it's going to look something like this. Okay, that looks fairly reasonable. All right, we're not going to get exactly 3.2 as our answer, but we'll come pretty close. So now I have to pick 2 points on this line. Let me pick the point here where it intersects the y-axis. So what are the coordinates of that point? Well, the x value of that point is 0. And we got to estimate the y value, right? Maybe it looks like 1800? What am I doing? 1800. I must be looking at a different graph than you are, right? It should be about 180, it looks like. Okay, let's call this one y1. Excuse me, x1, and let's call this one y1. Okay, let's find another point. So it looks like 30, if I were to bring a line up, it looks like the x value of 30 would be somewhere around there. So that would have an x value of 30. And then its y value here would have, I don't know, what do you want to call that, 270? 270. Call this one x2 now, and call this y2. Okay, great. Now we have enough we need to plug it into our slope formula. So remember that I can rewrite the slope formula as m is equal to y2 minus y1 over x2 minus x1. Okay, so the slope is equal to our y2 value, which is 270, minus the y1 value, which was 180, divided by my x2 value, which was 30, and my x1 was 0. so now let's see what this works out to be. So let's take 270 minus 180. So that should work out to be 90. Okay, great. So 90 over 30. And that looks like it should come out to about 3.0 meters per second squared. Okay, why meters per second squared? Well, we talked about it already. It's the acceleration. Okay, so the acceleration they told me was 3.2. So I'm off by a slight bit, but we knew that going into it. It's almost impossible that I'm going to get exactly 3.2 because I have to create my own line and then I have to approximate where those points are. But this is definitely close enough. So as long as you understand how to do this process, that's what's important. Number 63. Construct the position graph for the subway shuttle train as shown in figure 2.18a. That's over on the right-hand side here. Your graph should show the position of the train in kilometers from t equals 0 to 20 seconds. You will need to use the information on acceleration and velocity given in the examples for this figure. All right, so this acceleration graph is the acceleration graph given back in the chapter. And the only other piece of information we need here, I think, is that the velocity of the train, let's assume as it starts at its initial displacement, let's assume that the velocity of the train is equal to 0 meters per second. Okay, so let's try to construct, we can basically just use the average acceleration graph to help us construct the velocity graph first. Okay, so it looks like the average acceleration, if I were to look at this black line, it appears that it might be about 1.8. What would you say? That sounds about right. 1.8 meters per second squared. And so I'm going to use the average velocity to help construct my velocity graph. So let's draw a graph. Straight line, and this is going to be the velocity. I'm going to say a v versus t graph. Okay, so time is on the x-axis, and that's in seconds. Velocity is on the y-axis, that's meters per second. Now we know that the velocity is 0 when the time is 0. Okay, great. Now let's look at the acceleration graph, and let's look at where the acceleration is 1. Again, I'm just going to use the average value of the acceleration. So what's the acceleration at 1 second? 1.8, right? Meters per second squared. So if I were to use the formula that the acceleration is equal to velocity over time, and I plug in the average acceleration of 1.8, and I know that occurs at 1 second, then I can calculate the velocity, right, of that object, assuming it was starting at 0, which is what we assumed. So the velocity here at 1 second will be 1.8. Okay, so let's go to the velocity graph and let's plot. Here's number 1, and let's say here's number 2. Okay, and let's say here's number 1. So it appears that the velocity is the point will be somewhere around here. Okay, great. Now let's move on to the next point. All right, let's now look at the point of 2 seconds, right? So again, the average velocity, the average acceleration is still the same, right? It's still 1.8. So if I were to now create another formula here, the acceleration is 1.8. That equals v over now 2 seconds. Right, so what would we get here? We would get a value of 3.6 for the velocity, right? Okay, so now let's go to our velocity graph. Let's graph the number 2 on the x, and then we got to go up to now 3.6. So this looks like it'd be about where 3 is. This looks like it would be around where 4 is. And we get a number here, right? Or a dot, I should say, a dot right about there. All right, now if you were to extrapolate this, I'm not going to keep going in terms of the math, but you'll notice the only value that's going to change here is the numbers down here, right? It's going to be a 3, and then a 4, and then a 5, etc. Okay, so I know, that being the case, that these values of the velocity are going to increase incrementally, and then they're going to increase by 1.8 every time. All right, so that kind of gives me a little insight now as to where the next point should be. So if I go and I graph 3, now what I'm going to do is essentially take the value of 3.6, which was the velocity, and just add 1.8 to it. And that comes out to 5.4, so my next point will be somewhere around 5.4. So it looks like it would be somewhere about, I don't know, here, right? And that should do it now. I can now create a nice line, and if we notice, this line should be linear. Okay, one of the dots is a little off, but that works. All right, so it's a nice linear line. That's always going to be the case, all right? Whenever you have an acceleration graph that looks like this, your velocity graph will always be linear and increasing. Okay. Now let's look at a graph. So this was velocity versus time. Now let's look at a graph of position versus time. Okay. So let's draw some axes here. Y-axis. Whoa, it's a little crooked. Y-axis. X-axis. Again, time, and now position or displacement, right, in meters is going to be on the left, on the y-axis, and then seconds here down at the bottom on the x-axis. So now we're essentially going to do the same thing, okay, but now we have to use the information about velocity to help us understand position, okay? So remember, this value right here was essentially velocity at 1 second. Okay, this was essentially the velocity at 2 seconds, right? The 5.4 would have been the velocity at 3 seconds, etc. So we'll use that to help us understand, all right, what's going on. So again, if the velocity was 0 at the beginning, I'm also going to assume that the position was 0 as well. Even though, I mean, here, if you look at the picture, it's showing that it's starting at 4.7. It doesn't really matter. I mean, we're just trying to get the general gist of what the graph will look like. All right, so let's just assume it's going to start at 0. So now, what's a general position formula or a general velocity formula, right? Well, velocity we know is equal to position or displacement over time. Reworking this formula to solve it for x, it would simply be that the position is equal to the velocity times time. Okay, great. So in order to find my position, I need to know the velocity and the time. So let's look. So let me change the color here. So what is the position at time 1 when time is 1? In order to figure this out, I would need to know the velocity, correct? So do we know the velocity when the time is 1? Well, yeah, right? We do. What is it? Well, here it is. Right? We found it. It's 1.8. So this is simply 1.8. Okay? Now, does that make sense? Well, let's see. So x1 is equal to 1.8. Okay, so let's plot it. So now we'll plot the point here. So this is 1. And this will be, we'll say that this is point 1 here. This will be point 2. Etc. So we have a point that's right about here. Okay, great. How about now let's do the next one. What about when the position is 2, or the position at time 2? We would have to know the velocity at time 2, right, which was 3.6. And then that would be multiplied by the time value, right, of 2. So what does that work out to be? So this is 3.6 times 2. And that works out to be 7.2. Okay, so let's plot that. So this would be 2. And now this is going all the way up here, right? So it looks like we're flying off the graph. Okay, so I don't know. Does this sound reasonable? Well, let's do a check. All right, so how would we check something like this? Well, maybe what we can do is we can use an alternative formula. Right, so what other formulas do we know of kinematics that might talk about position? Oh, wait a minute. Yeah, we do know that formula, right? The change in displacement is equal to the initial velocity times time plus 1/2 at squared. Ooh, where's the t? There it is. Okay, so let's see what happens when I plug in my initial velocity of 0, because that's what it's starting at, so that term drops out. Right? Remember, that's what I assumed here at the start. The initial velocity is 0. So that whole term goes to 0, then it's plus 1/2. The acceleration in the problem was, we found it to be 1.8 meters per second, and now the time, let's say, is 1 second, right, because I want to find the position at 1. So let's see what it works out to be. So take out the calculator, 0.5 times 1.8, and then times 1 squared is just itself. So wait a minute. This now came out to 0.9 meters. That's weird. So this told me when the time is 1, it should be 0.9 meters. And what I did over here told me that the value should be 1.8. So what was the mistake, guys? Did you catch it? The mistake is this. It's this value right here. It's not simply the velocity at time 1 or 2. It's the average velocity over the period. Okay? So what does that mean? Well, if at, let's go back to the velocity graph, if at 0 seconds it was 0, and then at 1 second it was 1.8, what was the average velocity? Well, you'd say it should be simple, right? 0 plus 1.8 over 2. What does that work out to be? Oh, 0.9. Well, not meters, but 0.9 meters per second. Interesting. Wait a minute, didn't I just find 0.9? Yeah. Right? And then what's this value over here in terms of the velocity? If I were to plug it in and then use the time of 1, what would it be? 0.9 times 1 is 0.9. All right? So you have to be very careful when you use these formulas, okay? This velocity here is not just simple, it's average velocity. Okay? So just keep that in mind. So this work, I was trying to see if you guys were going to catch that. Okay? I also wanted to show you how to, in case you go down a wrong path, how you might be able to say, let me check it in another way. Well, do we know any alternative formulas? Sure we do. We know this set. Now you're getting 2 different answers. So what's going on? All right, that's because this formula involves the average velocity. Okay, so we can continue using that formula, it doesn't matter. Or we can use the formula of the displacement. Okay, so let me just erase these points, right? So now the first point should be 0.9. So at x is equal to 1, when time is equal to 1, the position was 0.9. We just found that out over here. Now let's see what happens when time is 2. So let's do another formula here. So change in position is equal to the initial velocity times time plus 1/2 at squared. So the change in position is going to be, remember, this term is going to be 0 because the initial velocity was 0. So this just works out to 1/2 times 1.8, and now times 2 squared. Right? So let's see. Take out the calculator. 0.5 times 1.8 times 4. 3.6. So 3.6 meters. Okay, so that's going to be the distance when the time is 2. Right? So when time is 2, the distance will be 3.6. Okay, so let's graph that. So here's 3, here's 4. And this is looking now a little more reasonable. Right? Maybe it should be about there. Let's go out one more, okay? Let's go to 3. I'm going to do the calculation right over here. So I'll do it right here. So remember, x is equal to VIT, but the velocity, the initial velocity is 0. So I'm just going to simplify it to 1/2 at squared in this case, just because I'm short on room. So it's 1.8 times now 3 squared. And what do we get? So 0.5 times 1.8 times 3 squared. We get 8.1. So 8.1 meters. Okay, so now this is the distance or displacement when time is 3. So let's go to the value of 3 on the graph, and let's go up to about where 8 would be. 5, 6, 7, 8 is going to be somewhere up here, right? So it's always run out of room. Let me just erase that. So this is, again, the P versus T graph. And the line will extend a little bit. Okay. And now we're going to plot the point up here somewhere. So what's the shape of this graph now? Well, it's hardly linear, right? Because if it were linear, I would have to like start the line here somewhere, right? And the points are a little bit, I'm off by a little bit, but not by that much, right? So the graph is actually going to have this type of a shape to it. Okay. I could have done a little better there. Okay, it's a nice increasing curve. So this will always be the case whenever we have a positive acceleration. So whenever the acceleration graph looks like this, the velocity graph will look like this, and the position graph will look like this, always. All right, guys, thanks for checking it out. Hopefully this helped. Remember, always consider, do the numbers make sense? If they're sounding a little large, maybe try a different way or an alternative formula. Maybe there's something you might have missed. All right. Again, that'll help. Having those thoughts in your mind will help get you to that A level. Number 64, letter A. Take the slope of the curve in figure 2.64 to find the jogger's velocity at time is equal to 2.5 seconds. Okay, so let's take a look at this figure 2.64. Now, the graph is a position versus time graph, so you have to remember that the slope of this graph is equal to the velocity. Why? Well, slope is equal to change in y over change in x. Okay, what are the units for y in this graph? The units of y are meters. What are the units for x? Seconds. Meters per second. What are those the units of? Velocity. Easy peasy. Now, let's take a look at the time of 2.5. So let's look at the graph and locate the time value of 2.5 seconds. So it looks like it occurs, right? This looks like about 2.5. And if we scroll up, it actually looks like they marked this point out nicely for us. Okay, now, what this means is that we have to find the slope of the line that is tangent or just grazes the graph at this point. Okay, so what I need to do now is draw a slope line. And it almost looks like it's going to match, right? It looks like it's going to just match that line. So that's basically just what I'm going to draw here. There's a slight curve to it, but not enough to make a big difference here. All right, so that looks about accurate, roughly. All right, so let's now calculate the slope of this line. So we got to find m of this particular line. So let's write it down. Slope is equal to change in y over change in x. Okay, great. So let's expand that. So that's y2 minus y1 over x2 minus x1. What this means is that we need 2 points on that particular line. So let me choose the point here because that's really simple. Right? The point there is going to be 0, 0, 0. So let's call this my x1 and call this my y1. Now let's choose a point maybe, I don't know, about where the 25 mark is. That looks like it's about here. Right? And if I were to dot my way down, maybe it's about 7 or so, right? It looks like it might be about that. So the x-coordinate of this particular point right here is going to be 7, and the y is about 25. So call that now your x2 and your y2. So let's just plug them in now. Back to the slope formula. The y2 value we said was 25. The y1 value was 0. The x2 value was 7, and the the x1 value is 0. So just simplifying this a little bit, right? Subtracting by 0, nothing happens. So now my slope becomes 25 over 7. So plug it into the calculator. And the value becomes 3.57. Okay, so 3.57. So about 3.5 meters per second. All right, that's the slope value. So this would be the velocity. Okay, great. Now, let's take a look on the right-hand side. All right, the next graph figure, so letter B, so I'm skipping, I'm reading letter B but not reading it to you guys. So it now says letter B. Repeat this for 7.5 seconds. So now I have to go onto the same graph, find my value of 7.5 seconds. So it looks like here, right? I'm going to have to do the same thing. Okay, so let's draw the slope at that particular point. Looks like it's going to be a nice, relatively straight line here, right? Yeah, that looks a little off, right? So let me try that again. I'm not the best artist. Oh, wow, that got a lot worse. Okay. I mean, you don't have to be an artist to draw a straight line. Wow, okay, one more time, guys, one more. All right, I can deal with that. So now what we have to do is find the slope of this black line. All right, so I'm going to use the point here because that's where it crosses the x-axis. So I know that the y value is 0, and the x value looks like it's a little greater than 10, right? Not quite 11, but why don't we just call it 11 for now? All right, so call this x1 and y1, and then find a point, let's say right about here where the 25 is again. Okay, and it looks like the x value is going to be about 4 there. So that point will have a coordinate of about 4, 25. Call this x2, y2. Great, let's do it again. So slope is equal to y2 minus y1 over x2 minus x1. So the slope here would be the y2 value, which we defined as 25, the y1 value, which we defined as 0, the x2 value, which was 4, and the x1 value, which was 11. So let's clean it up a little bit. So it's 25 over negative 7. Okay, great. So now what we're going to look to do is now we're going to look to divide the two, right? So let's take 25 divided by negative 7. And that comes out to be, wow, that's actually, it's actually a really good guess I made. So the answer comes out, it's the same exact thing, right, as before. It's just negative now, 3.57. And that's meters per second. And that's, again, the velocity. Now, it's negative because the slope is decreasing, so the velocity is going down, which definitely makes sense. All right. So now what they want us to do is make sure, then at the end of the question, it says, make sure these values must be consistent with the graph over here. So, because now this is the velocity versus time graph. So let's take a look. The first thing I calculated was the slope, right, at 2.5 seconds. So right here, this is the velocity at 2.5 seconds. So now let's go to the graph over here. Let's find 2.5 seconds. That should be right about here. Now scroll up to where the graph is about, right? So 2.5 would be about there, right? It looks like it would be, right, if I were to go, it looks like it's about 4 here, okay? They might say, well, Andrew, you did, that's 3.5, and that's 4. Yeah, I know, it's going to be a little off, right? Like I said, my straight line, my slope, I'm slightly guessing at some of the numbers, you know, when I'm doing my calculations here, right? I don't have grid lines and whatnot, so I have to go by eye. But this is definitely close enough. It's not like the answer was 17 and I got 3. That's a problem. But, you know, so when you guys are checking over your work, if you get a slightly different answer than me, even, that's totally fine. As long as you're within a slight margin, you know, a low margin of error here. That's not a big deal. What's a low margin of error? I don't know, 0.5, you know, 0.6, somewhere around there. Okay, so that's fine. Now, they wanted us to find then, okay, so that makes sense. Now they want us to check this value here. So remember that this value was the velocity at now 7.5 seconds. So go to the same graph, locate 7.5. That would be about here. Find the point on the graph. And it looks like it's about here. Right, so my line actually looks much more accurate for the 7.5 than it was. That looks like it's about 3.5 almost. All right, but they're both reasonable, and they both make sense. So, yeah, I just checked it. Number 65. A graph of v of t is shown for a world-class track sprinter in a 100-meter race. A. What is his average velocity for the first 4 seconds? Okay, so let's dissect part A. What is the formula for average velocity? So the formula for average velocity is the velocity at one point plus the velocity at a second point divided by 2. That would be the average velocity between 2 particular points. So, in the question it's asking us the average velocity for the first 4 seconds. So what are the 2 points that correlate with the first 4 seconds? Well, let's take a look at the graph. Well, that means we have to take the point at the start, right? And what was the velocity here at the start? Well, it was 0, right? So this would be 0 meters per second. And it wants us to calculate the average velocity for the first 4 seconds, so the second point should be at 4 seconds. And what's the average velocity here at this point? Well, it looks like it'll be about 12. Right? So this will be about 12 meters per second. So now we have all the information we need in order to calculate. So let's go back to the formula. So the average velocity is equal to the velocity at 1.0 plus the velocity at another point, 12, all divided by 2. So the average velocity here will be equal to 6 meters per second. Easy peasy. Let's take a look at part B. So now it says, what is his instantaneous velocity at t is equal to 5 seconds? Okay. So the instantaneous velocity for this particular question. Now, let me, hold on one second. Let me change the color here. Okay. So instantaneous velocity at t is equal to 5 seconds. You might say to yourself, oh, well, wait a minute. It's talking about instantaneous velocity. So I have to find the slope because I know in other problems I've had to calculate the slope when I'm talking about instantaneous velocities and stuff like that, or accelerations, or whatever the case is. But not in this problem. Why? Well, you have to always consider what graph you're being given. So in this particular graph, we're considering the velocity versus time. So if you had a position versus time graph, let's say P and T, right, or a displacement graph, and let's say they gave you, the curve something like this, right, and they wanted you to find the instantaneous velocity at 5 seconds, what you would do is you would go up to the graph, draw the dot, and then, I'll put the dot in a different color, and then create your straight line, right, your tangent line. Okay, and then what you would do is you would calculate the slope. But why? Well, remember, the slope is change in y over change in x. What are the units of y in this graph? Well, it's displacement, right? So displacement has units of meters. What's the units of x on this graph? Well, it's time, right? So time is in seconds. And look, meters per second. What does that mean? In terms of physics, those are velocity units. So that should make sense. But here, they want us to calculate the instantaneous velocity, but they gave us the velocity graph. It says the runner velocity versus time. So interpreting this a different way, right? Instead of it's saying what is his instantaneous velocity, which is a valid question, but if we were to reframe it and say, what is his velocity at 5 seconds? I would be answering the same question, right? So what I need to do is, here's 5 seconds, go up to the graph, locate the point where 5 seconds would be, right about here, and then just, what is the velocity at that point? Well, it was the same at 4 seconds, right? It's 12 meters per second. So for letter B, the answer is going to be 12 meters per second. Okay, easy enough. Now let's take a look at letter C. What is his average acceleration between 0 and 4 seconds? Okay, so now again, we're thinking about acceleration. So what is the graph of? Well, the graph is of velocity and time. Okay, so how does acceleration connect to velocity and time? Well, I know the formula, right? Acceleration is equal to velocity over time. Now let's compare that to the formula of a slope, right? The formula of a slope is change in y over change in x. Now for this particular graph, guys, what are the units? So let's consider the slope. What are the units of y? They are meters per second. Okay, so let's rewrite this. So m is equal to meters per second divided by what is the value, what is the unit on the x-axis? Seconds. So what units in physics do meters per second correlate with? They correlate with velocity. What units in physics do seconds correlate with? They correlate with time. Wait a minute. I just told you that v over t is equal to a. So v over t is equal to a. But if the slope is equal to v over t and a is equal to v over t, then guess what? Simple syllogism, a is equal to m. So, in other words, the acceleration is the slope of this graph. Okay, so the acceleration is equal to change in y over change in x for this graph. So when we think about that, we have to take y2 minus y1 over x2 minus x1. Now let's find 2 points, right? Remember, they want to find the acceleration between 0 and 4 seconds. So, well, it looks like I already found the 2 points before, right, in red here, 0 and 4 seconds. But let me just now write them as coordinate points. So the point here would be written in terms of a coordinate as 0, 0. Call this one x1 and call this one y1. Now the point here would be represented as the coordinates of x being 4 and y being 12. Call this one now x2 and this one y2. And now I can just plug in the values. So y2's value was 12, as I mentioned. y1's value was 0. x2's value is 4. x1's value is 0. So this just works out to 12 over 4, aka 3 meters per second squared then. Great, so that would be the average acceleration. Now finally, for letter D, right, it says, what is his time for the race? So meaning, how long does it take? Well, actually, what is his time? What is his time for the race? What? I think it's just interpreting the graph, but it sounds too easy. So what is his time for the race? I don't know what that exactly does. Do they mean what is his, like, I don't know what exactly they're talking about here. Sorry to become a little fumbled here, but I guess, I mean, the way I'm interpreting it, it might not be totally correct, but it sounds to me like, what is his time for the race? Meaning, how fast did he, 100 meters per second. I don't exactly know what the heck they're asking for, except just how long did it take him to complete? Oh, never mind. Sorry about that, guys. You had to wade through that with me. All right. So, what they're saying here is that it's a 100-meter race. Okay? And we have in this graph, we have his velocity and whatnot. Okay? So what we're going to try to do is see how long it takes for him to cover 100 meters. Okay? So that's really what the question's asking. Sometimes these questions are a little ambiguous, but I think we can figure it out. So essentially, let me reframe D in terms of a better worded, in my opinion, question. So how long does it take the sprinter to cover 100 meters given his velocity graph? Okay, I think that makes a little more sense. All right, so let me go back to the graph and let me erase some stuff here just to make it a little cleaner so we can do our work. All right, so now, okay, so I'm going to think about this graph in 2 parts. Why? Well, because if you think about this in terms of accelerations, one, there's an acceleration going on in this part, and then there is no acceleration for this part. So hence why, since the accelerations are changing, I want to break them up into 2 parts so I can accurately calculate the displacement or the distance that's being traveled. All right? So this will be part 1, and then this will be part 2. So first, for part 1, let's calculate his displacement. Okay, so for part 1, let's calculate his displacement. Now we know in terms of part 1, the time value is 4 seconds because that's how long part 1, the way I framed it, lasts. We also just found his acceleration before, his average acceleration during this period. It's 3 meters per second squared. That's the value we found over here, right? The initial velocity we also know, right, because he's starting at 0. So we do know that. That's 0. We also do know the final velocity after this time period, right? Remember, part 1 goes up to the time of 4, and what was his velocity at that particular point? 12, right? 12 meters per second. So it sounds like we got a wealth of information and enough information in order to solve for the displacement. So we can choose a couple of ways to do this. There really is no one particular right way, but let's choose this formula. Change in displacement is equal to VIT plus 1/2 AT squared. So change in displacement would be the initial velocity, but we know that that's 0. So what happens to this whole term? It goes bye-bye. Plus 1/2, now times the acceleration, which was 3, and the time was 4, and that'll be squared. So let's see how far he traveled now. So 0.5 times 3 times 4 squared becomes 24. So this is 24 meters. Okay, great. So 24 meters. All right. So what I'm going to write over here, I'll write it above here. So at 4 seconds, he traveled 24 meters. Okay. Now tell me, how much longer does he have to go? Remember, it's a 100-meter race. Okay, so I don't know if you're talking to the computer screen, but that sounds good. We would take 100 meters and then subtract out the 24 meters that he just traveled to find out how much he has left. So how much would that be? 76 meters. So he's got 76 meters left to go, right? Now we're entering phase 2 of his velocity, right? This particular part. So tell me, what do we know about now phase 2? So I'm going to write phase 2 over here on the bottom right. So for phase 2, what do we know? We know the velocity he's traveling with, right? The initial velocity, which would be the start of part 2, is 12. The final velocity of part 2 is going to be, right? It's just going to continue on out, is going to be 12 as well. Okay. Now, why is that? Well, that is because there is no acceleration, right? If you were to think, what's the slope of this line? Remember, the slope of the velocity versus time graph will tell you the acceleration. What's the slope of a straight line that is perfectly horizontal? 0. Okay, great. So that's the acceleration. The time now, let's say the time is what we're trying to find. I don't know what the time will be. All right. And I also know just what I just calculated before, that he has 76 meters left to go. Okay. So can I find the time given the information I have? And I think we can, right? Now, which formula would you like to use? Right. So we can use a whole bunch of them, right? There's a couple that we can use. So it doesn't matter to me which one you choose. Some might be, harder than others. One formula to use would be the displacement is equal to initial velocity times time plus 1/2 AT squared. All right. Why don't we, since I just wrote that down, why don't we use that? Okay. So another one, right, might be just you could think about it in a simpler form, but actually this formula will work out to be simple nonetheless. Why? Well, let's start it. Change in displacement, which is 76, will equal the initial velocity, which is 12, multiplied by time, which is what we're trying to find. Plus then this piece. But what's the acceleration, guys? 0. So what happens to this whole term? Bye-bye. So there is no piece on out here. Okay? So problem just works out to be this. All right, and this would have been the simpler formula, like I was saying. You could use a couple of different formulas. Could have just gotten down to the simplicity right away. But if I got to solve for time now, I'm going to divide out the 12. So the time here, so let's do 76 divided by 12. So it works out to be 6.33 seconds. Okay, great. Now, if we found the time, right, or if we knew the time for part 1, so the part 1 time was 4 seconds on the bottom left of the page. 4 seconds. And the time to complete part 2, given he needs to travel 76 more meters, was 6.33. How would we find now the time it took him to run the 100-meter race? We would just add, right? So essentially the formula is the total time is equal to the time from part 1 plus the time from part 2. So the total time of this race is going to be the 4 seconds from part 1 plus the 6.33 seconds from part 2. And when I add them together, I get 10.33. And I wasn't even considering significant figures here, but it probably would work out to be 10.3 or something like that, or just 10. Number 66. Figure 2.68 shows the position graph for a particle for 5 seconds. Draw the corresponding velocity and acceleration graphs. Okay, so we have a position versus time graph here. Now, somehow we have to, from the position versus time graph, create a velocity versus time graph, and then create an acceleration versus time graph. Okay, so the first important step will be, how do we go from position versus time to a velocity versus time? Well, in order to figure that out, let me just erase this stuff. In order to figure that out, we have to understand how position is connected to velocity via the graph. So recall what slope is. Slope is the change in y over the change in x. So what, in this graph, in position versus time, what are the units for the y-axis? It would be meters. What are the units for the x-axis? They would be seconds. And in physics, what do you know meters per second to be? Right, velocity. So the slope of the position versus time graph is the same thing as the velocity. So what I need to do here is I need to find the slope of this graph. Now it looks like the lines are all over the place, right? And they are, but that's fine. We have to treat this as like a piecewise function, or essentially a graph that will have 4 pieces to it. I think 3 comes after 4, right? Yes. Okay. So we have 4 pieces. Okay. So I'm going to dot the points in between each piece. Okay. Beautiful. Now what? Just to clean it up a little bit, let me just erase these numbers here. Okay. All right. So we got the 4 pieces, and I'll include the dot for the end mark as well. So let's consider this first segment, segment number 1. What's the slope? Again, remember, so I'll call this segment 1. What's the formula? Well, slope is equal to change in y over change in x. Expanding on that, it would be y2 minus y1 over x2 minus x1. Okay, wonderful. So what that tells me is that I need 2 points. Well, I already dotted them, this point and this point. So what are the coordinates of this point? Right, it would be 0, 0, right? The x value is 0, the y value is 0. So let's call this one x1 and my y1. What are the coordinates of this point? Well, it has an x coordinate of 2 and a y coordinate of 2 as well. So it'd be 2, 2. Let's call this the x2 and this one the y2. Wonderful. And now all we have to do is plug them in. So my y2 value is 2. My y1 value is 0. My x2 value is 2. And my x1 value is 0. So 2 over 2 is equal to 1. So 1 meter per second would be the velocity over, so let me write this, over the first 2 seconds. Okay, great. Let's look at segment 2 now. All right, so segment 2, we're going to be looking at it from this point now to this point. So we need the coordinates. Again, I need to find the slope from between those 2 points, right? So slope, and I'll call this segment 2, right? So the slope is equal to change in y over change in x. Same thing, the slope is equal to y2 minus y1 over x2 minus x1. So the slope here will be, I need to find the points. So I already found the coordinates here. All right, now let me start with the coordinates here. So this looks like it has an x value of 3 and then y value of -3. Right? So 3, -3. And what I'm going to do is, since I already labeled this x2, y2, I'm just going to call this x1, y1. All right, just so I don't have to keep going back and erasing stuff. So now, when I'm considering those 2 points, right, I said that my my y2 value is 2. My y1 value is -3, so it's 2 minus -3. Divided by my x2 value is 2, And now my x1 value is 3. Okay, so let's see what we get. We get now 5 over 1, right? And specifically negative 1. Now that should make sense. The slope is negative. It's pointing down and to the left. To the right. So this is negative 5 meters per second. And that will be equal to the velocity. And that's over the next 1 second. So meaning that from 0 to 2 seconds was my velocity in red. Now from 2 seconds to 3 seconds, right, was my velocity now in yellow here. Let's do the next segment, segment number 3 now. I think you guys might be seeing the pattern. I need to find the points of these two. I already found the points here, so I'm going to keep that. I got to find the point here. What are the coordinates? Well, it looks like it has an x value of 5. And its y value should be the same, negative 3. Okay, so let's call this, since these are my x1, y1, let's just call this x2, y2. So same thing now. For segment 3, the slope is equal to change in y over change in x. Slope is equal to y2 minus y1 over x2 minus x1. So the slope here is equal to my y2 value, which was negative 3, my y1 value, which was negative 3, so it's a minus negative 3, divided by x2, which was 5, and then my x1, which was 3. So my slope here in black will be 0 over 2, which works out to be 0. So it's 0 meters per second, that's the velocity, over the next 2 seconds. Right? Because the segment 3 went from 3 seconds to 5 seconds. So here we go from 3 seconds to 5 seconds. And now finally, last but not least, let's do segment number 4 here. Okay, we need the 2 points. We already have the coordinates here. So let's find the coordinates of this point. It looks like the coordinates there should be 6, comma, looks like about negative 2. Right? Since these are x2, y2, let's call this x1, y1. And again, segment 4, right? Slope is equal to change in y over change in x. Slope is equal to y2 minus y1 over x2 minus x1. So slope here will be equal to my y2 value, which is negative 3, and then minus a negative 2, okay, divided by my x2 value, which is 5, and my x1, which is 6. Okay, great. So how do the numbers work out? So the numerator is going to be a negative 1 divided by a negative 1. So the slope here becomes positive 1, right? Or just 1 meter per second. That's the velocity. Okay, and this is over the next second, right? 1 second. Because we went from then 5 seconds to 6. Okay, great. So we got all this stuff going on. All right, so now we have enough information we need in order to finally graph the velocity versus time graph. All right, so let's draw an axis. I'm going to draw it on the upper left. Okay, let's draw something that looks like this. Okay, so let's put in some markings here. Say this is 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, negative 5. That should be good enough. Okay, so I also need my x, right? Let's call this 1, 2, 3, 4, 5, and then 6. That should cover all the time. Okay, so now for my first segment, right, from 0 to 2 seconds, what was the velocity? We calculated it to be 1 meter per second, right? So go to 1 meter. So remember, I should have labeled the axes. Remember, this is the time axis, and this is now my velocity axis. Okay, meters per second. So go find 1 meter per second. That's right here. And draw a line that represents 1 meter per second for 2 seconds. It would look just like that. Let me actually autocorrect so it comes out nice and straight. There we go. I'll make it a little longer. Okay, I don't see the difference, but okay. So next thing what we're going to do now is we're going to take a look at the next segment, right? So what's the next segment? Well, the next segment occurs from 2 to 3 seconds, right? So just the next second, and its velocity is -5. So locate -5 on the graph. So here it is. Now what you have to do here is draw a line down, straight down to -5. And that's not exactly straight. Line straight down. Okay, that'll do. And now what we have to do is for the next second, make a straight line at -5. So we have something that looks like that. Okay, great. Now, moving forward, let's find now the next interval, or segment 3. It says that on segment 3, the velocity was 0 meters per second, and that occurs from 3 to 5 seconds. So now what I need to do, go back to the velocity graph. I need to now draw a line straight up to where the velocity is 0. So the velocity is 0, remember, right at the x-axis. So I have to draw my line straight up. So it's going to come right up to 3 or so. Okay, great. And now it's going to be, I have to represent now 0 velocity for 2 seconds, right? Or from the time of 3 to 5. So it looks just like that. Okay, great. We're almost there. We just got to do one more segment. Okay. And now, for the last segment, right, take a look. So over the time interval 5 to 6 now, what's the velocity? The velocity is 1 meter per second. Okay, wonderful. So let's do that. So we got to go back to our velocity graph, draw a line up to about where 1 second is. So it looks like it's about there. And now draw a line right on over. And it looks like it goes to there, right? Okay, so that is perfect. And it looks like now the graph has stopped, right? There's no more continuation. So what we could do from here is we could leave the graph like this, or we could bring the line back down to the starting point, because if I assume that the object, looking at the graph in the upper right-hand corner, if I assume that the object stopped here, then I know that the velocity should have been 0. So I can just bring this back down if I like. All right, so now I just graphed the velocity versus time graph. And this is exactly what it would look like. Okay, now all we have to do is the acceleration graph. So let's erase everything. No, we're not going to erase everything. It's actually going to be a lot faster. Why? Well, remember, if I were to create an acceleration graph, I would have to create it understanding the slope of my velocity graph. But what's the problem with some of the slopes here? Like, what's the slope of this line? It's not 0. It's undefined, right? It's undefined because if I think about what slope is, m is equal to change in y over change in x, right? From this point here, I'll dot it, from this point here to this point here, how much does the x value change? Meaning, what's the x value of this point? It's 2, right? What's the x value of this point? Well, it's also 2. So if I, in terms of my formula here, if I plug in 2 minus 2 in the denominator, what does that become? Well, it becomes 0. And what happens when 0's in the denominator? It becomes undefined. So you really can't even draw an acceleration graph for this, right? I do know at certain points the acceleration is 0, and then here it's here for this path it's 0, then for here it's 0, then for here it's 0 because there's no change in velocities over that time. But when the velocities do actually change, they're undefined changes. They're not smooth, continuous changes. So therefore, we can't really even graph the acceleration graph. So, doesn't feel satisfactory, especially since this is the last problem in the chapter. I always like to end on a bright note, but it seems like that's going to be the case, guys. Hey, you made it. Excellent work. I'm really proud of you. Great job. I really do hope the video helped. And for the next video in the series, please click this button right over here. And if you wouldn't mind giving us a hand, if you really found the video helpful, why don't you subscribe, smash that like button, and tell your friends. All right? We really appreciate it so much, and we really look forward to helping you with more problems. We'll see you soon. Bye.